So we allowed today, we're allowed today to stay here. And another peculiarity of this place is that the chairman has extreme power. I have a red button which mutes all microphones. So please follow I'll try to follow the schedule. And the first talk today in the morning is the presenter is Sergey Frolov, and the topic is searching for triplet superconductivity nanostructures. I will give you 5 minutes before 25. So we keep the formula 25 plus 5 for questions. Thank you. And the green button, if you press the green button, you can ask the question. Only after you press the green button. But remember, I have a red one here.
Thank you, Mr. Chairman, for your great leadership, and we fully submit to your great powers. Okay, before we get to the scientific part, I would like to explain several things. So this slide, or a version of it, is something I showed in every single talk I gave for the past 4 and several months, years. And so it's not just for this audience. And of course, this shows the destruction of some of the labs, specifically in Kharkiv. And since then, since the invasion started, I reached out to some of the colleagues in Ukraine. I actually didn't know too many who work in Ukraine, but I connected especially with people in Kharkiv because there is a strong activity on condensed matter physics. And Ksenia, for example, visited us in Pittsburgh as well. This is Ksenia Minakova, and this is her lab, and she's carrying out these broken instruments. Since then, we also had some success organizing at the appropriate level. So we are here thanks to the German-Ukrainian project, and some of you may know that we also organized something with the support of United States National Academy of Sciences, and the NSF, and there is also funding from Poland. It's a 3-country program, and it's something around quantum science, quantum physics, mostly with Kharkiv, and it's a number of projects. Colleagues in Kharkiv started a master's program in quantum computing, and there's a Kharkiv Quantum Seminar, which some of you participated in, and it actually took place yesterday, I believe. While we are at the conference. Andrii Sotnikov is one of the organizers of that. And there's many other things. And one of the things, of course, research collaborations, one of the things we also do is what is shown here is we collect surplus equipment, try to develop approaches to it, and we deliver it to Ukraine. And this is not a theoretical concept, because here you can see in Pittsburgh, this is Tatiana Mikhailova. She's a lawyer with Ukrainian and American degrees, and she is my partner in this. And here are the boxes, and here are the same boxes, believe me. And they are now in Kharkiv, and there is more boxes on the way, and it is things like lock-in amplifiers, pumps, and cryogenic magnets, and things like that that we collected. And so I hope there'll be more of this going forward. And if you have some ideas about that, I'm happy to discuss. I already discussed with some of you on this as well. Okay, and now this is my lab. So I'm an experimentalist. I do low temperature transport and also increasingly microwave, things like qubits, transmons, etc. With low dimensional systems. This is our main building of our university. It's a pleasure and honor to be here in this beautiful building, but this is where we are. This is my labs, my students, my PhD students. And so we do nano fabrication in the clean room, and then these low temperature measurements, but we don't grow the crystals. So crystals come from all these wonderful people that are collaborators in Europe, as well as in the United States, and they are nanostructures, low dimensional, high quality, mostly semiconductor crystals. Like these are semiconductor nanowires, indium arsenide, grown specifically in this crisscross configuration because they're grown on a 1, 0, 0 substrate. So they grow in the 1, 1, 1 direction. So we take advantage of this crisscross to deposit superconductor, like think that it's coming into the screen, and then it creates shadows. So create junctions. So we study sort of not bulk, but devices like Josephson junctions, quantum dots, quantum point contacts. I'm saying all this because the conference is heavily in the bulk, so I would like to explain. So this is a called selective area grown structure where a substrate is masked with a dielectric, and then in the opening of the mask, a semiconductor is grown on the substrate, creating, in principle, an arbitrary structure, but in this case, also a wire. And then a very tall shadow wall is built in front of it, so that superconductor is deposited from this direction, creating islands and chains and things like that. And this is I will not explain, but there is a quantum well underneath, so it's 1D, 2D, 0D objects that we study. Okay, and I'm grateful to the organizers of this. It's meaningful and emotional to be here in Ukraine. For me, I was born here, but also because I get an opportunity to talk about the sort of exotic physics, because most of my talks are either about devices like qubits, quantum limited amplifiers that we do with these same nanostructures, or they are about fraud in science. If you don't know why, I will highlight it a little bit. So basically, I created a mashup of the two talks, and it's about some exotic superconductivity, essentially. Okay, click back. Okay, now how do I click back? Scroll. Great. Merci. The not just triplet, but also, related things like chiral superconductivity, topological. They are certainly my main interest and all my research geared towards it. But I also have a dilemma because at this moment in time, I do not believe I have studied any existing exotic superconductivity. Okay. So I've done a lot of work in this direction, but I don't think any of the things I found are very exotic superconductivity. Maybe a FFLO state in the SFS Josephson junctions was my PhD. But still, it's a fascinating activity that is really worth doing. But you have to have at least for me, a certain set of mind where it's not about the result within the next 6 months, but it's a process. So build a process which will, with higher likelihood, give results, right? So that's how reliability, reproducibility in science comes in. And the reason for this is because, my PhD was in Urbana-Champaign in the early 2000s. It was a Sean scandal, the high-flying guy. But also, if you know Urbana-Champaign, it's a place for high-temperature superconductivity for a lot of the things that you also work on. And all these wonderful people were there. And already back then, of course, we know BCS theory allows for triplet superconductivity. And so the question comes, well, which one is the triplet one? Can we build it? Can we find it? And at that time, strontium ruthenate, this material, which many of you, I'm sure, know, was sort of the triplet superconductor, potential triplet superconductor. And so fast forward 20 years, we have this news and views or Nature highlight, triplet no more. Right? This is about the same material, strontium ruthenate. And it's written by editor David Abergel, and I believe based on the work of Stuart Brown from UCLA, who himself in the early 2000s thought he discovered a triplet superconductivity in strontium ruthenate. And then later on, we did some of the experiments, put some strain, and thought, well, maybe it's not. And so now I think the awareness is spreading that maybe this specific one is not. But I should also say, really, I don't do bulk. So this is just I read these papers. I don't do anything with these crystals. So this is more to say that, of course, you can find triplet superconductivity in a bulk crystal. Now, my interests are more in the more engineered structures, interfaces, and so on. So this picture is actually from our paper 2012, where we thought we found Majorana fermion in a nanowire of semiconductor, very boring, non-interacting, just a 3-5 semiconductor, but it's low dimensional, and then a very conventional S-wave superconductor, niobium tinitrate deposited on top. And I will talk a little bit about this. Fun fact, this was published in Science. And if you open the magazine and you look here, we snuck a portrait of Ettore Majorana on the end of the wire. And then another thing that I just recently started this activity, it's again the same, by coincidence, the same superconductor. And you can see the triplet Cooper pairs flying around here. But it's because it's coated with molecules that have some chirality to them. And so there is a whole research direction where they study these chiral molecules. It's called Chirality-Induced Spin Selectivity effect. So it's a non-magnetic material, but they pass electrons through it or they pass light and it becomes spin polarized. And it's a bit of a mystery. I haven't made up my mind about this field, but we're trying a little bit. Okay, so just a brief, essentially, update on Majorana. It's been a lot all over the place. I don't want to take too much time, but it's, of course, a particle is on antiparticle, and it's in the context of relativistic quantum mechanics, and maybe neutrino is a Majorana. And well, one good thing about it is that theory seems to be solid. These are three of the essential theoretical works, starting with Kitaev toy model, and then a more realistic proposal by Fu and Kane, where they thought, well, if we took a topological insulator and put a superconductor on it, we could induce Majorana modes in a hybrid structure. And then the one we work on is this Hamiltonian that I will explain a little bit in a little bit more detail, and it's 2010. It's already some time ago. Well, of course, all of these are derived in some approximation, like Boголюбов, Dejean, or so, right? So and of course, BCS theory is an approximation. So we don't know for sure that we can build them, but there is a great degree of confidence that it can, in principle, be achieved. And there is a huge variety of platforms where these Hamiltonians are being implemented. And until some recent events in the last 5 years, I would say, well, the nanowires are the leading one. And now I don't say that anymore, although nanowires in principle check all these boxes on the right, because it's a reasonable proposal in terms of the combination of terms in the Hamiltonian of the right magnitude, like you find in a nanowire, like spin-orbit interaction, superconductivity induced, should work. And it's verifiable because we have techniques to verify Majorana based on tunneling, even though there is some ambiguity, but with more attention to details, essentially, you can overcome that. And then these two other ones, it's more if you want to build a quantum computer out of them, but if you want to verify their non-abelian properties, you go down the list here. And of course, semiconductors are scalable because we scale them in our CMOS chips. So this is one of our devices from Pittsburgh. It's an indium antimonide nanowire. It's an interesting semiconductor. It has very low band gap, like 200 milli-electron volts, because of the huge spin-orbit interaction. G factor is around 50, and there is no Schottky barrier to metals, which is very lucky because then we coat it with the ultra-thin layer of tin superconductor, beta tin, and you cannot see the tin. It's so thin, it's about 10 nanometers, 15 nanometers. And that's because it's deposited at low temperature, cryogenically, and the interface is gently cleaned with hydrogen. So there's all these tricks you have to do because the interface quality and the overall quality of this nanostructure is what makes a difference between Majorana being there and not being there, which is the current status. But basically, you take one-dimensional system, which is realizing this Kitaev toy chain Hamiltonian, essentially, and superconductivity pairing between sides of the Kitaev chain is induced externally by the superconductor. Then you need to break fermion doubling problem because there'll be two Majoranas if there's two bands. So you do that by very large magnetic field, and one of the bands just goes away. So you have a one-band system or an odd number of bands system, and these are one-dimensional bands, right? Think about parabolas. Just have one parabola crossing the Fermi level in the ideal case with induced gap. And then spin-orbit interaction, well, you can think of it as, well, magnetic field destroys conventional superconductivity, the S-wave type, because it's singlet. And then spin-orbit offers a bridge because it cans the two spins, the spin up and spin down. So it offers a bridge into the triplet phase. So there may be some kind of a phase transition. At the critical field, you normally kill superconductivity, but then because of spin orbit, it is allowed to reopen as you keep increasing field. And you go into the exotic phase, into the triplet phase, into the topological superconducting phase, and Majorana modes pop up at the ends of the wire. That's the goal of this research. And this is, you know, this part should be okay once we dial in this nanowire. So yeah, there was a theoretical prediction that there should be a zero bias peak at the transition point, so at high magnetic field, and we built devices like this. You're already familiar with a nanowire and a superconductor, and this left part is essentially the tunneling probe. Think of your STM, but it's parked at the end of the wire, because this left side of the wire, we wire it with electrical circuit and a non-superconducting contact. Then electrons go into the wire and they jump over this tunnel barrier. And if there is a Majorana there, there will be a signature, a bit increased conductance, increased peak in this tunneling transport data. So here, this is our paper from 2012. Which started this madness. And so you can see these peaks. These are just induced superconductivity peaks. And then in the middle, a little peak that appears at about 100 millitesla is also rigidly pinned to zero bias, which was very interesting and maybe one of the sort of smoking gun for Majorana that, remember, G factor of indium antimonide is 50. So if it were an electron that had spin, it would move like crazy. For instance, this is a 1.5 millivolts here. So in 1 Tesla, which is this distance, it would start on the bottom and cross all the way to the top of this graph. That's how much Zeeman energy these electrons have. Instead, we've studied a zero bias peak, which is over the same range, just kind of pinned to zero bias. And so that was not seen before and fed so many theoretical predictions. And then post-dictions, and you know, there was about 1,000 theoretical papers written before and after this experiment. And this is a replication in Pittsburgh of this original experiment in Delft. And I'll be showing some of these color maps. So this is conductance. This is just the conductance from left to right in this device. And the color is, you know, white, bright is high, red is high, and blue is low. So this will be the superconducting gap at low field, and then it closes and then leaves behind this feature. This is the kind of stuff that we studied for a while. Okay, so then this is, we are here because of, I hope, fundamental interest in the physics of exotic superconductors, but there is another class of questions you can ask, and can you manufacture these? Can you harness their properties, because they also have nanobillion properties, which I will not talk about here, but they are allegedly useful for quantum computing, which is more of a sales pitch, to be honest, because not all the gates are protected topologically. But it goes something like this. You have these Majoranas sitting now in a two-dimensional plane, so you have to, at some point, abandon the wire and go in 2D. And then you move them around, you make knots in space-time, braids, and in these braids, quantum gates are encoded, and at the end of the day, you read the parity of these islands. And so some people took this concept very far, and there is literally probably over $1 billion now that's been spent, let's say, on this type of computers. And okay, quiz. Who thinks that Bill Gates is the main guy at Microsoft? Raise your hand. Okay, very good. So, okay, who knows who this guy is? Ah, Flavio. Do you push a button and say
Satya Nadella?
Satya Nadella? Thank you. So Satya Nadella is the current CEO of Microsoft, which is okay, I didn't read the stock market this morning, but it's somewhere between $3 and $4 trillion company. And this is him presenting this last week, Monday, at Microsoft showcase to developers. And this is a chip which is Majorana 2. So if you missed Majorana 1, that was last year, but this one is just from 1 week ago. And it's a little bit confusing, the slide, but this behind Satya here is what Microsoft says about the chip, reliability, blah, blah, blah. And this is what the press says about it, so especially the scientific press. So it's Scientific American, Nature, Science. And you can see some of the keywords there: fundamental problem, skeptical, and controversial. And this was a sort of a reception of this talk. Yeah, I'm moving very slowly. At the same time, people we trust more, like Professor Carlo Beinacker, who is one of the biggest cheerleaders and would be very happy to have Majoranas there, says that there is no convincing evidence for Majoranas. So what is the problem? The problem is there is a doppelganger of the zero bias peaks that comes essentially from a trivial, essentially quantum dot with bound states hybridized with a superconductor inside the dot. Sometimes they're called Andreev bound states, but because of recent events in Russia, I prefer to call them by Silvano, who is Italian, and he did the first experiment that showed that such a feature can survive for a large magnetic field because of some level repulsion. So basically you have spinful states that move to zero energy, but then they cannot leave zero energy because of trivial reasons. There is no topological phase behind them. And these quantum dots tend to form because minor disorder can lead to their spontaneous formation. So Silvano did it on purpose, but it can also occur sort of naturally, and it's a difficult problem to deal with. And so it's a material science problem, which we are dealing with now. We are engineering the wire, improving the quality of the crystals. We have some successes. We change materials around and we work on these different features. Ideally, you have this topological wire realized in a fully epitaxial, but a very complex structure with also an interlayer tunnel barrier between. And so we are working on this. This is an unpublished work where we actually coated indium arsenide with a zinc telluride shell. This is fourth work. So indium arsenide core, zinc telluride shell. So this will be to protect the core and also to create the tunable tunnel barrier to the superconductor. So this is one of the works we're doing. There's some DFT. Now I wanted to mention briefly these chiral molecules. Well, there's not much to say really, but just for the sake of it's more about the rigorous science. Unfortunately, my collaborator passed away, so I don't know if I'll continue this work because the chiral molecules come from them. But basically, you make a superconductor, put chiral molecules, and there is, believe it or not, a body of work that say something like superconductivity plus chirality equals chiral superconductivity. And so we are checking this hypothesis. It's a well-defined problem. So here's some XPS spectrum where this blue peak, I'm really not an expert in XPX, but it says that these SAM, which are these molecules, are deposited on the surface, so they're there. And as you can imagine, there is some effect. So like the gray curve is a Bayer film, and then with molecules, the critical temperature of this film shifts, typically down. And then the red and the black are chiral and no chiral, and you can see, well, sometimes chiral is lower than ichiral, sometimes the other way around. The critical temperature also, critical magnetic field also shifts somehow with respect, inconsistent with TC. Well, if you look at the statistics of this, well, for very thin films, there is, we can see that TC drops for thin films. But when we go for thick films, even not very thick, there is no difference between chiral, achiral, and even bare, and that's also understandable because it's just a surface effect. So you have a big thick film of conventional S-wave superconductor, and then sprinkled on top something chiral. Okay, there is no effect. Now, when you make the film thickness very, very thin, it starts to fan out, so there is some effect. And that's, of course, could be many different things. A very thin film, and you mess with its surface, you passivate it with these molecules, you partially remove the oxide, it's still there. You may be able to dope this film, change the density, and by that measure change the TC, according to the BCS theory. But there is no systematics in, which way the dots go. So at this point, this will be probably some kind of baseline study. If we want to take it further, we may want to create some more clever schemes with these chiral molecules, but it's also possible that the effect is simply not there. And so in the last 1 minute, I just want to highlight that my other activity, inspired by the zero bias peaks that I can even fine tune to be quantized according to the predictions of Majorana, led me to believe that at least in this field of mesoscopic physics, even such dramatic patterns are predicted, like critical current growing with magnetic field, some missing features like Shapiro steps, fractional jumps, can all be fudged essentially. If you shuffle through gigabytes of your data, you will find the pattern that the theory predicted. And so we published these 4 experiments in Science. Even though they show dramatic features, they are all trivial effects. So this is something to think about. For instance, here is supercurrent growing with magnetic field. You can see 0 Tesla is lower, and 0.6 Tesla is higher. So that could be triplet, right? Because one way how to find triplet, well, it's resistant to magnetic field. Magnetic field doesn't destroy triplet superconductivity. So maybe this is it. This is in a Josephson junction created by the same nanowire. Well, if you look broader at the data, along this dashed line, it is growing with field, but outside this dashed box, it is shrinking. So it's some kind of mesoscopic effect where critical current ebbs and flows, and sometimes at some field here, it's bigger here, it's smaller here, and I can select the data to look like triplet. This is one example I wanted to show you. I want to highlight this one also because this is a theory that is one explanation for these patterns. And the reason I'm showing is because this is also an undergraduate student from Kharkiv who I worked with remotely that did these calculations of this simple classical model. This differential equation is called an RSJ model in Josephson physics, and you basically just solve this equation with some conditions. You make a bias-dependent resistance at the right spot, and you can suppress or enhance critical current at will in this device. There is also reentrances, which I will not talk about, but this is a paper on arXiv where we go to very high field and you close the gap and reopen. It's a 2D material, and this was predicted to be due to Majorana or pi junctions, but it can also come from trivial effects like interference. And so the idea would be that one phase is killed, the other one appears, right? Same as with Majorana. So this region would be triplet, or this region here in gate voltage versus field. But there is another explanation for this one as well. So we have to be really extremely careful. There is a theory, which is, again, a trivial model, very simple model, some disorder in a junction. And by the way, you can take graphene. It's atomically flat, perfect. There is no third dimension, right? Except, of course, we know there is a little bit of ripples in graphene. And if you put the field in plane into the graphene flake, you go to 1 Tesla, you start threading about the flux quantum with in-plane field. So this is sort of the pitfall here. Okay, and the last one to scare you all for the rest of the day. Me and my wife wrote this paper, very proud of it, is on arXiv as of last week as well. Last week was very big in fraud. So this is actually our data from my postdoc from 2019, and this shows this trivial Andreev crossing or Silvano crossing So these states are just bound states in a quantum dot that experience magnetic field Zeeman splitting, and they cross at zero bias here. Now go to ChatGPT and say, hey, ChatGPT, can you please add a zero bias peak that starts about here and goes all the way to here? So this is like 3 minutes of work. And well, here it's because you can still see it's a crossing. And if we want to see a gap closing and reopening, we want this bulk states to come down and then move back up. So here I ask, hey, ChatGPT, can you identify these crossing states? And then for higher bias than that, raise the signal a little bit. So I don't know if you can see it, but these are brighter. And then combine the two effects. So now we have made a discovery of topological superconductivity, because here we have the gap closing and reopening. And at the gap closing and reopening, a new state appears, and Majorana zero mode. Right? So this is about half an hour of work. And of course, what we see in a typical Nature paper is just 4 or 5 of these pictures. And the solution is simple: share your data. So we put some effort into this. There was a conference in Pittsburgh with some big names came to Pittsburgh, and we wrote this report on reproducibility in condensed matter physics. It's now published, and the main idea is share all your data, and then it will be helpful for many things like verifying your results, but also maybe people can build on your work more effectively. So hopefully this will be adopted broadly going forward. We made a movie. I encourage you to watch. It's about half hour, different people giving interviews, including some famous people like Jessica is the executive editor of all APS journals, and Carl is a Nature guy, where here in this screenshot he says something like, to consider a publication in Nature in career promotion is, I don't know, stupid or something like that. That's from the editor of Nature, so keep that in mind. Okay, well, there is something about, open science is just very natural to people, so we should just call it science. And remember why we're all here, and thanks to all the Ukrainians who are working in Ukraine, outside Ukraine, and thanks to all the non-Ukrainians that came to support this conference and to engage in these wonderful collaborations. It's really extremely meaningful. Thank you.
Thank you, Sergey, for this talk. Wonderful talk. We have time, unfortunately, only for one short question.
Yeah, sorry.
I try to be short. I do not expect the short answer, but actually, the Majorana zero mode, it is considered to be useful because of its stability. So what you've shown, which of the experiments would be demonstrate this stability from what you've shown? It is, or why not to demonstrate directly this stability?
Well, look, this is pretty stable, right?
Yeah, it is here.
Yeah, no, yes. I mean, this is a sales pitch, stability, right? So, like I said, I'm after just to find some exotic physics in these structures. By the way, I think, semiconductor platform still has a lot to offer because of how manufacturable and how tunable it is compared to some of the bulk, for instance, crystals. The requirements are always high. But at the same time, I think we all know that topological effects are. This is a sales pitch that they're stable, because many of them are not. Right, the symmetry protected topological phases. So we kind of, to me, the way it developed is the quantum Hall effects in the early '80s, and those are really difficult to kill. And then many of the other topological phases are a lot less stable. But they
just my personal experience. I first believed that actually topological surface states in topological insulators are real because we saw that it is stable, not because of a bunch of Hassan's papers, but it was really stable because so it's stable to impurity, really. Much more than normal state.
Yeah, well, okay, maybe the 3D ones, but the 2D ones, there is still ongoing debates, right? If they're a lot less stable than we thought they would be.
Okay, I suggest to transfer this discussion to the coffee break. Let's thank the speaker again. The next talk will be given by Eteri Svanidze, and the title is Design and Discovery of New Quantum Material. How to switch to the online presentation? Okay, so we have it. Eteri, I will briefly interrupt you when you have 5 minutes left, if you don't mind.
Oh, yes, please do. Thank you so much. Can you hear me okay? Hello? Can you hear me?
We see your screen.
Can you hear me?
But we don't hear you very well, Eteri.
You do not hear me.
Now it looks good.
Now it's better? Is it good?
Now it looks good. We see your screen and looks like
You can hear me. Okay, excellent. Okay, thank you. Okay, well, good morning. Thank you so much for having me. I really wish I could be there in person, but unfortunately I could not, so my apologies. So yes, today I would like to talk about design and discovery of new quantum materials, and briefly to tell you what it is that my group does and why. So my group is primarily interested in, again, new materials and ways of finding them. We combine really the physics and chemistry perspectives, and I would say that my group is 50-50 in that regard. And in addition to, let's say, our core, we're benefiting from a lot of visiting scientists that come from us, and actually this Lev, Olga, and Olga, the other Olga, are all coming from Lviv, Ivano-Franko University. In terms of topics, what we're interested in is a number of various things, again, coming from chemistry and physics. I will, in principle, discuss some of the materials, but more globally, we'll like really complex structures with more than 100 atoms per unit cell, something that is computationally is not trivial. We like to spin engineer, and this is a topic I will touch up on in terms of combining different magnetic species to discover new phenomena. In terms of structure, we're really interested in determining how exactly the small impurities are affecting the physical properties. I believe there was already a talk 2 days ago on the uranium ditellurate system from Yuri Grin. Disorder sort of comes hand in hand. Again, many materials are disordered, even though we don't want to believe it. And we're interested in seeing how this disorder affects both conventional and unconventional superconductivity. Topology is something that has been coming in recently, and of course, we also are interested in that. And non-centrosymmetric materials give us another way to tune our systems. Actually, for this talk, I will cover topics that were primarily contributed by Oksana Periturt, who is currently a student in Lviv. She actually came to me on a couple of DAAD visits, so this program I can personally highly recommend. She was exceptionally productive, and I will show some of her work. And Nazar actually did his PhD and master's also in Lviv, and he's currently my postdoc. Great. So more of a global topic that I will cover today is arsenides. And when we talk about arsenides, immediately you probably think about the iron-based superconductors and how they sort of changed our perspective on superconductivity. I'm sorry to disappoint you, but in fact, the talk today would not be on the structures or the architectures that are shown here, but rather on other arsenides. And what I want to showcase by this is that there are still many, many materials left to be discovered, even among arsenides. Great. So the plan for today is threefold. I will briefly discuss 3 ways of finding new materials, and we will start by discussing unexplored places, or in principle going where somebody hasn't gone before. So if we think about arsenides and uranium in the uranium iron arsenic ternary, the first material that was ever reported in 1992, note that again this was before the superconductors came sort of into play for this. It was 112 system, which was crystallographically well described, but physical properties were not known. So going into this, our original plan was in fact to try to synthesize this material and trying to see what the physical properties are. To be honest, it's actually not currently possible to make it phase pure, but what happened instead, we discovered a new material. 153. So you can see it can be grown as large, millimeter size, single crystal, stable in air. The structure is uranium, chromium 5, phosphorus 3. And you can think of it this way, where this is the uranium atoms, this is arsenic, this is iron. But a more common way to think about it is actually this shamrock patterns, where the shamrock, the center of the shamrock is uranium. Then you have sort of shamrock or windmill, whatever you choose to describe. And uranium here is actually following a line. The bold is the layer closer to us. The faint is the layer further away from us. And again, they're typically referred to as shamrocks or windmills. Of course, for me, this has a bit of a different way to present it. Nonetheless, when thinking about physical properties, we thought, okay, so there are many, many materials in this shamrock family. What if we could try and sort of predict the properties based on the structure? So this is the first example. We have the shamrocks following a line. And in fact, besides the uranium iron 5 arsenic 3, we also have yttrium nickel 5 silicon 3, which also sort of forms this line. Second possibility that you have, instead of a line, you have a zigzag chain. And here we have the centers following the zigzag chain for this cobalt system with lanthanum or yttrium. Third and last, instead of having zigzag chain line, you will have two different types of islands. Here we have the smaller island containing the centers of the shamrocks, or sort of a bigger, almost star-shaped island connecting 4 instead of 3 shamrocks. So when we looked at the 153 system with the uranium and iron, we found out that actually it is antiferromagnetic around 50 Kelvin. It does not have any frustration. But in principle, as you go to the other end, where you have the islands, it is still antiferromagnetic at 30 Kelvin, fairly low temperature, but here we have indications that, in fact, the system is frustrated. Now, our grand plan sort of failed because these systems that are in between are only known crystallographically. The physical properties of these materials are not yet known. So this is something we're exploring in the future. Besides the 153, we're also very successful in finding the 142 material. So the 142 system is in principle visually looks very similar. You also have thin metallic looking needles that are on the order of 1 millimeter, but as I will show you shortly, the physical and chemical properties are drastically different from the 153. So this is a close-up of the needle. These little droplets on the surface is actually bismuth flux, because these crystals are grown from bismuth flux. It doesn't really affect the physical properties. We could remove them, but it doesn't really make much difference. So immediately when you look at the crystal structure, you see that it has a very distinct 1D nature. Here we have the uranium chains in gray, sort of going along the C-axis. And then we have these networks that also are quasi-1D going in the C-axis. Again, the structure is quite different from the 153. So then when thinking about physical properties, the first taste of physical properties is when we make the material and we try to, mount it to be measured. And this is where Nazar came to me and said, look, the crystals are moving. And I'm a low temperature physicist, so for me to see things moving in air at room temperature was a very, very surprising. And in fact, yes, so these are our crystals. They're placed in the Petri dish. Below we have a magnet, and if you place it next to the magnet, the crystals start moving along. What does that mean? Well, in fact, it means that it orders around room temperature. We have the magnetic susceptibility as a function of temperature that clearly shows the sharp transition around 300 Kelvin. You will also see that the material is highly anisotropic, so we measured perpendicular to the needle and parallel to the needle, and it gives us a different size of magnetic moment. The ordering temperature, the device temperature is very close to the ordering temperature, so here again we do not expect any frustration. So trying to understand magnetism better, we took a cluster of these crystals, we polished it, and we gave it to our colleagues at IFW, where they did magnetic domain imaging. And as the temperature is going up, you will see that these domains start to basically fade. This is again uniaxial magnet, so that's why the zebra-shaped patterns are looking the way they are. This over here, it is not skyrmions. I'm sorry to disappoint you, neither is this. It has to do with the fact that now, instead of looking parallel to the needle, we're looking perpendicular to the needle. And at about 300 Kelvin, all of the domains are switched off, so we're now in paramagnetic state. Now, in principle, we want to know, is uranium magnetic? Is it actually playing any role? And for this, we took our crystals to ESRF, where the XANES and XMCD pattern clearly indicates this peak, showing us that uranium is in fact magnetic in this system. Okay, but in principle, we have iron, right? And you can always say, look, you have room temperature magnetism. Maybe uranium doesn't matter. Maybe anything in this structure and any similar material would also be magnetic at room temperature. Great, so let's check it. To do this, we'll take uranium out, we will keep iron, and we will swap arsenic for silicon. So this material was actually coincidentally investigated also in our institute. What they found, it is not only frustrated, but it also orders antiferromagnetically only at 6 Kelvin. So very, very low temperature, right? Now you can say, okay, you maybe need a rare earth or something like this to make the magnetism occur at room temperature again. Fine. So this is what we look at here. We have various isostructural systems with rare earth, iron, or nickel, plus germanium, phosphorus, arsenic. And you can see that none of them have ordering temperature even above 150 Kelvin, while our system here is, again, 300 Kelvin. Now, you could argue maybe it has something to do with arsenic, right? Combination of iron and arsenic. But if you look at the uraniums, you can see that clearly as we increase the unit cell volume, we're increasing the ordering temperature. So I would say it probably has to do with the release of this frustration as we're spreading the uranium atoms apart. We're giving them a chance to actually participate in magnetism and push this ordering temperature higher and higher. Yeah, here you can see that there are some germanides, silicides, phosphides. We're still looking for other members of this material because potentially if we can swap, let's say, uranium out for gadolinium, we could envision making a very strong, very anisotropic magnet. So this is still ongoing. So what did we learn? In principle, uranium materials are super understudied. If you combine 3D and 4F or 5F, in the case of 5F, what you would have is this dual nature. And the majority of the uranium-based systems are actually just fairly vanilla and antiferromagnetic at low temperatures, but you could see high temperature magnetic order. Great. So now moving on to places where others have tried. And here we're going to look at the intrinsic structure. So we found these systems in the uranium phase space. You can say, okay, uranium is understudied. That's sort of a given. What about more common elements? Let's think about the barium, iron, arsenic. And when we discussed with Oksana looking at this, she was a little bit discouraged because the only material in this ternary is 1,4,12 scuteridide, which could only be synthesized by pressure. It is ferromagnetic below 30 Kelvin and was published in 2008. But Oksana is really, really great. So she took this challenge and actually found a new material with a very conventional synthesis. So this is liquid flux synthesis made using these custom-made crucibles, which are available online, then placed in a tantalum tube, sealed, and heated up, cooled down using this profile. The crystals, again, look quite similar to what I showed you before. They're needle-like. You have these channels of bismuth on the surface. Again, we do not think that it is affecting the physical properties. The structure of this samarium iron arsenide is what makes it special. It is 3D, and it has this ability to sort of morph in all directions. It's very flexible, and I will show you why that matters. So the first thing we did was measure magnetic properties, and here we clearly have two magnetic transitions, 1 and 2. And in principle, you can take a derivative. You can clearly see that both are very strong. You can say that upper perhaps has some sort of hysteretic behavior. And the transitions are very sharp, very, very nice and sharp. In the specific heat data, you see them both. And again, magnetic domain imaging is telling us that the system is fairly anisotropic. You can also see it on this plot where the dark and light colors indicate measurements along perpendicular and parallel to B. Now, we always look at structure, and in this case, it was sort of a chance meets preparedness, and we looked at the structure as a function of temperature. And to be fair, if you look above about 100 Kelvin, everything happens, everything behaves as you expect it to. So we have a contraction of all of the parameters, all of the lattice parameters. And yeah, it's normal, it behaves normally, but the fun things start to happen when you cool down. So these gray regions are two magnetic transitions, and you will see that shortly, or actually this is quite close to the upper transition, we have contraction, or actually expansion of the B and C lattice parameter, while the lattice parameter A is contracting. Overall, in this region, we have sort of zero thermal expansion. And then later on at the lower magnetic transition, we have the opposite effect. So the lattice parameter A is increasing, while the lattice parameters B and C compensating for it and decreasing. Now, the very impressive part is this negative thermal expansion that we see in the lattice parameters B and C. It's fairly large, even though it looks quite small here. We wanted to quantify and think about how big is this phenomenon. And what I give you here is a relative change along the B and C lattice parameter at 90 Kelvin. It is usually noted in this ppm, so we have about 5,000 to 6,000 ppms, while for terphenol D is a commercially used negative thermal expansion material. It is on the order of 2,000. Yes, it is at room temperature, but in principle, if we're looking for materials with negative thermal expansion at low temperature, this samarium system is actually quite interesting. So trying to understand the microstructure, we did EBSD patterning, and here basically you see that the two domains with different orientation are intergrown. Taking a lamella cut across the green and red, what you will get is a lamella that contains both of the twins, and then the intersection. All of this also confirmed in the single crystal X-ray diffraction. We have some twinning on the microscale. It does not actually affect the physical properties, but it's only fair that we mention it. So trying to understand the thermal expansion, we did dialitometry with our colleagues at Idaho. I'd like to point out how hard it is. So we have these needles, which are long, which is good, but they're super, super, super thin. They're on the order of, almost hair thickness. To be able to mount something and be able to measure this change in length is very, very tricky. So they did a fantastic job here. So here again, we have this change in the length as we expect. There's a bigger change associated with the upper transition, smaller change associated with the lower transition. And also what we can do is we can track this change in the length as a function of field. And you can see that at the low temperature, so in the ground state, this change is even much larger. This is the other way to look at it. So we have the thermal expansion, and in the end, what we can get is the lattice parameter B extracted from both X-ray data and dialitometry. And I hope you agree that they are, in principle, following the same path. Great. So what do we have here? We have this very complex phase diagram for the samarium system. Above 80 Kelvin, it's paramagnetic, it's vanilla, nothing is really that exciting. But as soon as you hit this first magnetic transition, something really great is happening. You go in what we think is ferromagnetic state, and consequently at around 30 Kelvin, you enter ferromagnetic state. Now, this is a representation of what we think magnetic structures are doing as you go from the lower to the upper magnetic state, but we're still trying to figure the exact magnetic configuration out. What it does is this magnetism is driving this unconventional thermoelastic behavior. In the region of 150 to 300 Kelvin, we have this conventional, usual thermal expansion that we would expect. Between 100 and 150, we have a constant or zero thermal expansion. And then we have two regions of contraction or negative thermal expansion with a small expansion here. So overall, this material is not quite application ready, but we're thinking of how we can perhaps engineer the morphology to make it even more, let's say, technologically interesting, and perhaps even push this region of constant and negative thermal expansion to higher temperatures. Great. So still, most ternaries are not known. I would like to stress that out. There are many, many materials that are left to be found. I would like to remind everybody to try and be open, to areas which were not discussed in the context of these materials before. And when we're thinking about applications, of course, we need to think a little bit more out of the box. Great. And the last part is we're going to listen to theorists. So here we're going to, again, discuss intrinsic structure and touch upon topology. So this family is an exception for me because this family has been known before we started working on it. So let me explain to you why we did it anyway. So first member of the series was the cerium compound that was described in monoclinic space group in 1972. It is very common if you have other rare earths to say, okay, cerium is monoclinic, so we will assume the rest of the rare earth are. This was done in 1977, and the material that was revisited most recently prior to start of our work was samarium, which was correctly identified to be orthorhombic in 2003. It happened so that these materials were part of the scan for a database for search of new topological states. And, theorists came to us and said, hey, could you possibly make it? We said, of course, no problem. And this is where yttrium, lanthanum, and samarium were made. So they form as platelets, nice, they are stable, perhaps a little bit small. You can ask how Sergey feels about their size if you want to. But here's where we could have in principle said, okay, here are the crystals that you wanted, take them to ARPIS, take them to STM, and we move on. But we have excellent crystallographers that we work with. So they said, look, let us try and think and understand the structure a little bit better. And what you have to realize—
3 minutes notice, sorry, 3 minutes,
Yeah.
5 was...
Okay. That was not there. Okay, good. Sure, I'm almost done. So the black pattern here is the lab, your in-house X-ray data that does not, the big peaks, yeah, that you would see in your at-home equipment measurements. But the red peaks are the ones that actually show that there's distortion, very small, so you can really only see it in synchrotron. And the difference in the lattice is actually also very small. So if you follow this blue arsenic chains, you see that here they're more like square-like, and here they're a little bit more trapezoid-like. And this small difference can only be resolved in synchrotron, which was done here. Yeah, so in principle, when we went back and gave the, let's say, new and improved CIF files to the theorists, they said, okay, great, the surface states are still there. There's a zoo of exciting states that are present in this material. And for me, what was interesting is actually the samarium analog is heavy. So this is the Sommerfeld coefficient that tells you that the effective electron mass is enhanced compared to what you would expect for a normal metal. Of course, we then went ahead and made other members of the series, including cerium, that actually is not heavy. So for me, that is quite unexpected and interesting. So yeah, so here in principle, we love database mining. I think it's an excellent tool. One has to be a little bit careful and, talk both ways, kind of. Great, so this is a brief summary for today. I showed you 3 new arsenides that basically come from very different parts of material space. One is a room temperature, one antiferromagnet. Samarium is a new magnetostrictive material, and the rare earth arsenic sulfur is a new topological family. I would like to thank all of the people that give us money, especially DAAD, because without DAAD, Oksana would not have been able to come visit us so many times. And with that, I leave you with this, because in principle, I did not talk about all of the materials, just some. If you're interested in something else, please do reach out and we can chat more about that. Thank you.
Thank you very much. We have time for questions. I can start with one. Eteri, you showed this nice new magnetostrictive material with atoms, which reminded me one of the highest temperature pnictide superconductor. I understand that this one is completely different, right? But do you have your own opinion of how close the superconductivity could be to the structures you investigate?
Short answer is no. So in principle, there's really no way to say, right? Because in many cases, people just did, for example, pressure, and they unexpectedly saw, okay, there's this huge suppression of the ordering, right? And then superconductivity emerges. So in some cases, you can sort of predict and try to see how the structure is changing if the TC could be suppressed easily. In the uranium analog, for example, we did pressure, and the pressure actually is pushing the TC up. So for all of them, we try to think when pressure makes sense or when doping makes sense. But I think this is such a large parameter space that I don't necessarily know how to exactly say this material should be pressurized to this temperature, to this pressure to give us a superconductor.
Okay, thank you very much. More questions, please? Sasha, please.
Yeah, just wanted to ask about your illustration of uranium compound. It looked like levitating, but it is not diamagnet, it is ferromagnet. What was this illustration about? How we should understand it?
It's not levitating. No. This is not what I meant to show. I meant to show that they're moving. So they're magnetic at room temperature, right? And if you take, let's say, the other uranium compound that is paramagnetic at room temperature, they would not move. They were moving. That's it. They were not, the levitation was not part of it.
Good. Other questions? If not, let's thank Eteri again.
Thank you.
And we'll switch to the next talk. The talk will be given by Andrii Terekhov with the title of Possible Signatures of Triplet Superconductivity in Rare Earth Borides. Andrii, we see your screen.
Okay.
Looks
And
good. You can start.
do you hear me? Do you hear me?
We hear you and we see your slides.
Okay. Maybe I start my report. First of all, I would like to thank the organizer for inviting me to participate in this workshop. In my talk, I will present the result obtained by our research group on the investigation of unconventional superconductivity in dysprosium-based rare earth rhodium borides. In recent years, our research has been partially supported by USA National Science Foundation through the IM Paris EU program. And this work also is conducted in collaboration with colleagues from different research international centers. And we also plan to further expand these research activities within the recently established non-governmental organization Kharkiv Quantum Center, which is developing successfully with support of Professor Sergey Frolov and other international colleagues. Over the last few years, our research group has been actively exploring unconventional superconductivity in a wide range of material system. A major focus of our work has been on magnetic superconductors, This interest stems from the fundamental challenge of understanding the coexistence of magnetism and superconductivity. As you know, two phenomena that are generally regarded as competing orders, as well as from the ongoing search for bulk triplet superconductors. Before discussing unconventional superconductivity, let us first consider magnetic superconductors exhibit the conventional singlet pairing mechanism. The coexistence of antiferromagnetism and superconductivity is most common. In this case, the moments of the two magnetic sublattices are compensated so that the total magnetization is zero or close to it, and the effect of magnetism on superconductivity is weak. In such materials, antiferromagnetic ordering occur below the transition to the superconducting state. In this case, superconductivity can be partially suppressed, and the two types of ordering can coexist. And good questions, what would happen in the case of ferromagnetic ordering in conventional superconductors? In this case, the superconductivity is destroyed or strongly suppressed during the transition to the ferromagnetic state. For example, in the compound erbium rhodium boride, there is a transition to superconducting state at 8.7 Kelvin, and then ferromagnetism appears at 0.9 Kelvin, suppressing the superconductivity. However, in a narrow temperature range before the transition to the ferromagnetic state, superconductivity and magnetism can coexist in this compound in the form of an unhomogeneous magnetic structure with sinusoidal modulation of the magnetization. Okay, next. All of the above applies to singlet superconductors where the electron in Cooper pair have opposite spin orientations. In triplet superconductors, as you know, the electrons in Cooper pairs have the same spin orientations, and in addition, in such superconductors, electron in the Cooper pair are coupled through spin fluctuations, raises, and phonons as in conventional ones. As the temperature decreases, such superconductors often may exhibit the establishment of ferromagnetic order, and then the appearance of superconductivity coexisting with ferromagnetic state over a wide temperature range. Example of such materials are the heavy fermion compounds, and at present, next slide. At present, the most common approach to realize a triplet superconductivity state is through the use of hybrid superconductor ferromagnetic structures. However, the formation of triplet correlations in such system requires several stringent conditions to be satisfied, including next the presence of ultra-clean interfaces, precise control of the thickness of individual layers, careful engineering of magnetic inhomogeneity, control of the transparency of interfacial boundaries. In contrast, bulk materials are free from these constraints since the triplet superconducting state, if present, is realized intrinsically within the crystal. And if a bulk spin triplet superconductor is discovered, it could enable superconducting spintronics without the need for complex multilayer heterostructures. sources of spin polarized supercurrents, quantum devices with enhanced robustness against magnetic fields, topological qubits without the need to efficiently generate triplet correlations at interface. For this reason, the search for new bulk spin triplet superconductors remains one of the most important and actively pursued directions in superconductivity research, despite the remarkable progress shift with hybrid superconductor ferromagnetic structures. Rare earth rhodium borides with the tetragonal body-centered crystal structure of the lutetium-ruthenium 4 type are convenient for elucidating the aspect of superconductivity and long-range magnetic ordering coexistence. As the temperature decrease, the transition to the magnetically ordered state is established in these materials due to regular sublattice of magnetic dysprosium ions, which interact with each other through conductions electrons, Y exchange interaction. And then the transition to the superconducting sand is observed, which may coexist with magnetic ordering down to the lowest temperature available in the experiment. I will now turn to our studies of unconventional superconductivity in polycrystalline rhodium borides with dysprosium samples prepared by argon arc melting under high pressure conditions of about 8 gigapascal. Subsequent studies showed that polycrystals with this type of structure can also be synthesized without high pressure through partial substitution of rhodium by ruthenium. It has been shown that replacing rhodium with ruthenium in such compounds can alter the nature of magnetic interaction with the dysprosium subsystem through modifications of the electronic structure and associated Y exchange interaction. Okay, next slide. This slide presents the temperature dependence of the magnetization for this compound, for one of this compound, the M of T curve measured under zero field cooling conditions. And shows really clearly reveals a magnetic compensation point where the magnetization of two oppositely aligned magnetic sublattices become equal in magnitude and leading to vanishing net magnetic moment. Such behavior is often regarded as evidence of ferromagnetic ordering. Below T compensation, the magnetization M of T becomes negative in this region. However, this is not associated with the emergence of diamagnetic response. Rather, it reflects the fact that the magnetic moments oriented downward the weak sublattice become larger in magnitude than those oriented upward the strong sublattice. Upon further cooling below TC onset, 5.5 Kelvin, genuine diamagnetic response appears as a result of the onset of superconductivity. Okay, the next slide presents the temperature dependence of the low temperature specific Herd of compounds with dysprosium. Two distinct features are clearly observed. The first feature is anomaly appears at TC onset, which may be associated with superconducting transition. But the second anomaly is observed at approximately 2.7 Kelvin. It's considerably more pronounced and exhibit a sharp peak, suggesting the presence of additional magnetic phase transition. One possible interpretation is a transition from ferromagnetic to antiferromagnetic state.
4 minutes notice. Andrei, 4 minutes left. Thanks.
Only 4 minutes.
Yes, I see you have 20 minutes talk. So
Okay.
17 plus 3 minutes for questions.
Okay. I quickly. The next slide presents the temperature dependence of the low temperature of the. The next slide shows point contact spectra measured at different temperatures on the same contact in zero magnetic field. The obtained ratio to delta zero over KBTC is approximately 4, exceeds the value of 3.52 predicted by BCS theory for weak coupling singlet superconductors. The figure on the right presents the temperature dependence of the superconducting order parameter. Of particular interest is a small minimum observed at approximately 2.7 Kelvin, which may be associated with the onset of antiferromagnetic ordering. At the same time, no significant suppression of the superconducting order parameter delta is observed within the temperature range where superconductivity and ferromagnetism coexist. Collectively, these findings may be considered as evidence for a possible spin triplet pairing state, which is generally expected to be more robust against magnetism than conventional singlet superconductivity. Next slide presents a point contact spectra measured at 1.6 Kelvin. In different magnetic fields, the spectra, as you see, were fitted within the framework on Blondin-Dingham classic theory, allowing us to determine the values of superconducting order parameters, delta. Similar analysis were performed for spectra measured at other temperatures, yielding the corresponding values, and the right panel shows the magnetic field dependence of the superconducting gap at different temperatures. The highest temperature, 3.4 Kelvin, is above the antiferromagnetic transition temperature, and the field dependence exhibit no noticeable anomalies. In contrast, at 1.6 Kelvin, the field dependence is clearly non-monotonic and displays a pronounced minimum followed by the maximum. It is proposed that in magnetic fields exceeding approximately 2 kilooerstat, the system undergoes transition from antiferromagnetic state to ferromagnetic state, possessing a non-compensation internal magnetic moment. with a further increase in the external magnetic field, the dominant effect becomes the suppression of superconductivity. And at 2.4 Kelvin, an anomaly is still observed in the field dependence of the order parameter. Also, it's considerably less pronounced. Okay, maybe next interesting results is that during magnetization measurements of series of rare earth rhodium borides, an unusual positive magnetic response was observed below the superconducting transition. In field under field cooling conditions. It was instead of the conventional diamagnetic signal associated with Meissner effect. This positive magnetization, such behavior had previously been reported in high temperature superconductors and was later observed in variety of other superconducting systems. This phenomenon became known as the Oleban effects or paramagnetic effect, paramagnetic Meissner effect. Okay, maybe.
If you wish to leave a time for question, then you should conclude shortly.
Okay. Summary: coexistence of superconductivity and non-collinear magnetism over a wide temperature range, non-monotonic behavior of delta of T and delta of H dependencies, strong dependence of upper field of T and R of T on the slope of external magnetic field, and the Oleban effect, paramagnetic Meissner effect, were discovered in different rare earth compounds with rhodium Bohr compounds with dysprosium. All these results did not fit well into the framework of Bardeen-Cooper-Schrieffer theory for conventional superconductors and could be one piece of evidence for the presence of unconventional mechanism of superconductivity pairing in these superconductors. Thank you so much. Unfortunately, I don't
Thank you very much.
much time. Don't have much time to present all of my results, but okay. Please.
Thank you.
Question.
Let's see whether we have questions. We have time for questions. I have one to start. So these are beautiful materials. Do the single crystals exist, and what is known about the electronic structure?
Okay, we have a big problem that connected with that we don't have, unfortunately, we don't have single crystals of these compounds because it's very complex. We try to do single crystals Chirality method, but it's not good. And now, yes, we need to prepare single crystals, these compounds. In the literature, presents information about electron structure, similar compounds, but we don't conduct such experiments. It's a very good, it will be a very good experience on monocrystal, on single crystals with ARPES, I think.
Okay, thank you. More questions, please? If not, let's thank the speaker again. We move on to the last talk in this session. The talk will be given by Eduard Gobar, and the title is Impact of Impurities on the Density of States and Thermodynamic Properties of Pseudo-Spin 1 Fermions. Eduard, please. The floor is yours.
Sorry, but there was a change in schedule, so Pavlo Sukhachov is going to give a talk, and I will give a talk in afternoon.
Okay, accepted. So the next talk will be given by Pavlo Sukhachov, and he will speak about odd-parity orbital magnetism. Pavlo, please start.
Yes, hello. Thank you for the invitation to this workshop. And yes, there is a change in the program. It was actually updated yesterday, but yeah. So today I would like to talk about our recent research done in University of Missouri on p-wave orbital magnetism. So it's a little bit different topic compared to the spin triplet superconductivity that you were enjoying so far. There were several excellent talks on unconventional magnets, so I will be very brief in my introduction. Well, perhaps the most well-known class of magnets are ferromagnets. They have non-zero net magnetization, break time reversal symmetry, they're common, widespread, and actively used in modern technology. Another class is antiferromagnets. These materials also break time reversal symmetry, but they have preserved parity time reversal symmetry, which leads to the degenerate energy spectrum. So we don't have net magnetization, and spin up and spin down bands remain degenerate, as you can see from this cartoon. And well, as was emphasized by speakers before, it was long believed that antiferromagnets are sort of useless, which is clearly not the case now. So what are unconventional magnets, namely altermagnets? Well, there were excellent introductions before, so I will just flash through this slide. The idea is to consider a similar lattice as we have for antiferromagnets, but introduce the asymmetry in spin up and spin down atomic orbitals. This can be done, for example, by inserting an additional atom and creating the so-called Lieb lattice, as was described in, let me see, yes, in this work. The key idea is that the symmetry of altermagnets is not inversion or translation, and we can use spin groups. Of course, if we ignore spin-orbit coupling. In this case, spin groups correspond to separate rotations of lattice and spins. And then in this lattice, one can show that one can realize the so-called G-wave altermagnet. Its energy spectrum shown here, where red and blue correspond to spin up and spin down spin polarized bands. So it's even parity magnet, because if we flip K to minus K, K to minus K, we don't need to flip spin. There are several material candidates, both in D-wave channel and higher channels, and there were excellent talks, and there were several materials, excellent papers. Now this field is quite rich now. But in this talk, I will focus on a slightly broader class of unconventional magnets. In particular, I will define a conventional magnet as a magnet that has a non-zero net magnetization, but has a momentum-dependent spin polarization of bands, momentum-dependent magnetization. This is a little bit broader definition than for altermagnets, and it includes an additional class, which I show in the next slide. So what are the magnets that we know so far? We know conventional magnets, ferromagnets, antiferromagnets, unconventional altermagnet, and there is an additional class that haven't received so far coverage at this workshop, so-called odd-parity magnets. They share several properties with altermagnets. In particular, they can show strong spin response. They have no net magnetization. The response is in the terahertz range, which is believed to be very beneficial for spintronic applications. It's actually one of the reasons why antiferromagnets were considered to be as one of the breakthroughs in spintronics. Well, so far that haven't happened, but maybe unconventional magnets is a key to success. As altermagnets, odd-parity magnets are under active investigation, yet experimental studies are much less frequent compared to those in altermagnets. So still some work should be done. Compared to conventional ferromagnets, which operate in gigahertz range and have net magnetization, these classes show promises not only for fast, let's say, magnetic, antiferromagnetic, altermagnetic access memory, but also open new ways for miniaturization, because no net magnetization, since we can create smaller devices. All right, so what makes these odd-parity magnets different from altermagnets? What is the benefit, essentially? Well, the benefit is in the name, and the difference is in the name. So they are odd-parity. When we're talking about altermagnets, we're talking about materials whose energy spectrum is even. So K to minus K, spin remains the same. We break time reversal, but we preserve inversion symmetry. Well, then the natural question, can we have a material that that preserves time reversal symmetry, at least in some form, but breaks inversion? In this case, the energy spectrum of our material should be odd, which means that if we flip K to minus K, we need to flip spin. One of the simplest models to create such odd parity, or P-wave, well, in 1D, everything that is odd parity is P-wave, right? Is this chain with this rotating spin polarization, cyclical spin polarization. This chain is particularly interesting because it's, first of all, not antiferromagnet. Because for antiferromagnet, you will need to have spin up and spin down to be neighbors. But it has so-called tau-T symmetry, which is a combination of time reversal and translation. Because if we apply time reversal or essentially a spin flip, we can just translate, and then this lattice will coincide with itself. So in essence, this lattice is just two intercalated antiferromagnets. The spectrum of this chain can be easily calculated, and it looks as follows. So in this cartoon, one can see that there are bands with spin up polarized here, red, and these bands have polarization with spin down, blue. Well, this is odd parity, right? K to minus K, spin to minus spin. One can generalize this model to 2 dimensions. The immediate issue with this model is that if we try to generalize it to 2 dimensions, we will need to include more atoms in the unit cell. Even here, we do have 4 atoms per unit cell, 4 atoms, and then spin up, spin down, which means that we will have 8 bands. This is a pretty hostile model for pen and paper theoreticians. Therefore, in our work with my Norwegian colleagues, we decided to introduce an effective model for P-wave magnets. The idea is as follows. So we consider this one-dimensional chain. We gather spins here in so-called blocks or sectors. And we can consider only the hopping between the same sectors here. This sectoral degree of freedom allows us to reduce the number of degrees of freedom by factor of 2, which is not bad, right? So we went from 8 by 8 to 4 by 4. Then the generalization to 2 dimensions is as follows. We can just add another chain, well, particularly ferromagnetic coupling, just to avoid expanding the unit cell. And the effective model will have a particularly simple form. So it's essentially just a kinetic term, which is a combination of these cosine terms here, and this is a hopping term here. Sigma is a Pauli matrix in the spin space, and tau is a Pauli matrix in the so-called sectoral space. This model will also have this so-called spin splitting parameter, as we call it. Yeah, this alpha, which is different for different spins, and this GSD coupling, which is operates on the level of different sectors. That's why it has tau Z here. This model can be further simplified because it's an energy spectrum, as you can see here. It's relatively simple. It's just essentially 2 parabolas colored with spin. And we can expand this model nearby the gamma point and obtain the following effective Hamiltonian, which is really simple. It's actually just a k squared divided by 2m model. Then there is a spin splitting term, alpha k. And then there is this GSD term which separates these two bands and prevents them from essentially canceling each other. And as you can see, that the spin polarization of this model is indeed p-wave. It's one contour, one half of it is spin up, and the other half is spin down. And I would like to emphasize that this term is something that differs this low energy model from other models that were proposed in the literature, which include only this term, which is essentially just effective spin orbit coupling. Well, not a rush, but just effective. And this model, where one ignores this decoupling term, actually has higher symmetries than it should, and it leads to several vanishing responses. So what are the key properties of p-wave magnets? What makes them different from these altermagnets and other materials like ferromagnets? One of the immediate properties that we looked at was tunneling magnetic resistance. So if you consider junction of two p-wave magnets where the spin splitting vector has a different orientation, one can see that tunneling magnetic resistance, which is essentially magnetic resistance between the magnet with, let's say, spin up and then flipped magnetization to spin down. One can see that this tunneling magnetic resistance has a pi over 2 periodicity. So essentially at the angle between the spin polarization on the left and the right hand sides of the junctions equal to pi over 2, we have a vanishing TMR. This is different from, let's say, D-wave altermagnets, where this angle is pi over 4. So this is one of simple measures of symmetry of your magnetism. Of course, since we have this elongated Fermi surface, we will have anisotropic magnetic resistance. It's really trivial to understand. In this case, for example, if we spin split along x direction, our parabola, our spectrum is parabola, it's wider in x direction and narrower in y direction. Hence, we expect velocity to be larger in y direction. Hence, conductivity is larger in y direction. This is indeed what we see at this calculation that we did in our work. Yet, I would like to emphasize that this anisotropy has a little to do with p-wave spin polarization. Hence, I think there was an experimental result that used this to confirm p-wave magnetism. I would like to disagree with that, but at least this is one of signatures. What else? Superconductivity. Of course, the non-trivial spin polarization in these magnets allows for essentially spin singlet-like pairing. Indeed, if we couple electron with its time reverse partner, we couple spin down, K, minus K, spin up. Well, it's perfectly compatible with such type of pairing. In fact, if one takes a look deeper into the pairing amplitude for such superconductivity, one realizes that this is so-called easing superconductivity, which is a combination of singlet and triplet correlations, essentially just 50% singlet, 50% triplet. Edelstein effect. This, I think, one of the most direct transport measurements of p-wave polarization. So what is the core idea of Edelstein effect? You apply electric field and you generate spin polarization in your material. Indeed, if you have a p-wave magnet, by applying electric field, you introduce this non-equilibrium accumulation, non-equilibrium distribution. Hence, you just have more spin-ups than spin-downs because just you shift this distribution. Just a simple Boltzmann type of calculation. All right, what are the key material candidates and potential platforms for odd-parity magnets? Perhaps the first material candidate that was proposed to be a p-wave magnet is this cerium nickel arsenic oxide compound. It has non-trivial spin texture. It's one can see it's non-collinear here. And this is a DFT result obtained by the group of Libor, Smejkal, Hyrasinova, and Tomasz Ingres, and Anna Hedens. Of course, did a whole job. But if you're just interested in odd-parity magnetism, one can look at helimagnets, which are more numerous than p-wave magnets, and in particular, this recent material, nickel iodide 2, which was actually claimed to be a p-wave magnet. Yes, here is the numerical data for it. Yet difference between p-wave magnet and helimagnet is in its stability with respect to spin-orbit coupling. And this material is perhaps not stable with respect to spin-orbit coupling, but fortunately, I was told that the spin-orbit coupling is quite weak there, so it can be considered to be a p-wave magnet. And here one can see that DFT result indeed show this p-wave type spin splitting here. So p-wave magnets, as they exist, they could be interesting. Yet current realizations of p-wave magnets, they almost exclusively rely on one particular detail of your material. You need to have a non-collinear spin texture. So you need to have this helical spin texture arrangement in your material. This type of spin texture has several drawbacks. In particular, usually it requires a larger unit cell. It's hard to simulate. Okay, this is a minute disadvantage for us, right? It always says that it can just take longer to calculate. Furthermore, large unit cell means that these p-wave magnets should be susceptible to imperfections, to temperature. Such non-collinear spin textures are harder to control, yet this is under active investigation, so ways to design and control may appear. Multiple domain will reduce p-wave signal, same as with altermagnets. So natural question is, do we really need to have a non-collinear spin texture? Are there other platforms for odd-parity magnetism? Perhaps almost a year ago, there was a preprint, an archive that asked a similar question. So can we realize odd-parity altermagnets, what they call them altermagnets, that is odd-parity spin splitting in collinear magnetic system? And the idea of that work was to consider a Haldane-Hubbard model with repulsive interaction. Here is a lattice with interactions shown here. Here's a model for condensates, just regular hopping, hopping with a phase, interaction. And in this model, you realize by interaction this type of spin phase. So you accumulate spin at particular sites. And it was shown that this model can in fact realize F-wave odd-parity magnet. Here is a distribution of spin polarization here. So you see that it has this characteristic shape. It's odd, but it's not p-wave. Next step was made several months later, almost a year. People decided to realize something simpler. They looked at unconventional altermagnetism without spin texture. A similar idea. So you have a model, you have complex hoppings here, but here the statement was made that, well, one can realize a material with loop currents running in a particular D-wave manner. And, well, you realize a so-called orbital altermagnet. A material was proposed, this is molybdenum oxide. Our idea was quite straightforward. So since a more complicated texture were realized, can we realize a simpler texture? For that, we considered with my postdoc the following lattice. It's a ladder type lattice. So this is one-dimensional lattice, and then we just stack them ferromagnetically. This lattice has two fluxes. Let's say flux up and let's say flux down here. Energy spectrum of this lattice is pretty rich. It has 4 bands. It realizes Dirac nodes, and the position and topology of this band structure strongly depends on the flux that you run through these triangles. Here, for example, I'm fixing flux 0.45 pi, but if I tune it to 0 or pi over half, I will close the gap here and I will have a Dirac nodes. This model, so why is this model? This model has a particular structure. It has a tau T symmetry. Indeed, if we just shift and flip apply time reverse symmetry, we flip the flux. So we shift, flip the flux, and this is a symmetry. So that was a key idea to realize a model that is similar to this minimal model for regular spinful p-wave materials. Since we have this tau T symmetry, have this loop current order, we expect that we could realize the p-wave magnetization. But this is not the magnetization that comes from spin sector. This is orbital magnetization. So there are no spins on sides. So this is not an antiferromagnet. If I remove flux, it's non-magnetic material at all. Indeed, by using standard formulas, we can calculate the distribution of orbital magnetization for different fluxes. Here we just took 0.2 pi, and here we at a gapless regime at 0.5. One can clearly see that the orbital magnetization has a odd structure. It's a p-wave structure. Ky to minus ky, we flip m to minus m. So these are contributions from different bands. Indeed, we have 4 bands, and these are higher bands, and these are lower bands nearby 0. And we can see that for smaller fluxes, everything comes exclusively from bands nearby 0. And in the case of a gapless model, there are these non-trivial sign changes, but still magnetization remains odd. All right.
Although 5 minutes. 5 minutes.
Yes, I will finish in time. Don't worry. So I emphasized several times this tau T symmetry, and that is important. And so what will happen if I break it? So I can break it by hand. I'm theoretician. I have lattice. I can just take the hopping between these D sides here and change it to be 0.5 of other hoppings, while keeping all other hoppings to be equivalent. What will happen in this case? As you can see from this figure, while I'm having tau T symmetry, I have a perfect odd-parity spectrum. In the system with a broken tau T symmetry, it becomes non-symmetric. So I generate even parity magnetization here. So the presence of tau T symmetry is crucial to protect this odd-parity, ideal odd-parity splitting, in the same way as is the case for regular spinful p-wave magnets. One can also calculate transport responses for this model. Hall effect is 0 in this model. If we have tau T symmetry, only the valley Hall is non-trivial, as you can see here. Hall response can be actually generated when you break this tau T symmetry, as you can see here. It's generated nearby the gap when you break tau x. So this could be a signature of the broken symmetry. But since we have orbital magnetization and everything is hinged on orbital degrees of freedom, a natural response is orbital Hall effect, which is given by this more complicated expression. And here is a calculation. So the key point is that it has this non-trivial peaks nearby gap closing fluxes. So at 0, pi, and 0.5, we close the gap, and we do have these peaks nearby. If we break tau x symmetry here, we see that this peak here nearby 0.5, it splits in 2. Hence, this could be also considered to be a signature of this broken tau x T symmetry and transition from ideal p-wave case to p-wave plus even parity. All right. So perhaps the most important question, and the question that I hear almost all the time when I'm talking about this work is, well, how do you realize this loop current order that is needed to have this orbital p-wave magnet? The most direct way is to have interaction-driven instabilities, somewhat similar to works considered by Valentin Lieb and Johannes Knolle, and also this work. So the idea is to have interactions, and then in principle they can generate these loop currents. But I would like to emphasize that this is different from what we propose, because here you need to have antiferromagnetic lattice to begin with. One can also generate loop currents by light. This a little bit goes into the territory of Floquet-driven systems. Just a few weeks after we posted on archives, there was a work proposing to use a 2-color Floquet driving to generate such type of loop currents. Yet, as far as I remember, no explicit calculations were done. And also, we can go further and propose to use synthetic systems, in particular ultra-cold atoms, flux ladders, somewhat similar to what was done almost a decade ago. It might be not so easy to realize this checkerboard type of flux lattice, but perhaps it could be possible. So since my time is running out, let me summarize the key points of this talk and provide an outlook. So I showed that p-wave magnetism can be generated by a loop current order without non-trivial, non-collinear spin texture. This odd-parity magnetization is enforced and protected by tau-T symmetry. Orbital and Wally Hall effects are sensitive to the breakdowns of the symmetry. And we believe that since this orbital odd-parity magnetism doesn't require this long period helical texture, it could be more robust and controllable. Particularly, we can create artificial systems that could realize this p-wave magnetism. Future research direction is to investigate whether there are any peculiarities of interaction effects in the system, dynamical responses, quantum geometry, and particularly it would be interesting to have a material realization of such odd-parity magnetism. Then, for example, by using this magneto-optical methods, one can directly probe the spin polarization of bands. Okay, before concluding, I would like to acknowledge my collaborators, in particular my revision collaborators, Jakob, Arne, Bjornov, and Hans, with whom we started this field of p-wave magnetism, and of course my postdoc Jan Taoli, with whom we worked on this orbital magnetization, who actually did all dirty job. And short advertisement, those who are interested in, still interested in going to United States, we have a PhD program at University of Missouri. We work on theoretical condensed matter physics, experimental condensed matter physics, biophysics, and astrophysics, and good students are always welcome. If you're interested, just contact me. We can talk. And with this, I would like to leave at this slide, and would be happy to address any questions. Thank you.
Thank you very much. Questions, please, Jeroen.
Thank you, Pavlo. Very, very nice talk. The first question would be, you can also make a D-wave out of this, or are you restricted to odd parity?
Of course, you can make a D-wave, but that was done. Short answer.
Okay. So the next question, you did not consider an Edelstein effect in this P-wave, right? Or you could have an orbital Edelstein effect here as well.
Yes, this would be direct calculation. It's essentially a regular spin Edelstein effect was calculated by a group of higher Libor Tomasz linguists, as far as I remember.
Because one issue could be that these are always insulating, or you have a gapped P wave in this case, right?
Okay. In my case, my model has a gap, but I can tune Fermi level. So you see that at certain fluxes, yes, you have a gap, but if your chemical potential is higher here, in particular, this is what I was showing here. My chemical potential here was, I think it was -1. It was here.
Right. But
so you can be in metallic regime.
Right, but likely this kind of states will be stabilized by the gap that's opened by some other instability.
Right. Well, yeah, this could be possible, but I guess I need to have the realization of the state in realistic material to talk about whether chemical potential is in the gap or not.
Yeah.
Yeah.
Thank you.
Jan was the first.
Okay. Thank you. Very nice talk. I have a comment since you come up with these rather complicated models. We have a paper 10 years ago where we found a p-wave spin texture in just a 2-orbital Hubbard model on a square lattice. It's a kind of similar state to yours. We have these like spin currents that are essentially flowing on side between the two orbitals. And basically by modeling the hopping on the square lattice, we can tune p-wave, d-wave spin textures.
Yeah, this I'm not sure that I can recall the paper, and I would be happy if you could share the link.
Sure.
Looks interesting.
Aslan?
Yeah. Hi, Pavlo. Nice talk.
Hi, Asle.
I just wonder, you mentioned that one way of stabilizing these loop currents is by, for instance, interactions, I guess, some off-site Hubbard type interactions or something. Typically, you would compete against other instabilities. Did you consider that? Or did you just go with this?
No, we haven't considered, actually, we haven't considered interactions in our model. We just postulated these complex hoppings and loop currents. Attempts, actually, the works done by these people who used different lattices. I think in this work, they just considered a repulsive Hubbard and no other competing instabilities. This work is more detailed, but it was different in terms that they had actual antiferromagnetic texture. I think this is in part because they wanted to stabilize these loop currents. Yes, so in our work, we don't have direct calculations of interaction-driven instabilities that lead to loop currents. It would be interesting to investigate them, actually.
Thank you.
Yeah, so I have a comment of a comment. On two orbital ladder, you can already stabilize these fluxes. I mean, you don't have to go to 2D. On the ladder, you can already stabilize this. Yeah, just by interaction. Yeah.
Yeah, sure. The point to go to 2D was, yeah, we don't really need to have 2D to have odd-parity magnets. That's 100%. So the idea here was to see that if you go beyond 1D, you can have other types of textures like F-wave, etc. And we wanted to have the minimal one, the P-wave. And if you have 1D, then yeah, sure, just have odd-parity and that's it. If you have 2D, then you have these contours that can be P-wave or other type. This is what we want. But I agree that you don't really need to go to 2D to have odd-parity. This I agree.
I allow myself as a chairman a naive experimentalist question. One of the possible theories of high-temperature superconductivity is based on antiferromagnetic spin fluctuations. With this era of new types of magnetism, do I have to expect new exotic mechanism of superconductivity?
Yes, and I think there were similar works already considering superconductivity in altermagnets and P-wave magnets driven by phonons and magnons. I think this question is actually better asked to Asle, who is an expert in superconducting instabilities in such unconventional magnets. But my humble opinion, yes, one could expect different types of mechanisms in unconventional magnets too.
Well, I think potentially the answer is yes, and not only that, but you can actually get very interesting quantum critical fluctuations from such loop configurations in the Q plates.
Thank you very much. I do not see any more questions, so let's thank all the speakers and Pavlo again.
Yes, thank you.
And I think that this session can be closed. We have a coffee break and we reconvene in 11:15, in 20 minutes. Thank you.
Hi, everybody. It's time for the next session. Please take your seats. So, the first talk on this session will be given by Andrii Sotnikov from the Ahiezer Institute for Theoretical Physics of the Kharkiv Physical and Technical Institute. So please, you have 20 minutes, and please leave some time for questions.
Thank you very much for introducing. Shall I open by myself? Okay, thank you very much for giving me opportunity to present my results here in this wonderful atmosphere. Actually, rather relaxing for me. I'm from Kharkiv, and I feel myself like on vacation here. Only one air raid alert, as far as I remember, and hope there will be only this single one. Okay. So my research was performed in collaboration with Denis Bonder from Tulane University, New Orleans, and my student Alexander Popovichan, who performed this analysis while being in ETH Zurich. And I'm pleased to say that it was a research in the framework of IMPRESS-U project together with two speakers of the previous session, Sergey Frolov and Andrii Terekhov, with their contributions, and also partly supported by National Research Foundation of Ukraine. Let me go to the topic of this talk, enhancement of photoinduced superconducting pairing via quantum Lyapunov control. And I would like to give credit to wonderful experiments by Andrea Cavalieri's group around 10 years ago. They published papers on optically enhanced coherent transport in superconductors, cuprate superconductors, organic superconductors, which have in equilibrium critical temperatures of about 50 or 20 Kelvin, but show superconducting properties under coherent excitations up to room temperatures, with peculiarity that relaxation times are quite short, so about picoseconds. But this is maybe the single slide which is material oriented on my topic, because the focus of our group is kind of concept oriented and model oriented. So we start with a favorite toy, Hubbard model, which continues to be one of the most popular contrivances of theoretical condensed matters physics, according to Nature editorial. And the model is quite simple. If you look at the situation, you have nearest neighbor hopping, you have two flavors of fermions, like spin 1/2. You have repulsive interaction, so we will talk about a strong coupling regime when interaction U is much larger than hopping T in this model. And what is more kind of relevant for this model, that recently there are many experiments with the realization of this model in optical lattice setups with cold atoms. And there are many degrees of freedom you can realize these models, especially the focus of my talk at half filling with span balance, but also in different geometries and different configurations, including orbital degrees of freedom, as in previous talks, for example. So let me just go back, slightly back than 25 years ago or so. So the eta pairing in Hubbard model, so this kind of superconducting pairing was suggested by Young in 1989. So that among states of the Hubbard model, there are states that possess long-range superconducting order in this simple setting with hopping and interaction and simple kind of lattice geometry, no even frustration. And he introduced, by analogy to spin 1/2 operators, SU2 algebra for pairs and holes. So you just see, if you're familiar with spin operators, then you replace spin operators with eta operators, and you immediately see analogy to square of the eta operator. This is analogy to the square spin operator. So you have ladder operators, multiplication, eta plus, eta minus, and eta z square. Eta z square just controls the filling of the lattice. At half filling, you have action of eta z equals to 0. And essentially, you have the product of eta plus to eta minus, and these operators contain this staggered prefactor -1 to the power of lattice side, which means that to enhance superconducting correlations, you need doublons and holes next to each other in kind of checkerboard fashion distributed in the lattice. And what is important that in the ground state, unperturbed Hamiltonian, which is written here, just commutes with eta squared, so it preserves absolute value of eta parameter. And then we also can look at the eigenstates of this model and look where these states are hidden. So let us think, in the ground state, there is no eta paired states, of course, because you have Mermin-Wagner theorem, especially in 1D. If we talk, so we plot for one-dimensional finite size system, just exact diagonalization, and we can look at the horizontal axis. We have just distribution of eigenstates, and if you have interaction strengths equal to 20 Hoppian parameters, so you immediately see the bands between. So the doublon excitation, then 2 doublon excitations, 3 doublons, etc. And on the vertical axis, we have the absolute value of the order parameter just normalized by the lattice length. And we have then excitations, excited states already in the second band, where we have this kind of eta pairing. And now the question, please do not so pay much attention to these romps, but they actually correspond when you excite the system already. So with coherent excitations, these romps just represent the relative weights where these eta paired states are located in the spectrum. But it depends on the type of the signal, of course. So just typical signal, and then you excite eta paired states. And now the question, of course, how to induce this pairing. And then you just subject the model or the lattice to the electromagnetic field. You have the Peierls phase, exponential prefactor. And now this Hamiltonian time dependent, this Hamiltonian doesn't commute with eta squared. And now, depending on the pulse, so I just show envelopes of the pulses, so 3 different envelopes, and kind of a range of different frequencies close to resonant one. Envelopes are just determined by sine squared. And inside this envelope, we have like 50 modulations, periods of the pulse. So we can enhance order parameter significantly, but if we're slightly off resonant or we have different pulse amplitude, we can fail to induce superconducting order. So it requires kind of fine tuning. So you can end up at almost 0 eta squared if you just slightly away in frequency or in amplitude. So the question then arises, can we enhance eta pairing that we observed previously just for regular pulse with quantum control? And now it goes, and I'm kind of proud to slightly go into history and mention Alexander Lyapunov, because he worked for 17 years in Kharkiv. And there are many mathematical concepts and school after him, and we have streets in Kharkiv after him. Due to his developed stability theory, we can formulate and adapt his methodology to the quantum control, and in particular to superconducting pairing. And actually, this looks not that difficult. So we need to recall the Ehrenfest theorem for any observable. So time derivative of the observable is determined by the average of the commutator of Hamiltonian with this particular operator. And if we do the just straightforward in second quantization, just calculation of the commutator, we can just extract the time dependence into sine function, and then operator which is time independent, but contains products or 4 operators two creation and two annihilation operators. This is anti-commutator, just compact form, just written in this way. But usually, so this generative operator just contains annihilation of two particles on the single side, for example, and creation of on nearest neighbor side on the bond, and vice versa. Annihilation of two particles on the bond and creation on the particular side. And because of product, so some of all lattices, so this is independent of relative position where two particles were created and where two particles on the bond annihilated and vice versa. So, and now Lyapunov control just says that we need to keep condition that this eta squared during our time evolution always increases. So we need to fulfill the requirement that derivative is positive or non-negative. And this means that we can dynamically adjust the phi, our field, during the time evolution. So we can, with Lyapunov control, we only need a single pass. We just immediately measure feedback and put the feedback and observables into the next step. So as soon as we observe that our order parameter starts to decrease, we can then adjust our field appropriately. So how it works? So actually, we have the pulse that started. At some point, if we do have the uncontrolled evolution, so it reaches the maximum and then drops down. But with Lyapunov control, we can then further enhance superconducting correlations just by automatic protocol, as I showed just math. And this, have a large contrast when you have not adjusted in advance the frequency of the initial pulse or the amplitude. So for blue line, with uncontrolled evolution, we have almost zero, but this is modulation shown in background for blue behavior. So then the Lyapunov control switch on, and you have a proper increase of the relative value of the order parameter. And in the frequency domain, if we plot it, we see that the frequency when Lyapunov control switches on as a vertical line, then the frequency readjusts closer to the resonance. So the only thing that we need to feed our automatic protocol is just macroscopic parameters, of course. And then the system just finds the proper regime for time evolution. And this is comparison, the maximal value with uncontrolled evolution, just single pulse with a given envelope, then saturated values in the domain. These are axis amplitude of the signal on the vertical axis, on the horizontal is frequency. Around 20, we have this resonance. But if we switch on Lyapunov control, we have a large domain where we can enhance superconducting pairing. There are some stripes where it's not working well, but this depends on slight readjustments of the activation conditions for this Lyapunov control, because we need to monitor the pulse and then switch on, in particular when we cross the threshold, certain threshold for activation of this control. And as kids, when they construct something with their toys, they first construct, for example, castle, and they are wondering, what happens if they destroy it? And the same with superconducting pairing. We were wondering, and can we suppress when we initially just induced the superconducting order and it saturated without any control? Can we just shut the second pulse, but with control, in order to suppress the superconductivity? And the answer is yes, but not completely. So the best achievement for us was like 10% of the initial value. So not completely, but fairly well. We can also suppress superconducting correlations with similar signals. But the envelope of the signals just controlled automatically without any manual control.
I'm sorry, Andrei, 3 minutes.
Okay, thank you. So I am almost at the end. There are some also questions on what happens if we do not abruptly switch on the control, and it seems that this is not the problem. We can just put some special smoothing filters and it doesn't affect much the relative value of the order parameter. Or what if we switch off because we have some kind of echo after switch using Lyapunov control? Can we just smoothly switch off the field? And the answer is also yes, but this kind of following signals just slightly increase the relative value of the order parameter, but mainly since these particular calculations are at 0 temperature, as soon as we switch off the control according to the Hamiltonian structure, our order parameter remains unchanged and we see perfect picture. But this raises additional questions for the outlook. But firstly, let me say a few words about our results. So we have this quantum Lyapunov control that doesn't require intricate fine-tuning of pulse parameters from theoretical point of view, of course. Lyapunov control efficiently amplifies weakly excited states, and particularly at low frequencies. No need for precise knowledge of optimal carrier frequency before we just start to excite the system. And we can also use Lyapunov control to suppress the superconducting correlations. And further research directions just go to finite temperatures, include then calculation of charge stiffness in this analysis, because at finite temperature you have just thermally populated states with non-zero eta squared. And also go to dissipative environments closer to experimental realizations. And of course, we can do now with tensor networks larger systems and two-dimensional extensions, and hope we will succeed. And the last, but not least, so I would like to thank Denis Bondar, my collaborator, with students, and Alexander Povichan, who was the first author of the paper, and also support by organizations like US Academy of Sciences, STCU organization, then within the ImpressU project and National Research Foundation of Ukraine with particular project. And thank you for your attention.
So let's ask the speaker. We have time for small question, please.
Thank you for the talk. So can you say how the calculations were done? This is numerical finite clusters?
Yeah. This is a one-dimensional chain. So this is by now exact diagonalization routines.
Okay.
Yeah, just time evolution of the wave function, but also we can transform to density operators, language, work with phenomena.
Sure.
Yeah.
So, but then, for instance, the frequency you choose, because it's very, you have a fast oscillating phi of t, right? Does that depend on the cluster size, on the length of your system? For instance,
yeah, I understand you. Yeah, it slightly depends. So there are some finite size effects. So the larger the system, then the closer you go to explicit charge gap value, so that you assume just interaction U amplitude. Yeah, but there are some finite size effects that we observe.
Okay, one more question.
Yeah, I have a question. So do you investigate what you're actually driving? Because initially you just drive a gap, yes, or close to the gap. But then you're changing the frequency, so you have some sidebands for sure in evolution. So what is actually driving? What is the process that actually enhance your eta pairing creation?
Yeah, so
because initially it's just taking electrons from the lower Haber band to the upper Haber band, yeah. But then you're changing frequency, so you have to have a sidebands. And what are the sidebands are?
Right. So we didn't look. Yeah, I understood your question, but we didn't analyze this particular effect in detail. But yeah, I'm happy to discuss.
I see that there are more wishes to ask questions, but we must keep our schedule, sorry. So please, I invite next speaker is Roman Verba from the Bayraktar Institute of Magnetism of the National Academy of Sciences. The talk is speeding up gyrotropic motion of artificial stabilized radial magnetic vortices. And please, 15 minutes and leave some time for questions.
Okay. So the work I present here is a result of collaboration between a group of Gleb Kakazey from University of Porto, group of Maciej Krawczyk from Poznan, and Konstantin Guslienko, who unfortunately passed away last year. And I will be speaking about much simple things. Is the simplest topological magnetization texture is just a magnetic vortex. And it might appear that this object has been studied for a long time, more than 20 years, and what can be new here? But in fact, this magnetic vortices still attract certain attention. Historically, they have been studied for a while in respect with prospect application in vortex magnetic random access memory. Now it's not so relevant application except for some specific environments like in space, but intense investigation of magnetic vortices uncover many other interesting applications. It's magnetic-resistive vortex-based field sensors, which appears to be one of the most sensitive to the date, and nonlinear interaction between magnons in magnetization texture, in particular in vortices, and allows scientists to propose different schemes for neuromorphic non-Boolean applications, like shown here. It's result of our colleagues also from Dresden, but from another institute, is RZDR, and they propose to use this nonlinear interaction for reservoir-based computing in reciprocal space. And finally, it's vortex-based spin transfer torque nano-oscillator, which we'll be talking about in this talk. So what they use? They use so-called gyrotropic motion of magnetic vortices, or Galton mode. So you have a Galton mode is a motion of the whole vortexes, and in particular its position of its core. And if we work with some finite confined structure, we have restored forces coming from edges, and this mode becomes of a certain non-zero frequency. What is important for application? Of course, it's as a usual magnetic excitation. It's possess multi-stability, easy to control both of sense of rotation, frequency, and so on. And in terms of application in spin oscillators, the vortices possess the largest output power. Because when magnetization texture moves, it creates a strong magnetic resistive response in comparison to the simple single domain structure. That is why the most studied object in terms of nano-oscillators, spin transfer torque nano-oscillators, are exactly the vortices. However, there are such certain problems. First of all, is the frequency. And typical frequency of magnetic vortices in soft thin circular magnetic dots like 100 of megahertz. It's very hard to achieve even in 1 gigahertz, and it's to the date it's a little bit small. The second problem is that to stabilize magnetic vortice, we need to success with some geometrical parameter, and vortices exist in relatively thick and relatively large magnetic dots. And relatively large dots, it's not a problem. Large, I mean micron size. But thick dot is really problem for any spintronic application, because spin transfer torque is interfacial effect, it's inversely proportional to the thickness, and of course we want to get vortices in the thinnest as possible dot. So we have two questions. Is there a way to increase the frequency of the gyrotropic motion, and is there a way to reduce the size of free layer of vortex-based spintronic oscillator? And the answer is yes, and what we propose is to add artificial field of radial symmetry to our structure. It can be produced in the following way, so placing a soft magnetic dot in an antidot matrix with a perpendicular magnetic anisotropy, so it has perpendicular out-of-plane magnetization, and this matrix creates stray fields shown here, which has out-of-plane, and what is more important is radial symmetric radial component. And skipping all those calculations, what we found that indeed in such a structure we can expect formation of vortices, but not common vortices. It's not Bloch vortices like shown here. Yes, so curved closed magnetization structure. It's radial vortices or unconventional vortices, which I will shown in the next slide. And calculating the effect of radial stray fields, we found that indeed these fields lead to the reduction of vortex core size. And if we have reduction of core size, then we expect this to stabilize vortex in smaller geometrical size. And this was fully confirmed in micromagnetic simulation. So here are possible states of our soft magnetic dot. Here is radial vortexes, more common object, and certain case we achieve curved or unconventional vortex with some non-zero helicity like shown here. But what is important for our particular problem is that the radial vortexes can be stabilized in much smaller dots than it happens if the dot is isolated. Just 50, 60 nanometers in diameter, and this could be even ground state. It's not just one of a metastable state, and ground state is perfect because from the stability point of view. Even more, if you look on the diagram in the coordinate dot thickness with dot diameter, so it's the same diagram as for free dot. You can see that this diagram becomes reversed. So the vortices are stable in the region of the most thin dots and small in diameter. That is exactly what we need. Okay, this was the part of static. And what about dynamics? For this study, we performed another series of simulations and a little bit changed the structure to this one. The physics is exactly the same because hard magnetic layer with perpendicular magnetic anisotropy produce the same stray field as the antidot. It behave absolutely the same. But this structure is already ready for use in spintronic application because it's exactly spin torque nano oscillator, nothing else. And we see that indeed using realistic parameters of soft layer at Bernoulli standard, hard layer at some of cobalt platinum materials, and we found that gyrotropic modes indeed attract much higher frequency. It's already several gigahertz, and while in free dot we have 200-300 of megahertz, so it's almost 10-time increase. And looking on the dependencies of the frequency, okay, One is trivial because we need to increase the thickness of hard layer to get higher frequency because we increase the fields coming from hard layers. We have untypical dependencies that, one more time, inverted dependencies on the dot thickness, because in free layer, the thicker is dot, the higher is gyrotropic mode frequency. Here we have inverted dependencies, and we have some optimal diameter for our structure to have the largest possible frequency. And here another interesting point is that appeared to us not clear the first look, that the highest frequencies resides in the materials with the lowest saturation magnetization among the reasonable choice. It's also not typical because common behavior, the ferromagnetic resonance frequency is proportional to the saturation magnetization. Here we see unexpected opposite behavior. So to realize what's happening, we develop this theoretical model based on modified use of Peshana and Zatz. And this model, it does not give our quantitative description, but qualitatively we can catch all the features, and then we are able to discuss what is really happening. So in fact, we have 4 different contributions to the frequency of our gyrotropic motion. It's the Zeeman contribution from radial fields, the positive one, out of plane tilt, because we have also some out of plane stray fields. It's also positive contribution, and 2 negative contribution coming from dipole interaction and exchange interaction. And exactly the contribution is from dipolar explains the inverted thickness dependencies. While this one, contribution out of plane tilt, explains the unexpected dependencies on saturation magnetization, because this tilt is the strongest is saturation magnetization, the smallest is tilt, and the magnetization lies more in plane. And this is exactly what is happening. Okay, can we go further? The answer is not very conclusive, because formally, yes, we can use material instead of soft magnetic layers. We can use materials with perpendicular magnetic anisotropy, and
3 minutes.
Yeah, and we can enhance frequency to the tens of gigahertz, but at the same time, the amplitude of output signal decrease. So from the point of prospect of spin torque oscillator, it's not a very good way. So something like 5, maybe 10 gigahertz is reachable. Everything above is not practical. So, and with this, we'll come into conclusion. So the main idea is that strong radial fields in artificial structure with hard layer anti-dot matrix or hard layer dot results in the stabilization of vortex ground state in a much thinner and much smaller soft magnetic layers, which is interesting for spintronic application, especially for spintronic oscillator. And the same structure allows to increase of gyrotropic mode frequency, at least in one order, to several gigahertz, with some viable extension up to 10, maybe 10. And at last, the funding from National Research Foundation is also should be acknowledged. Thank you for attention.
Thank you. So the talk is open for discussion. Any questions? Please.
So it's very interesting you find this higher frequency. Can you give some physics intuition why this increase happens?
The main reason of increase because radial fields from the matrix create additional confining force. So you can see that the most positive contribution is exactly this one, and this function is nothing other than strength of radial stray fields. So we have just additional confining potential.
Okay. Any more questions? So if not, please. Yeah.
Please slide with resonance line, vortex line.
This one.
Oh, this. Explain, please. This is experimental.
No, it's simulation.
Theoretical?
Simulations.
Do you make experiment? No?
Not yet. We are waiting for samples.
Okay. But maybe for this, your objects can be used for magnetic resonance technique.
Yes, sure. For magnetic resonance for gyrotropic motion is absolutely okay. It works.
Thank you.
Okay. One more question. So the last question, please.
So thank you for the talk. So I'm just curious, where are you expecting samples from, and do you have this gigahertz equipment at your institute?
We have gigahertz equipment and samples Brno University. Brno, Czechia.
Let's then speaker again. And the next talk will be given by Olha Boliasova, SKU Academic University. The title of talk is Electric Field Control of Spin Wave Dynamics in Antiferromagnets, the Aharonov cache effect. Please, you have 15 minutes, and please leave some time for questions.
Okay. Thank you very much for introduction. So I am one of the organizers of this conference from Kyiv Academic University. So first of all, I want to thank all other co-organizers. And also, I hope that everyone participant will enjoy this conference and maybe will participate in the next ones. So today it will be a topic about electric field effect on spin wave propagation on insulating antiferromagnets, maybe not so cool and popular as altermagnets, but I hope that there will be something interesting for you. So, how can I change slides? My outline will be the next, so I will start with introduction. Then I present the model, and the main topic is damping for this presentation. So, considering damping, you can use two approaches. So you can use the real part of the frequency, and for the wave vector, you can use real part and imaginary part. And you can find like special damping. Another option is temporal damping, so you can use only real part of the wave vector and also a real and imaginary part of the frequency. I will summarize everything with conclusions and acknowledgements. So I think you already know a lot about insulating antiferromagnets. It's just a short reminder that they have some promising features for future magnetic devices, like they are stable to external magnetic fields, they have target separation speed, lower power consumption. There are lots of such materials in the nature, and one of the features that we could use the chirality in antiferromagnets. So under the impact of some external fields, we could distinguish left-handed and right-handed spin waves, and compared to ferromagnet, in addition to phase and amplitude, you also can manipulate by chirality. So what is Aharonov cache effect? It was firstly introduced in 1984 as topological effect, and it is very similar to Aharonov bomb effect, where the charged particle moving around magnetic field acquired additional phase shift in its wave function. So Aharonov-Kesher effect, it's very similar. Here is a neutral particle with magnetic moment. It's acquire phase shift in their wave function moving around electric field. So there are some experimental results for ferromagnets that was made by Sergey and his colleagues in 2023. So they showed that if you want to have a good agreement with measurements, you should also take into account the Aharonov-Kesher effect. And you have also found very interesting effects when you apply a different electric field to ferromagnet with a different electric field. So on this body between these ferromagnets, you can refract the spin waves, and depending on the direction of electric field in one and other ferromagnet, they could refract in one side or in the other side. So the model we are considering here some easy axis antiferromagnet with two sublattices, and for its energy we take into account non-homogeneous exchange coupling, homogeneous exchange coupling, anisotropy along that axis, and electric field effect. At some points we also take into account magnetic field, and this electric field we have here is vector D, which is proportional to electric field, some exchange constant, and spin orbit coupling. To discover this dynamics, we use two equations of Landau-Lifshitz-Gilbert, but with some slight change. So usually people consider only one damping parameter, but here we consider an antiferromagnet and have two sublattices. So there is a possibility to have another damping. So for example, here we consider damping inside the sublattice and damping between sublattices. And such approach was introduced by Kamra and his co-authors in 2018. It's just a short reminder that if you do not have any external field, you have this black line, so the spectrum is degenerate, but when you apply electric field, you can split the spectrum into right-handed and left-handed spin waves. In addition, if you apply magnetic field, you also can make a shift, but magnetic field shift the spectrum along the energy axis, and the electric field made the shift along the wave vector. Here's the energy split, and so it depends on, it's proportional to electric field. The bigger electric field, the bigger this effect. And in addition, if you apply magnetic field, you can also influence this effect even more. To consider a spatial attenuation, we use in a wave vector with real and imaginary part, and can present magnetization vector in such a way where lambda is our attenuation length. We have found a formula for this attenuation length, and here K0, it's some quantity of wave vector which corresponds to the shift of the spin waves along the k-axis. And the bigger the applied electric field, the bigger difference between attenuation lengths of right-handed and left-handed spin waves. Here you can see how attenuation lengths looks like when you apply electric field and magnetic field. So if we apply just electric field, we split right-hand, left-handed. In addition, if we applied magnetic field, the splitting could be bigger. And if we change the direction of magnetic field, we can swap this curves places. And here you can see the difference between attenuation lengths of right-handed and left-handed spin waves, and also this central symmetric line, it's when you apply only electric field, and this non-symmetric lines when you in addition apply magnetic field. So at some point we found such people that found it, named it like superluminal like magnon propagation. So they observe a magnon velocity of 650 kilometers per second in the nickel oxide layer. And the more in a point from theoretical point of view that they could observe such a high velocity that previously considered only like 40 kilometers per second, it was that they take into account damping. And the low damping, the bigger effect you can see. So we tried to figure out how it could be in our case. So firstly, we found spin wave spectrum. So if we do not take into account damping, we see regular curves. But if we add and take into account these damping parameters, we could see in a small region some a big dip, and it corresponds to this damping effect. And additionally, we can see that when we apply electric field, this curve splits, and also right-handed have like this dip and left-handed like this. Without electric field, you can see one dip in the center. And it also impacts the group velocity. So without damping, using our parameters, we found like that group velocity is around 3 kilometers per second. But when we take into account damping, we found that it could be around 300 kilometers per second, and so on. So here is similar effect like with spin wave spectrum. If we take into account damping, we see a small region of unusual behavior. But the other part of this group velocity is similar, like you are not taking into account this damping. So this is one of the reasons why people tell this is not was discovered earlier or didn't pay attention for it. For temporal damping, we use only real part of the wave vector, but for spectrum we use like real part and imaginary part, and could find that the temporal damping has the same structure as spectrum, so it's very similar curves. The red ones correspond to right-handed spin waves, so the blue lines correspond to left-handed spin waves. So the bigger applied electric field, the bigger difference between this temporal damping. So here it is the most prominent effect of taking into account additional damping parameter like inter-sublattice damping. So if here we see the ratio between damping and frequency. Here we use the same intrasublattice damping, but we change intersublattice damping. And when we use smaller intersublattice damping, the damping is higher, but when we increase intersublattice damping, a part of this temporal damping is lower considering to the frequency. And this is intersublattice damping. It has like anti-damping character. Here you can also see the difference between lifetimes of right-handed and left-handed magnons. And if we consider that there are no any intersublattice damping, lifetime of right-handed and left-handed magnons are equal. But if we take into account this intersublattice damping, the bigger this intersublattice damping, the bigger the difference between this lifetime of two spin waves.
Excuse me, 3 minutes.
Okay, thank you. So I'm summarizing with conclusion. So electric field controls chirality, frequency, propagation length of the spin waves. Depending on the magnetic characteristic, you can have a group velocity, for example, 300, 600, and so on kilometers per second, and the maximum the group velocity is shifted at a distance of plus or minus k0 depending on its chirality, and this shift is proportional to the applied electric field and depends also on the exchange energy and spin orbit coupling of the antiferromagnet. And the intersublattice damping coefficient ensures that the temporal dissipation of right-handed and left-handed spin waves is different under the influence of an electric field. The presented results published in these two papers. So this work was made with Volodymyr Krivoruchko from Donetsk Institute for Physics and Engineering, named after Galkin of the NAS of Ukraine. It also was supported by German Ukrainian Research Center for Quantum Materials between IFW Dresden and Kyiv Academic University. Also, I work in Kurdumov Institute for Metal Physics of the NAS of Ukraine. And thank you for your attention.
Yes. So thank you for keeping the schedule, and talk is open for discussion. Any questions? Please.
Thank you. Regarding this intersublattice damping, okay, from this point of theory, I believe that it's allows some such terms. Do you know experimental work where this intersublattice dampings have been quantified and how much it could differ from intrasublattice damping?
Okay, so I didn't know such work for insulating antiferromagnet, but there's some work for metallic antiferromagnet, and they found a big difference between these two damping parameters, and it could be like 3 orders. But it depends also on materials.
Are there any more questions? Please.
Thank you for the talk. It's quite new to me. Can you explain briefly what is the microscopic mechanism for the coupling of magnons to the electric field?
So this is like when moving neutral particles with this magnetic moment, so it's like interact with field, but it's could be not in this field. It's like for this connection with potential of the field.
So if I understand correctly, what you're saying is that the field breaks the symmetry, for instance, like an inversion symmetry, which generates a Jaluzinski-Moraia, which then...
Yeah. Yeah, and it's very similar to Jaluzinski-Moraia. For theoretical point of view, it's almost equal, but with electric field, you could modify it more easily. So why people already use it and discovering some effect.
Any more questions?
Yeah.
Yeah, so just a question. So concerning the damping coefficients for the intrasublattice, intersublattice, is it understood why one of them should be much smaller and which one? Is it like microscopically understood?
Actually, it's not quite understood, and there's some discussion about should we take into account this two damping parameters. So, for example, some people didn't, for antiferromagnets, they also didn't consider additional damping parameters, or they could consider the difference of these two damping parameters. And maybe it's a field to more for more discovering, because and in insulating antiferromagnets it is small, so maybe no many scientists pay deep for this field.
So far it's more like phenomenological, yeah?
Yes, it's yeah.
Okay, last question.
Okay, just to clarify something, you are talking about the centrosymmetric structures.
Yeah.
So really crystallographically, no chirality is possible. This definition of chirality, you cannot build enantiomorphs within the centrosymmetric space groups. Well, what is the basic? Well, but you introduced the chirality in your consideration. Well, I understood this is just the influence of the electric field.
Yes.
But it cannot be that's to say a general influence of electric field. It should be some kind of symmetrical relation between the vector of electric fields and the crystallographic axis. Can you
I think yes. So it could depend because first, this effect was introduced like topological effect, so not dependent on this directions of all fields of electric and magnetization. But now there are a few works that say that it's more a geometrical effect, and it depends on the direction between electric field, magnetization, and the propagation of the spin waves.
Let's no, we might very short.
Can I make one remark because what Yuri said? So that's absolutely correct. But if you have a centrosymmetric crystal, still it is a ferromagnet. Then in this language, it's chiral because the magnons of a ferromagnet have a chirality, have a handedness because the G factor has a certain sign, and that's. No, chirality is the most abused word in modern condensed matter physics, I think. But one of them, one context is magnetism, and the other context is the crystallography that you correctly refer to.
Thank you.
Thank you for questions.
So let's then speaker again. And I invite next speaker. The next talk will be given by Oksana Kvitnytska from the Leibniz Institute for Solid State and Material Research in Dresden, and working Institute for Low Temperature Physics and Engineering of the National Academy of Sciences of Ukraine. Please, you have 20 minutes and please leave some time for questions.
Thank you very much for the introduction, and I would like to thank organizers to present our results in our beautiful Lviv. And here I switch to the superconductivity and to point contact study of well-known superconductor platinum bismuth 2. Let me introduce some properties and measurements which are important or relevant for our study. Platinum bismuth 2 is known to exist in two phases. This is cubic one and trigonal layer structure. And trigonal platinum bismuth 2 is supposed to be candidate for topological superconductivity. So electronic structure, it has electronic structure characteristics for type 1 vile semimetal, and also it shows the traces of superconductivity as seen in transport measurements with a rather low critical temperature of 600 millikelvin. This critical temperature can be increased in bulk by applying of pressure up to 2K, and also doping of trigonal platinum bismuth 2 with different elements can increase critical temperature up to 2.7 K, as in the case with rhodium doping. Also, in our previous point contact studies, we demonstrated that point contacts shows enhanced critical temperature up to 3.5 K, what is much greater than the bulk critical temperature. In thin flakes of platinum bismuth 2 up to 60 nanometers was revealed Brzezinski-Kosterlitz transition, what is convincing proof of two-dimensional superconductivity in this material. Also, scanning tunneling spectroscopy experiment observed the presence of the surface superconductivity at 5K with a rather huge gap of 20 millielectron volts. Next, recent ARPES measurements report about superconducting Fermi arcs at the surface of the trigonal platinum bismuth 2 up to 10K, whereas the bulk electronic states remain non-superconducting. Thus, trigonal platinum bismuth 2 is the ideal platform to study two-dimensional superconductivity in topological semimetal, which can lead to new types of topologically protected states. However, some issues of unique superconducting behavior in this material remain unclear. For example, such as unhomogeneity of superconducting state, absence of superconducting traces in low temperature specific heat or magnetization data, also absence vortices, and so on. Point contact study on a number of different topological materials showed enhancement of superconducting critical temperature. Here I would like to mention our previous work on molybdenum detelluride, tungsten detelluride, and our previous work on these materials added platinum bismuth 2 to such a list. And here in this work, we performed further extensive point contact measurements of platinum bismuth 2 using different high quality samples of this material and using different contour electrodes. What is point contact spectroscopy? It was experimentally discovered by Igor Jansen in 1974. He demonstrated that second derivative of current voltage characteristics of point contacts, ballistic point contacts at low temperatures, contains detailed information about electron-phonon interaction spectra. And thus, point contact spectroscopy is a powerful method for the investigation of different quasi-particle interaction in metals, such as electron-phonon, electron-magnon, quantum scattering, and so on. At the nanoscale down to 1 atom point contacts and under ultra-high current density up to 10 power 8 ampere per centimeter square. Point contact spectroscopy is also a valuable tool for the determining of the superconducting energy gap and parity via Andreev reflection processes at the interface between superconductor and normal metal. For the ballistic point contacts between superconductor and normal metal, differential resistance for decreases up to 2 times for such contacts. Blondin, Kingham, and Klapfeig, exploiting concept of the Andreev reflection effect, calculated transmission and propagation probability of electron through the SN interface. They shown that differential resistance at 0 temperature and at 0 barrier value looks like flat minimum with width of 2 delta. In real point contacts, if barrier parameter is not equal to 0, additional 0 bias maximum appears on differential resistance, and as a sum, we have 2 minima structure, which is characteristic for Andreev reflection effects in point contacts. And position of this minima roughly correspond to the superconducting order parameter. These calculations are valid for the ballistic point contacts with conventional S-wave superconductors, and in case of P or D wave superconductors, Andreev reflection processes reflects in differential resistance or conductance as single bias minima only, and it makes it difficult to distinguish between point contacts on unconventional superconductors and conventional superconductors being in non-ballistic regime, in thermal regime of the current flow. Our previous measurements on platinum bismuth 2 shown enhancement of the critical temperature in point contacts up to 3.5 K, as I already mentioned, and the prime origin of such enhancement could be a pressure, which is always presented at the point contact creation of the pressure type. But observed critical temperature is much greater than the critical temperature available in the pressure measurements on the bulk. Also, in previous work, we measured for the first time electron-phonon interaction spectra, platinum bismuth 2. So Janssen point contact spectra reveal maxima at 15 millielectrons, which millectron volt, which is due to supposedly phonons, and this spectra corresponds pretty good to the theoretically calculated Eliashberg electron-phonon interaction function. In connection with our study, I would like to mention another point contact study made by a Chinese group. They measured point contacts between platinum bismuth 2 and non-magnetic counterelectrodes and magnetic counterelectrodes, and in both cases they observed enhancement of superconducting temperature only up to 3 K. But for the point contacts with non-magnetic electrodes, they succeed to detect pretty good Andreev reflection spectra. This is double maxima structure in conductivity of point contacts. They estimate superconducting energy gap value, which is about 0.4 millielectron volt. And in the case of point contacts with magnetic electrodes, they observed only zero bias maxima, which they attribute to unconventional superconductivity. And so the claim that magnetism of metallic tip could influence on the symmetry of the enhanced superconducting state. Let's turn to our results. Here in the slides, a variety of differential resistance of different getter point contacts with platinum bismuth 2 is presented. Unfortunately, we could not detect Andreev reflection spectra, no double minima structure, only a single minimum structure due to transition in the superconducting state. So we suppose that our contacts were in thermal regime of the current flow. The intensity of the structure decreases at increasing temperature or magnetic field, and it disappears at reaching of critical temperature. As we can see here, critical temperature for presented point contacts even more higher than in our previous work, And also the most presented series of these contacts with magnetic counterelectrodes. So we conclude that superconductivity in platinum with Mo2 is compatible with the magnetism in counterelectrodes. Here, the distribution of superconducting critical temperature in superconducting critical field is presented. As we can see from this distribution, mainly TC is situated between 3 and 5 K, but notably highest enhancement of TC was detected for several point contacts, such as with magnetic counterelectrodes and also non-magnetic electrodes up to 8K. And critical magnetic field was found to be also greatly enhancement. Here we made also interesting observation. We established our point contacts in two direction. First group of measured point contacts, the tip was perpendicular to AB plane of platinum with Mo2, and the second one is the tip touched the edge of crystal flakes. And we observed that in for the plane point contacts, TC, average TC was about 3.7 K, and in the case of the edge contacts, TC was 1 K greater. This data can be in support of anisotropy of superconducting gap in platinum with Mo2. Another interesting observation, this is sometimes we observed such point contacts characteristics with two set of superconducting features, and the small minima disappeared usually at 3K, and the second one at much higher temperatures. If we were in ballistic regime and could detect Andreev reflection spectra, like in the case of well-known two-gap superconductor magnesium diboride, then we could speculate about two-gap superconductivity, but unfortunately this is not the case. And what we can conclude from such characteristics that probably this is multi-contact configurations, and such characteristics are also in support of anisotropy of superconducting gap in platinum with Mo2.
So, excuse me, 3 minutes.
Yeah, we also investigated GOMO point contacts. This is contacts between two flakes of platinum with Mo2. The purpose was to avoid possible intercalation effect from the counterelectrode, but in the case of GOMO contacts, we observed the same or even greater TC, like in the case of hetero contacts. And the last studies of soft point contacts, this is point contacts created between crystal and dripping of a small drop of silver paint between crystal and thin wire to avoid pressure effect, which is usually exist in pressure type of point contacts. For soft point contacts, the superconducting features were much weaker than for hetero point contacts, but nevertheless, critical temperature was much higher than the TC of the bulk, being between 2.5 and 4.5 Kelvin. So let me summarize our observations. The enhanced TC in mainly between 3 and 5K with notably a maximal TC rising up to 8K. Pressure is the primary origin of the enhanced TC, but at the same time, the enhanced TC is more than 2 times greater in comparison to the measurements under pressure of the bulk samples. And enhanced TC is on average greater for H-point contacts, what is in support of anisotropy of superconducting gap. There is no essential difference in TC enhancement by using normal or ferromagnetic tips. And we observe compatibility of enhanced superconductivity with magnetism, and this may suggest the complex nature of enhanced superconductivity. Observation of the same enhancement of TC in both homo and hetero point contacts eliminates doping as a possible reason for the TC rise. And also soft point contacts exhibit weaker superconducting signs with a low TC. And this is in support of predominantly pressure impact, but contrary observation of superconductivity in soft TC may serve as confirmation of surface superconductivity. And I would like to thank collaboration during this work to the sample preparation team. This is Luminita Harnaya, Grigory Shepunov, Svarham, Irina Kovalchuk, our point contact spectroscopy team, Dima Balshakov, Vasil Fesun, Yuri Naiduk, and also support and cooperation with IFW Dresden, Dima Efremov, and Bernd Buchner. Thank you for your attention.
Thank you. The talk is open for discussion. Any questions, please?
So the TCUC is higher than bulk, but it also seems lower than surface. So does this mean you're mostly sensitive to bulk superconductivity? And if so, why?
Why? This is a difficult question. Point contacts technique is sensitive, yeah, for surface, mostly for surface.
Mostly for surface?
Yeah.
Okay.
Okay. Please.
Yes, thank you for asking the question. I wanted to do the same and then a follow-up one. So we have those two different surfaces, right, in the platinum bismuth 2?
Yes.
Did you test both of them and do they result in the same?
No, in our experiment, it's impossible. So I tried to test both sides of flake, but no, I found no difference. Yeah.
So how big does the crystal need to be for a measurement in point contact? Can you measure flakes also?
Crystal size is usually a couple of millimeters. Yeah.
Please.
Thank you for the talk. Suppose that the superconductivity that you see is two-dimensional or very anisotropic, would that be visible in like angle dependence of critical fields, for instance? Did you check for that?
Unfortunately, I have no such possibility, but I tried, in differential orientation of magnetic fields, but I found no difference, but probably one need more statistics because here is huge amount of point contacts measurements and yeah.
Because if you do the electrostatic doping, which was done at IFW, you see that it is very two-dimensional, but
yeah,
it's a different situation, but still, yes.
Okay. So maybe we shall finish with questions. So let's thank speaker again, and let's thanks to all speakers of this session. And now it is the lunchtime, and next session will start at 2 p.m. Right?
So good afternoon. Let's start this afternoon session. Our first speaker is Jacek Herbrych with the talk Electronic Correlations Driving Chirality-Induced Spin Selectivity. You have 30 minutes. I will show you 5 before the end of the talk.
Yeah. Hi, thank you for introduction. Thank you for invitation. And most importantly, thank you for hospitality. I have a fun. It's actually a nice conference. And I wanted to tell you work that we did with Maria Dachover. We just submitted like last week. I'm in a strange situation because if I knew what I know right now, this whole project should be one paragraph in some paper in 2020 that we did together with Elbiota Gotto and Adriana Mareo, and also Maria Dachover was there. Yeah, but we didn't know that. So yeah, I want to talk about concept that we already introduced. So I want to take Krzysiek's idea yesterday that electronic correlations can give funny things, especially if there are strong electronic correlations. And I want to come back to Pavlo and Jan comments about some kind of non-trivial magnetic structures. And what we mostly do in my group is we are trying to do all of that, but just not through heterostructures, but through electronic correlations. So some kind of main topic of this talk is that, you can have a spin and charge, and often we ask a question, who's driving and who's a passenger? And all the talk today, it will be spin, will be crazy driving the electronic properties of a system. So what I didn't know 5 years ago was Chirality-Induced Spin Selectivity. For those of you who are not familiar with this effect, is actually unresolved to some extent issue. So let me guide you through experiment. You shine your laser on a gold substrate, and depending on the polarization of your light, you can induce polarized electrons. Laser doesn't, the electric field doesn't couple to spin directly, but polarized circular light carries angular momentum, and if you have something with strong spin-orbit coupling like gold, you can couple to the orbital, and since there is a spin-orbital coupling, you can induce given polarization. So what I'm showing here is just exactly what I described on a gold substrate. These different curves, green, blue, and red, represent different polarization. And depending on the polarization of a light, you can induce polarization of your ejected electrons. Yes. So if you have one or other polarization, you have more of these electrons. If you have a linear polarized light, you have just an average, you are on 0. So the people figured it out in 1999. But what I'm showing this beautiful experiment from 2011 is that if you coat this with some kind of chiral molecules, and here is so in this experiment they did DNA, and you repeat it, all of a sudden you have just all electrons have one polarization. And here is so recognize that this plot is from -50 to 50%, but this guy is from 0 to 60. So you have just one polarization. And so right now, we have plenty of examples of that, and typically these are things that I cannot even spell properly. These are biological molecules, but we see this not only from the substrate, we see this also on isolated molecules, and these are some kind of example of crystals, but also whatever this thing below is. So what's the theory behind it? So naively, you will say that spin orbit coupling plays important role. Yes. So you have a chirality based on your substrate. Now chirality allows for spin orbit coupling. So maybe you have some rush bar that you split bands, and this some kind of drives the phenomena that you have here. But this is actually not true for 2 reasons. One reason is that it will be so simple like this, right? Here. In reality, here and here, you'll have just delta functions. Yes, you'll have a not net magnetization in any direction. But the bigger problem is that biological molecules are light elements. It cannot be strong spin-orbit coupling in these molecules themselves. So there will have to be some kind of different mechanism. And now here is the whole zoo of a theory. This is, Sergey said it in the morning, is that nobody knows what's going on. And I'm showing you just two more or less recent reviews, and I will emphasize one word, theories of Chirality-Induced Spin Selectivity, and I'll just contribute to this, like, why not? Let's have it one more. So this theory is typically, to some extent, mix the fact that, well, in a substrate, I have a strong spin-orbit coupling. In my molecules, I don't. So, and there is some kind of interface. So, you know, there's like many theories for that. I will simplify this to very simple thing. And this is observation of Maria Dahofer, that if you look on DNA, how people try to model DNA, they actually, so here in this specific theory, they consider orbital order. So you have an orbital order in your system. So again, you can couple to orbital, which gives you some kind of spin polarization. But for us, the most important thing is that this thing is multi-orbital. So that's all what I need from my introduction here. So let me introduce multi-orbital model, and this will be workhorse of this presentation. So this is two-orbital Hubbard-Kanamori model, the simplest two-dimensional SU2 symmetric fermionic models, if you want to describe it. It's slightly more complicated than usual Hubbard model we typically know. The first term is just kinetic energy. Electron can hop on a lattice, but they can hop on two different orbitals. There is a crystal field splitting, and that's all. So there's nothing special here. Interaction has a standard Coulomb interaction, so the electrons repel if they're on the same side and the same orbital. But obviously, if they're on the same side but different orbitals, they will also repel. Chemistry tells us that should be also Hund's rule, so spins tend to be ferromagnetically aligned if they're on the same side on different orbitals. And for SU2 symmetric reason, there is also a term which is pair hopping, so there is a non-zero possibility that two electrons will jump simultaneously, but this is just to symmetry reason. This has nothing to do with superconductivity. Okay, so for small Hund, the phase diagram is like everybody, you know it. So there is a metal insulator transition. I'm in 1D, so in reality, I have an activated behavior, but well, we know all of this story. Now, interesting things happen if you have a large Hund, because there is another phase. It's called orbital selective mode phase. So in a systems where your two bands are unequal, have unequal hopping, one band can localize faster than the other. So one band will behave like a mode, and other will behave like still a metal, and they coexist. And this is orbital selective mode phase. So this is an example that these are numbers that I'm using in this presentation. So I have a wide band and narrow band. This is two orbital model. And there is also some crystal field splitting, but these numbers are not really important for all of this physics. So, and then I do, everything what I will show you is coming from DMRG in one dimension. So we can do large systems, 100 sites, 200 orbitals. We can also do dynamics. So we don't see large finite size effects. So what I'm showing you is just simple ARPES, a single particle spectral function, somewhere for small value of interaction. And all of these parameters obviously come from Coulomb. Yeah, so they're all related to each other. So in this talk, I will use that Hund is a quarter of a U. It is slightly larger than we see in real experiments, but we also don't see strong dependence on this Hund. Okay, so coming back, so this is small interaction on the very end. This thing is the same because there are small interactions, the bands are just renormalized. But if your interaction is large, so I express everything in a width of a kinetic energy, so around 2 electron volts if you want, or just 2. What you see here is that you have a one metallic orbital which crosses Fermi level, and this behaves like a metal, but this red color represents the narrow orbital, which now acquires a gap, and there is localized electrons there, and there is no charge fluctuations. All of this can be checked. And what is nice, what we did in the past, we actually recognize that as long as you're in the orbital selective mode phase, you can do standard Schiffer-Wolf transformation on the localized orbital. So then you'll have from the localized orbitals, all these spins will remain. The metallic orbital, you cannot touch it because there are still charge fluctuations there, and you end up with some kind of Kondo lattice model. But there's still interaction here, and this interaction is like semi-relevant. And it works perfectly. So this is comparison of a density of states between this two-orbital model and this Kondo-Heisenberg model, Kondo-lattice model. It's perfect as long as we are in orbital selective mode phase. So I'll switch between two-orbital and this Kondo, but well, I'll emphasize what that is important. Okay, so this is generic phase diagram. This is more detailed phase diagram right now that I'm interested in magnetism. So here I'm showing you on the y-axis there is the interaction strength, and on the x-axis is a filling. Okay, so remember that this is Kondo consideration. So filling is just in the metallic orbitals, and since I'm in OSMP, localized orbitals has always 1. So if I'm not have filling, this is like paramagnet to antiferromagnet transition. We know this. If I have a small interaction, I will always have a paramagnet. And there are many other phases that I want to comment right now. So we did for the last 5-6 years, we did actually a lot of work on this, on many topics that we actually cover here also. So for filling, this is some kind of physics of doped spin 1 antiferromagnet. This phase that I will comment in a second is relevant for iron-based superconductors. There is this non-trivial magnetic phase that is the most important for this talk. And also there is, well, you can describe here magnetites or maybe triplet superconductors. I will not comment on that, but you can, to some extent, find some analogy to it. So I had this slide like half an hour ago after the comment of Jan. So the phase diagram that I just showed you is in 1D. We actually did it also on the ladders, and so my student Max Hiroda did extensive work on two-orbital ladder and then on a Kondo ladder, and then indeed in the middle of this phase diagram for proper numbers within orbital selective mode phase, we can find phases like quantum spin flux, we call it right now, which is then on the ladder, on the plaquette, the spins rotate. But remember that I'm in a low-dimensional exact study, so I don't break any symmetry. So this is, think about this, I have a nil, because I have this state I'm presenting, and also opposite, yes, because I never break any symmetry, in a sense. And then the final plot I'm showing you that all of these phases that I will discuss in a second are actually also visible on a two-dimensional or just iron-based superconductors. Here I'm showing you some kind of flagship results for iron selenide and iron telluride, that the fix that the magnetism that I'll discuss in a second is also there. I'm especially interested in such a phases like this 2 up, 2 down, they call it dimer order, or this red color, which is a spiral order. And then depending on the pressure, the materials are in different phases, which are here, these dots. So I'm not claiming that I'm describing two-dimensional iron-based superconductors. I'm just saying that the phases that I will describe in a second are actually relevant through all the families. Right. So this is a family that this is the magnetism I'm most interested in. I want to. It's also not extremely theoretical concept. We had yesterday during the dinner nice discussion about theory-driven experimental findings, and this is exactly like that. So in 2015, Martin Murgiel had a beautiful results on so-called 1-2-3 Fermi or family of iron-based superconductors. These are ladders, low-dimensional ladders, where he actually found that the magnetism is a block magnetism. So within the ladder, you have a 2 spin up, 2 spin down, or 4, depending on how you think about this. Yes, so you have a 4 spin up, 4 spin down, block magnetic structure, and this was predicted by us in 2014 that we did when we look on the correlations of a spin correlation in this model, we actually indeed find that if you look on the correlations, you don't get standard antiferromagnet, but 2 up, 2 down, 2 up, 2 down, 2 up, 2 down. And we understand why it's going on. But the most important here is that I want to right now change the interaction along this line. So I want to start with this somewhere here and just move up. Okay, so this is the result. I'm showing you results from a Kondo lattice model. This is spin-spin correlation. So you see that for interaction order of 1, you have this 2 up, 2 down, 2 up, 2 down pattern. If you have a very large interaction, so if you move somewhere here, you have a ferromagnet, so you have a ferromagnetic spin correlations. And in between, you get some kind of strange sign profile. Now, why is a ferromagnet on the very end? We understand, because this is Kondo. If your Hund is large, if your interaction is large, so your Hund is large, and if your Hund is large, you'll end up with some kind of double exchange mechanism that drives everything. Okay. Now, so obviously now you can do a Fourier transform of that, and you'll get something that you can measure in scattering experiments. So this is static spin structure factor. You start with pi half. Yeah, this reflects this 2 up, 2 down. And then on the very end, for large interaction, you get ferromagnets. So you have a peak at Q0. Right. But in between, you smoothly move between this. So this is actually unusual. But what would happen, the magnetism could just, one peak could grow, other peak could go down, and I'll get the same transition. But here it smoothly moves. So that was like, nice observation. So let's calculate chirality. So on very end, I'm defining some kind of kappa, which is S cross S. If I have two spins which are parallel to each other, makes no difference if they're parallel or anti-parallel, this will give 0. Now, if there is some kind of angle between these two spins, I should get a finite value. But remember that I'm in a 1D, quantum mechanics, Marvin Wigner forbids me to break symmetries, so I have to look on the correlations. Okay? So indeed, in this block phase, I have a 2 up, 2 down. This is just 0. In ferromagnet, this is just 0. But in between, I get a finite value. Okay? And now, there is no frustration in the system. This is simple Hubbard model. There's nothing special, but I'm getting some kind of exotic state. So at the time we actually figure it out, that what happens is that you start from these blocks 2 up, 2 down, and you start to rotate them till the ferromagnet. And the ferromagnet is spiral with an infinitesimally small pitch. And we can do this for different doping. We'll get the different spirals. I mean, I will not show the proof that this indeed blocks rotate. We can discuss this later if you wish. For me, the most important thing is now, this is magnetism. But on the end, I have a metal. Yeah, so I have an orbital selective mode phase. So how the electrons look like? So now this is the results. On the left-hand side, you have a 2-orbital Hubbard model. On the right-hand side, you have a my effective Kondo description. So let's starting from 2-orbital. These are localized bands. Yeah, so this is OSMP. So and there is a metallic bands which have such a structure. Yes. Okay, and this is my workhorse. So let me just clean slightly a bit. This is the same result. I just rotated. Here I'm showing density of states. Here I'm showing what I showed you just a few seconds ago. And here I'm showing you states at Fermi level. So let's come back to the spin orbit. And I'm zooming in because we want to talk about this Cis effect, this electrons which are ejected from the gold. So only states close to Fermi level are relevant, so I just zoom it. Right. So let's come back to spin orbit coupling. Typically, what we teach students is that if you add some kind of Rashba in some given direction, you will have a band splitting. Okay. And now what I argue is that this thing. So maybe that this thing looks very similar to this thing. And I can even fit the results. Yes, so we can solve this exactly. This is simple tight banding calculations, 2 cosine plus 2 sine from spin orbit coupling. And I have an effective spin orbit coupling, which is 0.6 of a hopping. So this is huge. I don't have any spin orbit coupling in my system, but effectively I have something like split of a bands of a spin orbit coupling, which is order of the same of a hopping. Now remember that in reality, there are differences, yes? So in normal spin orbit coupling, I should have a spin split bands. Here I just have a shape, which is very similar. And this was like brilliant observation. Is like, okay, let's add infinitesimally small spin orbit coupling to our system. So here is the spin orbit coupling is like 2 orders of magnitude smaller than T itself. Yeah, so I didn't dare in my numerical calculations go to even smaller number. Probably this holds for infinitesimally small, but nevertheless, I have a 2 orders of magnitude smaller spin orbit coupling than my hopping. And then all of a sudden I get everything what I should want. Yeah, so I have a spin split bands, very large. So although this is 0.04, my effective one is 0.06, order of magnitude larger than I actually put it. At Fermi level, I'm solving the problem that typical spin orbit coupling will have, that this contribution and this contribution are the same magnitude, so you will not see anything in experiment. But my many body calculations, that this is suppressed, so this is positive directions. You can think about this. This is positive direction, this is negative direction, and I get I can have a polarized electrons from Fermi surface. So now, one of the important things that this in this chirality-induced spin selectivity, what experimentally is observed is that this effect is almost at room temperature, or for sure order of magnitudes larger than presumable spin orbit coupling that you could have in your biatom molecule. So Maria now, so why this happens? Okay, so our explanation is very simple. So typically, if you solve in low dimensions your system, you'll end up with some singlet. Yes, solve Hubbard model, you have just a nil antiferromagnetic singlet. And then if you add a staggered magnetic field, you will project on one of singlet projections. This is the same happens in our model, but we have the spirals are in all possible directions because, again, I don't break any symmetry. And then I'm adding small spin orbit coupling, so I just project on given direction. So then depending how I choose the spin orbit coupling or how it is in given material, I can project on given material. So this is like, simple mechanism of a complicated physics. Right. So then, so this, we are coming back, what I just said is that I have a correlations induced non-trivial magnetism, and electrons just follow it. Now, if I add spin orbit coupling, it's just choose the directions and the projections of my bands. Okay. So then, just to confirm it, Maria did classical Markov chain quantum Monte Carlo results, just to confirm that this survives at finite temperature. So right now I'm just showing you one of the projections at temperature still to some extent very small. And then so what is nice here is that we can now actually measure indeed the polarization. So we know we can relate density of states to the velocity, which is just curvature of a band, and we can present results which have just negative or positive curvature, so should be just given direction, and here I'm showing you just given direction. And then Maria did calculations finite temperature, even of a temperature order of 0.1 of a hopping, so this will be this red curve here. We see that one projection dominates at Fermi level, and indeed here we will have a not equal populations of electrons that we eject from the substrate. Right. So this is, I'm actually finishing. So this is my some kind of conclusion is that electronic correlations can drive non-trivial magnetism. We know that. And if it's really, really crazy, you just need slight little push. Okay, that actually then you'll project on one of your crazy stuff, and then you can see what they see in experiment without involving large spin orbit coupling. That it's not possible in organic compounds. Now, what is also very funny here is that typically your scales of your problems are given by spin orbit coupling. But here is electronic correlations that obviously if I change electronic correlation, the strength of it, or density, we know that it's not always strength of interaction. We can also control it with amount of electrons if we have a system. We change the length of our spirals, or change the correlation length of our spirals. So then changing the density, so this is just change of the density, we can actually inverse the projection, which is very funny, yes, because I can now, by some kind of bias, can dictate in which directions my which polarization my electrons will have. Right, that's all. Thank you for attention.
Hey, thank you. Okay, we actually have even 7 minutes for questions.
Yeah.
Okay, please.
Thank you, Jacek. Would one way of understanding it that you start with an SU2 invariant Hamiltonian and then you break the symmetry to actually Z2 or to some okay.
Yeah, exactly. Yeah. And then this can be infinitesimally small, yes, because it's just projection on.
Yeah, because you have an incipient order parameter that you
exactly.
couple to.
Yeah.
Okay, more questions? Okay, please.
Yeah. Thanks a lot. Yeah. So first of all, I think I got it correctly, but just to make sure. So you've got this block spiral spins, and when they dictate the electronic bands behave like this in this So because you've got this orbital selective mode transition.
Yeah.
Well, these spins are localized, and then you have these,
yeah.
and then they follow. Okay. Now, so this block spiral, it's kind of in between the block magnetism and then the ferromagnetism. So this I can understand. But now coming back, like the question is concerning the block magnetism. So this is established, but what's the microscopic mechanism for this? Because I don't remember how it is.
Yeah. So it is, well, Jeroen said that there's a few unused words, yes, and chirality is one thing. So there's competition between energy scales. So from one hand, from one point of view, you have a large Hund on very end because strongly, this is on very end large U physics. So if you have a large U, you have a tendency to double exchange mechanism, which is ferromagnet. On the other hand, you have still U, which is just antiferromagnet. And then if you have so this is, filling is 1.5, the system just compromises by creating this. Okay, and we see this on different doping. If we change the doping, we change the size of a block magnetism. We can have a 3 up, 3 down, 4 up, 4 down. We don't see nothing larger because it then becomes unstable numerically. Yeah. So you have two mechanisms. One is a double exchange ferromagnetism and super exchange antiferromagnetism. So that's absolutely true, but that's why I'm showing here. So max for sure. So now this is a ladder, and this is still condor, multi-orbital, whatever you want. So block magnetism, spiral, and ferromagnet is definitely here. You have more bands to fill, but if you properly fill bands, you still see this. There is obviously there is also much more phases possible here, and I want to say is that well, magnetism of iron-based superconductors is to some extent controversial topic, but nevertheless, if you look what people consider relevant, so there is this dimer phase here, so you have a 2 up, 2 down, 2 up, 2 down, which will be then, I have a toy model for that. And then this red region here is a spiral in this result. This is a classical two-dimensional J1, J2 to considerations.
Okay, more questions? Okay, please.
Thanks so much. Maybe not directly on what you studied, but because you mentioned these chiral molecules in the introduction, wondering if some similar intuition could be at work there. For instance, if maybe you already even answered it, but if the metal or a superconductor has a large spin orbit, and then the molecule has weak spin orbit, in a similar way, it would tip it one way or the other? Or?
This is one of the theories. I mean, I showed this reviews, which are somewhere here, and this is one of a possible explanation. Yeah. So in these theories here, one of these ideas is the idea that you describe it exactly. So the problem is that none of these ideas works universally, and especially discovery of these two guys, and then now there are related works which are without a substrate. This is just current through the molecule, and then they still see selectivity. Yeah.
Okay. More questions? Okay, please.
So, if in the thermodynamic limit, if you had a spin spiral, so there was really continuously rotating. Would you see it somehow in your calculations?
Okay, so I'm in a 1D, so I don't have a long range order. Yeah, so I have a finite length correlations, which is order of 7. I mean, exponential decay is like 7, 6. What I didn't show and Maria did is we especially did also cluster perturbation theory calculations just to have a small subsystems of 4 sites and then couple perturbatively. So we don't need any long range order to actually see this. Small correlations are enough.
I'm rather interested in the question whether you can see a tendency that the spins wants to be non-collinear.
Yeah, well, yeah. I don't see. I think I'm in thermodynamic limit, and I don't see any effect that this should go away. Yes.
Okay, thank you. Let's send the speaker. We should go to the next talk. So our next speaker is online. This is Andrei Varlamov, fluctuation spectroscopy from relay gene waves to abricosov vortex lattice.
Do you hear me?
Yes.
Hello everybody. Добрий день, колеги. Thank you very much for this invitation. I'm happy to be with you, at least online. Can I try to share my screen? Do you see my screen?
Yes, please just go to the full screen mode.
Yes, I will go to, yeah. Okay, is it okay now?
Oh, okay, yeah.
Okay, so today I wanted to speak about the old story which started from more or less 60 years ago from the papers of Levos Lamazov and Anatoly Larkin, Kazumi Maki, and now in view of the title of our workshop, so quantum materials, it has a new breath. So I want to speak about fluctuation spectroscopy from Rayleigh Jeans waves to Abrikosov vortex clusters. So I want to start from the statement of Gottfried Leibniz, which he wrote in New Essays in 1704. He wrote that natura non facit saltus. So natura does not make jumps. And it seems that when in 1911 Heike Kamerlingh-Onnes measured the resistance of mercury at the transition to superconducting state, so the statement of Gottfried Leibniz failed, because you see here the perfect jump. Nevertheless, if you will take a look at the modern superconductors, so for instance in titanium nitride films, so you will see the transitions not only very smeared, but before to become zero, in some samples resistance grows. So how to explain it? And the most important question, the first most evident question, what to call critical temperature. In the case of Kamerlingh-Onnes, no problem was, because the accuracy of his measurements of temperature were not very high, and the jump, and it was an evident jump around 4.16 Kelvin. What to call TC? Experimentalists usually there are different procedures, protocols to decide what is critical temperature, or half of the width of transition, or 0.1, or the derivative is maximum. So all this is subjective. So one of our tasks is to give the answer, what is a critical temperature? So I want to start to discuss superconducting fluctuations from the most habitual part, close to TC. And I don't want to write you microscopic theory. I don't want even to write you phenomenological Ginzburg-Landau theory. First of all, let's define what are fluctuations. So I will consider as fluctuations everything beyond mean field theory. So beyond BCS. So, but how to understand qualitatively what are fluctuations? So above TC, I speak without magnetic field now, electrons to form Cooper pairs is still energetically unprofitable. Nevertheless, it is possible to try. Two electrons with opposite spin can try to create correlation of superconducting type. What will be the characteristic time of such correlations? The answer gives us Heisenberg. Heisenberg says that the uncertainty in time is related to uncertainty in energy by means of the ratio h bar delta E. What I can how I can define the energy related with such superconducting fluctuation in terms of Heisenberg. What energy scales I have? Fermi energy, evidently not. This is bosonic effect. The omega d bar already enters to critical temperature. I could use Tc, but such defined correlation time would not satisfy continuity, because evidently that just below Tc, Cooper pairs will become eternal. So the only candidate what I can put in denominator is T minus Tc. Or if I will express it in terms of reduced temperature epsilon, T minus Tc over Tc close to Tc. So it will be H bar K Boltzmann minus 1 Tc minus 1 epsilon. The second question which I can ask, what is the characteristic scale, the space characteristic scale of such fluctuations? In assumption that the superconductor is dirty, so the answer gives me Einstein and Smoluchowski. They say that if two electrons started their motion at the same point with spin up, spin down, so during the correlation time tau Ginzburg-Landau, the distance between them will be Xc/BCS divided square root of epsilon. So you see that approaching Tc, the size of Cooper pairs will grow. So now I want to understand how many of such objects will be in 1 cubic centimeter of superconductor. They are bosons, so I can write Bose-Einstein distribution for them, and in assumptions that their energies, and we know that their energies are of the order of T minus Tc, from our assumption from uncertainty principle, so I can expand exponent and it will be Wien distribution, and I see that I can use as an energy of Cooper pair its binding energy. These are not binding because it is possible. So T positive T minus Tc plus the energy of kinetic energy of the motion of the center of mass, Q square over 2m, where m is some effective mass of Cooper pair. So integrating over momentum this distribution, I can find the answers for all 3 dimensions, 1, 2, 3. And I will see that actually the concentration of Cooper pairs is determined by the Ginzburg-Landau. In 1-dimensional case, it is proportional. In the 3-dimensional case, there's some constant minus 1 over xi. Very good. So let's go ahead. And now I want to compare the picture of superfluid density and the square of the order parameter averaged over fluctuations in different pictures. So in the case of the BCS, superconductivity should stop at Tc0. At Tc0. If I take into account fluctuations, so this Tc0, actually this is some formal value, moves to Tc, true Tc, which is measured by experimentalist, and I see that the square of order parameter averaged over fluctuations is different from 0 above Tc, what corresponds their presence in normal state. What is interesting that if I will compare, so the shift of critical temperature due to fluctuations already in the first order of perturbation theory is determined by the Ginzburg number, so the strength of fluctuations, Tc multiplied logarithm of 1 of Giersberg number. I speak about two-dimensional case. It is interesting to compare this with the Berezinski-Taulis-Kosterlitz transition, which is completely different from BCS. It is a vertex science. And we know that the superfluid density in the ordered state of Berezinski-Taulis-Kosterlitz suffers of the Taulis jump, which happens at the temperature of dissociations of vertex-antivertex pairs, so T-BK-T. What is beautiful, that the first approximation, so if I start from the Bardeen-Cooper-Schrieffer picture, and I take into, so I go beyond it only in the first order. I take into account possibility of Cooper pairing, and I see the shift of critical temperature, what was done by Ovchinnikov in 1973, where he did mistaken sign, but all other is correct. So I see that the difference between the renormalized by fluctuations BCS temperature coincides with BKT with the accuracy for Ginzburg numbers. So if I will develop all renormalization group, I will take into account all next orders, I should come to TBKT. So I have this coincidence from two sides. Okay, let's go ahead. So what are physical effects due to the presence of Cooper pairs? It is easy to understand. Formally, it was calculated by the diagram which you see here. It was calculated by Slomazov and Larkin, and but we will not calculate diagram until you understand that you have new channel of the charge transfer. You have, besides quasi-particles, Fermi quasi-particles, now you have some boson kinds of Cooper pairs, which move, as we know with you from Anderson and Abrikosov-Garkov theories, they do not fill impurities. So actually impurities are already in their size. So you have the ballistic motion of these Cooper pairs, new charged and carriers, and you can use just draw the formula and say that you use Cooper pairs density, which we just evaluated above, 2e as a size. What is m of Cooper pair, I do not know, but what is beautiful is that I do not need to know it. Because if you take a look at my previous transparencies, you will see that actually what I calculated is n divided m. So I do not know n, I do not know m, but I know their ratio. And then instead of scattering time, I will use Ginzburg-Landau time, which, because to be scattered or to die, it is the same. Next formation of Cooper pair will start with a zero momentum. So in this way, I can, with the accuracy to the coefficient, I can reproduce you expression for paraconductivity. Another, the same 1968, the Kazumi Maki found some enigmatic contribution, which we now understand now. It was not understood, and moreover, it was divergent. And it was Dick Thompson who proposed to cut it due to the phase breaking. And now we understand that this mechanism is nothing else as a anomalous pairing of two electrons with opposite spins at the self-intersecting trajectory. So taking the results of weak localization and recycling them for superconductivity, we can explain the physics of the Maki-Thompson contribution. But the fact, I told you that we have a new channel of charge transfer due to the new charge carriers, Cooper pairs. Where from they come? It is only God can create new electrons. So the electrons to feed Aslomazov-Larkin and Maki-Thompson are taken from the Fermi level from the one electron states. So it should be the deep in the density of states. Deep in the density of states means that you have the absence of some number of electrons and their working places for one electron through the formula. And this will give me the contribution proportional to the concentration of Cooper pairs, and it will give me in two-dimensional case log 1 over epsilon. So this contribution in the plane conductivity is less singular close to TC, but it can play important role when the Aslamazov-Larkin or Mackey-Thompson contributions are suppressed, for instance, for out-of-plane conductivity in layered superconductors. So this is important to explain the perpendicular transport in high-temperature superconductors. Very good. So we understood what happens close to TC, the summary, but what about vicinity of HC2? So what happens in the regime of quantum fluctuations when I approach the HC2 from the normal state at 0 temperature? The first, actually, when I was the postgraduate student, so Lev Aslamazov gave this problem to his another PhD student, and he failed. So it was too early in 1979 to explain this. Actually, it was done 20 years later by Galitsky and Larkin, who proposed how to describe quantum fluctuations above HC2 and the example of conductivity and diamagnetism. The problem is that the corrections were found only logarithmically dependent, so they're not so demonstrated, observed as close to TC, because Aslamazov-Larkin, the characteristic feature of Aslamazov-Larkin and Mackey-Thompson, that they were very strongly dependent on temperature. Here, corrections only logarithmic. It is not so easy to separate them from other corrections and to observe. How qualitatively discuss what happens close to HC2? I will repeat the same story appealing to Heisenberg. What is a characteristic time of quantum fluctuations? H bar divided some energy characteristic for quantum fluctuations. I understand that this value should turn 0 when magnetic field approach HC2. The only candidate is a difference in Larmor frequencies at the current magnetic field H above HC2 minus Larmor frequency at HC2. So it is, if I will substitute corresponding values, so characteristic energy is delta BCS multiplied reduced magnetic field H minus HC2 divided HC2. So 2 tau quantum fluctuations will be H bar delta BCS minus 1 divided H bar. Please compare it with what I had above TC. It was H bar TC minus 1 divided reduced temperature. So all is very similar, but here, so if above TC, I had the Rayleigh-Jeans picture of long waves with wavelengths larger than CBCS by parameter. Now, and tau is Ginzburg-Landau, some long times. Here, I notice that H bar delta BCS minus 1 is nothing else as a period of rotation of Cooper pair in abrikosa vertex. So if I'm a little bit above HC2, so if it is niobium, I have 2002 Gauss. I have something, and below I will have 1998, I will have abrikosa vertex structure with rotation delta minus 1. I see that here the characteristic time is much larger than rotation, much larger by parameter 1 divided H minus HC2 divided HC2. So this means that some fluctuation correlations exist much more than one rotation. So how I should imagine this picture? I should imagine that if above HC2 at 0 temperature appears superconducting fluctuation, Cooper pair immediately start to rotate as a future image of vertex. But this is not enough because this rotation period is much smaller than superconducting correlation. So actually, I can imagine that superconducting picture is the following. I have the clusters of abrikosa vertex closer to HC2, larger this, their size Q quantum fluctuation. Again, I can evaluate from Einstein-Smoluchowski, and it will be BCS, so size of vertex, divided square root of small parameter. So I will have these clusters, but if I would to take a picture, it would be difficult because the characteristic times are very short. They are tau quantum fluctuations. So if I would have some camera with very short exposition time, so putting exposition time shorter than tau quantum fluctuations, I would see the picture of these vertices. If longer, all will be smeared out. So I propose this scenario. So coming back to Gottfried Leibniz, I say that abrikosov lattice is formed already in normal state, but in the form of such clusters. And then closer to HC2, longer lifetime of these clusters, larger their size, and when we cross HC2, we obtain the stable abrikosov vertex. Very good. So what is our extended phase diagram of superconductor? It is the Meissner state, abrikosov lattice, vertex liquid, and then from above, this is a it is some set of vertex clusters. Here, the Ginzburg-Landau-Rayleigh-Jeans wave, the thermal fluctuations. Then the line, which is a mirror reflection of HC2 close to TC0. It divides the phase diagram for here the Ginzburg-Landau length becomes of the size of magnetic length, and we pass to the crossover region where Cooper pairs are broken in vertices. So this is a phase diagram. How to observe this? So formally, so I will pass in 2 minutes. So how to calculate conductivity? It is necessary to calculate these 10 diagrams, which is a little bit annoying. It requires couple of, let's say 1 year. And then you will get this answer, which you can produce three-dimensional pictures. You can see that fluctuations, if their contribution to conductivity was positive above TC, above HC2, it is negative, but only logarithmic, difficult to see. So what we proposed, it is just accepted to PRL, we proposed to study, to visualize this abrikosov, the formation of abrikosov lattice in the by their microwave signature or the emergence of abrikosov lattice. So we calculate. I want to recall you what happens in impure metal. You have just drew the theory, so you see that real part changes only when omega tau is of the one, when is formed imaginary part of conductivity. In superconductor, there is a old Abrikosov-Garikov-Khalatnikov theory, where you see that at 0 temperature up to delta nothing happens, then imaginary part is formed. We calculated all these 10 diagrams. At low temperatures, you cannot put it 0. So low temperatures, non-zero omega and non-zero magnetic field. So the answer is that all 6 diagrams of DOS type are cancelled out. The contribution of Aslamazov-Larkin at T0 is infinitesimally small. It is H minus HC2 divided. So it is X log X. So you can forget about this. The main contribution appears due to Mackey-Thompson contribution. And in zero frequency, it gives already promised -6 log hc2 divided IH minus hc2. So it is hardly observable. What is non-trivial that in imaginary part, so if you will measure impedance in some resonator, so you will have contribution which is singular, it is proportional to hc2 divided h minus c2. So it will give you, you see the growth of imaginary part of conductivity. In what is important, in the scale much smaller than it is foreseen from the mean field theory. In the Abrikosov, Garkov, Khalatnikov, it should happen at 2 delta. And you see that we have maximum around 0.01 delta. And this contribution you see at this, the right panel is singular as a function of magnetic field. Okay, if you approach magnetic field. And
you have 5 minutes.
Yes, I'm finished. Yes. So I just want to give you some main takeaway messages. So fluctuoscopy generally allows us to define critical temperature just as a fitting parameter of the theory, so not by hands. Then you can use it, for instance, very recent experiments of Geneva group where they studied the electric field control of fluctuations in two-dimensional superconductors. So you can extract how critical temperature depends on electric field. The fluctuation theory was extremely useful to explain the enigmas, all the enigmas of quarter of century about the giant Nernst effect in cuprates, where it was attributed to some pseudo vertices, something by Ong. Actually, the enigma was resolved by the Kamran Benya and his group in 2006, where they demonstrated this giant Nernst signal was 2,000 times more than background in the normal superconductor with critical temperature 0.38. And finally, we have succeeded with Glatz and Pourret to explain completely behavior of these complicated curves, predicting the behavior of maximum as a function of the temperature and magnetic field. That's all. So if someone interested, he can find in our review of moderns review the fluctuations, more or less what I told. And finally, I wanted just to tell some idea that when you, let's speak about quantum fluctuation regime. So you are in normal metal, the Fermi physics, and Cooper pairs give you some the nucleus of superconductivity. Then when you cross HC2, you become in superconducting state, and vertices are the nucleus of normal phase. So if you cross HC2, you have some duality. You I don't know how to say it in English. Выворачиваете наизнанку свою рубаху. So I want to attract attention to this beautiful duality. Thank you very much for your patience.
Let's end the speaker. Please, questions? Okay.
Hi, Andrei. Sasha speaking. I just wanted to understand your opinion. So it is, from my point of view, such a phenomenological approach that you put the mechanism, let's say, and the issue on the dimensionality in Ginzburg parameter. Yes, and but for example, practically speaking, I wanted to ask, let's say, this anomalous Ernst effect, large Ernst effect, that was for LCO, right? And LCO, it is quasi two-dimensional, but it is rather also three-dimensional. Three-dimensionality is very high comparing, for example, to BISCO. And then it would be expected that for BISCO, this fluctuation should be much higher. Could you derive some understanding how it depends on this dimensionality, let's say KZ hopping, so hopping in terms of anisotropy or something like this?
Yes, of course. Ginzburg number is actually the parameter which depends strongly on dimensionality. And I can give you the formula for any dimensionality. So, for instance, the most interesting is two-dimensional. In two-dimensional, it is 1 over P Fermi square LD, where D is the thickness of your film, L is the mean free path. So in two-dimensional superconducting films, it can be 0.01. And actually, Ginzburg number says you how close you can approach transition remaining in the Gaussian approximation. Then fluctuations start to interact, and you have described them by some kind of renormalization theory. Then returning to Nernst, I want to clear up two things. We know from the times of 1975, when people started to study niobium selen 2, then some intercalated systems, two-dimensional, that the tails in diamagnetic susceptibility were 30 times more than TC, were observable. In conductivity, it was only percents. Why? Because it is necessary to understand that diamagnetism and Nernst, they are parents, they are relatives. And with what you compare? The Nernst effect in normal metal is small by parameter temperature divided Fermi energy. So it is very small, like the Langevin, Landau, or Pauli diamagnetism. It is 10⁻⁵. At the same time, in superconducting state, you have for diamagnetic susceptibility -1 over 4 pi, so 10⁻⁻⁻. So actually system already far away from TC feels that the diamagnetism must grow. This is not the same with conductivity, because conductivity you speak about resistance, and resistance is finite. So the smearing of transition is much more straight. I don't know, did I answer your question or not?
I think it's a lot of here to discuss, so I could not say that I understand everything you say now. So, but okay.
No, I just want to say that it is necessary to distinguish two classes of phenomena: conductivity, sound attenuation, the Josephson current, etc., etc. It is one class. Another two are Nernst and diamagnetism. They are relatives. You cannot calculate Nernst without diamagnetism. It is necessary to take into account the diamagnetic currents. And these two phenomena are much more sensitive for fluctuations. They show up fluctuation corrections far from critical temperature.
Okay, thank you. Yeah.
Maybe
we can discuss it.
I've noticed the question online. Andrii Terekhov, please.
Yes, thank you. Thank you. Firstly, thank you very much for a very interesting talk, in my opinion. And I have questions that is interesting for me. What is your opinion on the mechanism of the pseudo gap observed in Kuprats? Do you believe that its origin is superconducting? Thank you.
Very good question. Very good question. This year, we celebrate 40 years of the discovery of high temperature superconductivity. And I think that it is a question of belief. So here, are present many experts in superconductivity, and if we will start now to discuss, you ask a very profound question, but I can make it even more profound, namely, what is the mechanism of superconductivity? And 20 years ago, we with Toля Larkin in our monograph devoted 17th chapter to the possible mechanism of high temperature superconductivity. Of course, no one now speaks about 5-dimensional Ginzburg-Landau, including three projects of momentum and 2 gap parameters, etc. Nevertheless, we still do not know. We know that in hydrates, this is phononic. If you ask my belief, so it is a question of belief. There is a Christianism and Islam, etc. So I more believe in some kind of BCS. So definitely Cooper pairs exist. What is the glue for them? I believe that antiferromagnetic exchange. So following ideas more or less of Pines and Andrei Chubukov. But this is a belief. So actually we are in some the theory is in depth, I would say. We do not know. And coming back to your question, for me, 25 years ago, I would answer you in my belief. I would say the pseudo gap can be explained by fluctuation origin. And we have the review about this. Indeed, I showed what happens at the level of the Fermi level I showed in one of my slides. But I did not have time to discuss how this suppression of density of states on the Fermi level, so density of states as a function of energy, it is very small, T minus Tc, or square root of T minus Tc, Tc for clean systems. But you cannot measure it. You can measure tunneling gap. And the sum rule says me that we cannot create new states. So the deep in it is compensed by maximum. And this sum rule results that when you calculate the fluctuation current, you will have very large pseudo gap. You will see gap, and this gap is determined as pi multiplied Tc. So having Tc 100, you will have gap the tens of milli-electron volts. So, but this is very local. I can say that I don't pretend that this is true, but one of possible mechanisms that is fluctuation, because they become very strong. Nevertheless, I can tell you another 5 explanations. I don't know.
Okay.
We are out of time, so one brief question, please.
Oh, thank you very much for your talk. And I'm afraid I don't have a quick question, but it relates to what Sasha was asking before, the role of dimensionality. So you can. My question is that there's an explicit thickness dependence in the experiment. The thickness of the samples is obviously scaling the R and the TC. And can that be understood, this thickness dependence, in some way?
Yes, exactly. Actually, this is so evident question which you ask, but for me, it was not evident 40 years. Actually, this question was asked by Kamran Benya. Maybe we discussed it 1 month ago in Paris, because indeed, experimentalist has some the film of the thickness D. If I'm close to Tc, so I can say that system will be 2-dimensional when Ginzburg-Landau length is much more than thickness of film. Then I change something, or magnetic field, and I break Cooper pairs, I force them to rotate, or I go far from Tc and their size decreases. So the question is my sample 2-dimensional or 3-dimensional is extremely important. It depends how close I am to Tc. And I just, of course, it is possible to do. How to do? we do not suppose that fluctuations are two-dimensional. I just quantize motion of Cooper pairs in the perpendicular direction. So it is necessary to take into account three-dimensional summation, but nevertheless summation, not integration, to sum over the standing waves. It is possible to do. We are doing this now for observations of Nernst in strong magnetic fields. And what I told the last about this duality between above HC2 and below HC2, I mean HC2 of T. This duality, I hope we will be able to explain, taking into account this quasi three-dimensionality. So
thank you very much. Thank you for the answer.
Yes. Okay, so let's send the speaker. So thank you, but we should go to the the next talk.
And so, for me, it is a great pleasure to see. Be happy to be in Lviv.
Yuliia Gusieva, field controlled thermal spin transport in radial type altermagnets. You have 15 minutes, so I will show you in 3 minutes. And are you trying to connect your notebook or? Okay, fine.
Okay. Hello, everyone, again. My name is Julia, and I'm glad to be here today. I had the opportunity to take a part in a workshop last year in Kyiv, like a guest, only participant listener, and it was a lucky event for me because I found new colleagues there, and now I have opportunity to present our results here. Yeah. The topic of our research is field-controlled thermal spin transport in radial type altermagnets, and I want to emphasize that we talk about magnon transport. I show you the effect of the generation of spin current carried by magnons. Okay. And this work was done in collaboration with Konstantin Yashov and Vladimir Kravchuk within a framework of the project GUCAMAT. And first, I want to explain your effect that we considered as a generation of spin current carried by magnons can generate by applied temperature gradient to the material. And we focus on two works, one of them about easy access D-wave altermagnet, where magnon spin current is generated by an applied temperature gradient in radial type altermagnet. And the other hand, another work about easy plane G-wave altermagnet. And this system, it's interesting result about magnetic moment induced by altermagnetism. It's interesting because compared with antiferromagnet, magnon magnetic moments doesn't induced. And but in this structure for G-wave altermagnet, no magnon spin transport occurs. That's why we decide to combine two ideas. We focus on easy plane D-wave altermagnets, and we check what about our effects about the generation spin current using applied temperature gradient. On Monday, Vladimir Kravchuk explained about how we model the alta-magnet contribution to theoretical calculation. We compared two diagonal. Now we focus on a 3D model, and if we compare two diagonal between two magnetic element, we have two fluoride, two non-magnetic element along the diagonal, but in another diagonal, the non-magnetic element are absent, and we have the rotation situation in next sublattice, and this effect we modulate using the alto-magnet indirect exchange interaction. We considered 2D model, only upper and middle layer, and we neglect the distance between these sublattice. We illustrate the octahedral blue and yellow. It's surrounding, non-magnetic surrounding, and blue and yellow sphere is nickel, but for two different sublattice. We include to consider ferromagnetic exchange interaction, antiferromagnetic exchange interaction, and our new contribution of altomagnetism. And additional, we include to consider the external magnetic field, and of course, in this situation, for easy planar, we have Kantian effect. It means the spins tilted slightly to the our external magnetic field. Okay. The Hamiltonian consists of 5 terms. It's antiferromagnetic Hamiltonian, our contribution of altomagnetism. Ferromagnetic Hamiltonian, we considered easy plane anisotropy. That's why we have Hamilton of anisotropy, and Zeeman energy, because we add to consider the external magnetic field. Okay, let's explain the mathematical approach that we use. We start with infinite set of Landau-Lifshitz equation formulated for each spins. Next, we use the classic analog of Holstein-Primakov representation, in which accretion and annihilation operators are replaced by complex valued function psi, and its function encodes the deviation of magnetic moments in respect with equilibrium position, equilibrium orientation, and then we linearize our equations of psi, apply to Fourier transformation, and our equations of motions are reformulated in form by equation Schrödinger equation, where psi is 4-component spinor, and using these equations we obtain the dispersion law. On the central slide you can see the 3D plot of dispersion relation, and panel A is constant energy cross section, and we can see that the specialization the spectrum consists of two branches, blue and yellow, and on panel C we take cut along the symmetry line, green line in our picture. We have a Magnon gap in the spectrum, and we estimated the gap, and it depends on anisotropic constant and the external magnetic field. And in our spectrum, we have one gapless goldstone mode. It's a blue line in our plot. Okay. Next, we calculate the Magnon magnetic moments and the complicated analytical expression is to demonstrate only to emphasize that Magnon magnetic moments depends on altomagnet parameter. The var epsilon is dimensionless altomagnet parameter. That's why if we don't have altomagnet, our Magnon magnetic moments equal to 0. And bottom, we illustrate 3D plot for Magnon magnetic moments for two branch of spectrum. And the Magnon magnetic moments for different branch has opposite side. On panel C, it's again the is an energy plot where we add the value of Magnon magnetic moment using the color scheme. Okay, we're using the Boltzmann transport equation in time relaxation approximation and found the spin current which appears in response to applied temperature gradient. Sigma is thermal spin conductivity tensor. C factor is capacity of magnetic moment per Magnon. And for choosing reference frame, our spin conductivity tensor have only non-diagonal components. We analyze the temperature dependence of spin conductivity for different value of the external magnetic fields. B is dimensionless field in the unit of spin flip field. And interesting effect that the spin conductivity.
You have 3 minutes.
Okay, thank you. Can be positive as well as negative. It depends on external magnetic field. And this effect I demonstrate in my animation. The relative orientation of the temperature gradient and spin current can be different, and it depends on the direction of temperature gradient relative to crystallographic axis. Okay. Also, we analyze different temperature behavior for low temperature. The dependence of spin conductivity is quadratic temperature dependence, and you can see this on slide. For low temperature, the curve has a parabolic segment, and for a high temperature, at high temperature, we have the curve becomes plateau, and the spin conductivity becomes temperature independent. And we, additional to analyze the situation for high temperature, we built a map of spin thermal conductivity as function of the magnetic field and anisotropic coefficient. Green line on the map, it's zero conductivity, and if we increase in altomagnetic parameter, this line shifts significantly, and as it's effective method to control the change as a reversal sign of spin as a direction of spin current. And then I want to make conclusions. The primary outline is existence of non-magnetic moments induced in this structure, and the applied temperature gradient generates a spin current in radial D-wave altomagnet, and additional conclusions, it's in system with the symmetry external magnetic fields can effective control the sign of thermal spin conductivity. That's all. Thank you.
Thank you. Let's send the speaker. Okay, please, questions? Okay. Online. Okay, then if not, so let's send again. Our next speaker is Francesca Buccieri, plasmon-driven nodal surface superconductivity of Fermi arcs, and you have 30 minutes. So I will stay in 5 minutes.
Thank you. Thank you very much. It's a pleasure to be here and to get to know some of you and this beautiful city, and it's an honor to give a talk in front of this audience. So I will talk about phonon-driven nodal surface superconductivity of Fermi arcs. Let me first thank my collaborators, Alessandro De Martino from City St. George University and Jeroen van den Brink from the IFW. So this is more or less the outline of my talk. I will first recap some facts about surface superconductivity in trigonal platinum bismuth 2. You have already heard 3 talks in this workshop by Sergey Borisenko, by Christian Melan, and by Oksana Kvitnytska. Sorry. So I'll just say a few basic facts. I will try to understand how general is this nodal superconductivity that has been detected in the recent year. In particular, I will propose a model based on electron phonons, Coulomb interactions, and their interplay. So, sorry, this is too far ahead. Yeah, okay, so these are the few things I will need for this talk. The trigonal platinum bismuth 2 is, as you can see, a layer material. The symmetries I will be using is this point C3V symmetry. So rotations around an axis and some reflections about symmetry planes. unless you break it, it has time reversal, but importantly, it lacks a point inversion center. So this allows the creation of 12 band touching points, which are non-degenerate and are very close to the Fermi energy to be relevant at low temperature. These are dubbed Weil nodes and define the topological properties, define this as a Weil semimetal. In recent years, it has been argued, as you know, that that superconductivity mainly develops on the surface of this material, and in particular, that it has been argued that the surface order parameter as I wave characters, Cooper pair, have L equals 6 orbital angular momentum. Now, this is remarkable for various reasons. That the surface superconductivity appears to be particularly robust. Let me put on the screen here the values from a Beijing-based collaboration. So as you can see, both with respect to the critical temperature and with the critical field. Now, this surface superconductivity appears to be connected with the topological surface states, the Fermi arcs, which connect the projection of the Weil nodes onto the surface Brillouin zone. So there is an interplay of various dimensions here, because your Fermi arcs are one-dimensional manifolds. They live on a two-dimensional surface, but they're actually there because of the three-dimensional bulk topology. Now, the material itself is interesting. An interesting playground for applied physicists. There's a spin-orbit coupling, so you can think to manipulating currents, spin and charge currents. It can realize in principle a Josephson junction without even needing an actual junction by using the two surfaces of the same material. And the two-dimensional superconductivity allows, in principle, an easy integration in two-dimensional circuits. So it has attracted some attention in the last years. Also from the theorists, because as we have learned on Monday, Majorana bands are localized on the surface, which might be of use for topological quantum computation. What I will be concerned about in this talk is the unconventional nature of the gap structure. Now, the bulk, so the fact that a topological semimetal can show a more robust surface superconductivity does not come as a surprise, and it's due to mainly to density of states consideration. So in an ideal Weil semimetal, you have a vanishingly small density of states in the bulk. So what is left for you to create Cooper pairs comes from the topological surface state. So nodal line semimetals and Weil semimetals may indeed develop surface superconductivity when the chemical potential is close to the Weil node. From an experimental point of view, this phenomenon is rather established. There are at least, to my knowledge, 3 groups which have detected surface superconductivity, the Peking-based that I was mentioning, Madrid probably, and the IFW who has played a big part in this business. I'll focus on this picture that Sergey Borisenko showed you on Monday. These are his ARPES data. And in particular, they exhibit the traces of the Fermi arc density of states, which are in good agreement with the prediction from theory. And this is the black dots are the leading edge gap. They are a proxy for the superconducting gap. I will treat it as the superconducting gap for this explanation. So it has a very peculiar structure. In particular, it has pronounced maxima, which are close to the ends of the arc. And it has a minimum, a zero actually, as we learned, at the center of the arc. Now, it is reasonable looking at this to ask what is the mechanism that is behind this behavior. In particular, because a famous nodal superconductor like cuprates, heavy fermion, and iron-based superconductors are not well described by BCS theory, and the mechanism is something else. Yes, so I've mentioned already the high wave symmetry of the order parameter, argue on symmetry considerations. And Christian has proposed us a phonon-based mechanism for the emergence of superconductivity. And there's also a recent preprint which proposes a purely Coulomb-based mechanism for the emergence of such structure. Okay, so I'll try to look at this from a more general perspective and write down a minimal model of inversion symmetry broken Weyl semi-metal. So this is a very simplified Hamiltonian. As you can see, it is written in terms of two bands, which are in general a mixture of spin and orbit degrees of freedom. It has a downgraded version of the C3V symmetry that I've told you before. It possesses time reversal, but there is no way in which you can enforce inversion symmetry here. In the bulk, it has 4 Weyl nodes, and let's see what happens on the surface. So the most general boundary condition that one can impose for ensuring that this is an Hermitian Hamiltonian are written in terms of this matrix, which contains a free parameter. You can see it's a combination of Pauli matrices acting on the spinor on the surface. What you find are surface localized states, are exponentially localized on the surface. They have a purely two-dimensional dispersion, and they have a penetration length which varies along the arc. Crucially, the penetration diverges with the distance in K-space from the end of the arc. So when they merge with the projection of the bulk Fermi surface, basically the Fermi arc become surface state. So this makes it clear why they call the arc. This is a equal energy projection. Yeah. Okay, let's couple them to phonos. Now for our analysis, we use a three-dimensional elastic continuum, the way you can find in the Landau books. It's well-established description of acoustic phonos. Basically, lattice sites are displaced by a displacement vector u, which becomes a field in the continuum limit. The dynamics of this field is governed by this action. It contains some parameters of the material, like its mass density and 2 Lamé parameters in the simplest approximation of isotropic and homogeneous continuum. These parameters enters in the phonon velocities, which will be inserted in our model based on some experimental determination. There appears in this object the linearized strain tensor, which is written like this in terms of the displacement. Basically, the diagonal components tell you how the distance are varying along the sample, so how much it's stretched. The off-diagonal components are telling you how the angles vary, so how much it is deformed. When you impose that there is a free boundary, or stress-free boundary conditions, if you want, you find some phonon modes. Sorry if I flash you these big formulas. I just want to highlight the non-zero component and more or less their structure. The details are not essential here. So the first component is along the wave vector of the phonon modes, which is oriented on the surface. The second component is on the surface but perpendicular to it. And the third component is along the z direction. So you see the first two are basically mixing your longitudinal and transverse wave at the surface, or principal and secondary wave. So these are really bulk modes. There is even another third bulk modes. There is an oscillation along Z here, which I have not written. Yeah, okay. Yes, it looks like this. So they oscillate in the bulk, and that's why they carry a factor 1 over the transverse size of our slab. Now this L is inserted as a regulator for us, and it will be sent to infinity at the end. There's another special mode which is localized on the surface. You see that there appear exponentials. And for low frequencies, this is the only surviving mode. It only moves on the surface. It's called a Rayleigh wave. Now, the next step is to couple electrons and phonons. In order to do this, we take a step back and we follow basically the chapter 2 of Mehan and define a lattice model, and which is basically a tool to reproduce the continuum Hamiltonian that I've written before. And assume that the hopping parameters that appear here depend on the distance of the lattice sites. Of course, this will introduce you a coupling between the deformation, the displacement field, sorry, and the electronic density in the end. Long story short, so through this term, expanding at the lowest order. Long story short, when arrived at an electron-phonon interaction of this form, you see a surface electron is scattered from a momentum k to momentum k plus q, either by absorption of a phonon or emission of a phonon with opposite momentum. These are complex objects. They involve the wave functions of the initial and final states, as well as the shape of the phonon which is mediating the interaction, which is involved in the interaction, which is this lambda species here. Okay, next step from electron-phonon interaction to electron-electron interaction. This we do by Schriefel-Wolff. We need somehow the Coulomb interaction to cut off the procedure at small momentum, but in the end we arrive at an effective phonon-mediated interaction of this form in the Cooper channel. So this is our simple model with this interaction potential containing both the Coulomb interaction between the Fermi arcs, I will come back on this, and the phonon-mediated attractive interaction, which is a sum over all the various contributions. Okay, so let's look at the possible processes that you can have. The rule here is to conserve momentum, and let's take a cut at the Fermi energy. So our Fermi surface is bipartite. It's composed by these two arcs, And the possible processes that we need to take into account are scattering in which the initial and final we are scattering time reverse pairs, and the final state can be on the same arc in which the electron has started, or the two electrons can exchange arc. So I call those intra-arc and inter-arc processes. Okay, so this is the phonon-mediated effective interaction that arises from this analysis. And you already can see that it inherits the shape of the Fermi arc, roughly. This is indeed maximal close to the end of the arc and is minimal around the center. That holds both for intra and inter-arc potential. And then there is a funny fact, maybe unexpected, that the surface phonons, which in principle have the largest overlap with initial and final states, are actually the ones that contribute less. And the reason is based on the density of state consideration, essentially. When our slab goes to infinity, the number of bark phonons also grows with the slab. And you have an integration over an additional phase-space integration over the frequencies, which makes this contribution dominant, even if the single matrix elements are smaller. Now, our model takes as input parameters something that you need to measure independently, but luckily in literature we could find Weil-Nodde separation, the bifrequency, and an estimate for the phonon velocity. Okay, well, we have our attractive potential. Let's basically let's crank the BCS wheel. This is the number spinner that one can define. As you can see, there appear explicitly an index describing the arc. So plus is for the top arc, minus is for the minus arc. And of course, this Hamiltonian is there to reproduce the two types of processes that I've shown you before. That's the typical BDG form. And when you diagonalize, you obtain this gap equation. There is actually an additional integration over the energy that I'm not showing. So that's for compactness. There is something interesting here, and in particular this sign. Intra-arc processes enter with the usual BCS sign. Inter-arc processes have the opposite sign in front, and this is due basically to the fermionic statistics. Even more interesting, the solutions associated to these two equations have a different parity along KZ. So the momentum, the effective potential depends only on the exchange momentum. So the parity along the arc is a good, so we can expand in eigenfunctions which have a definite parity for inversion of KZ. And in particular, the intra-arc solutions produce you even parity, and the inter-arc solution produce you odd parity gaps. Okay, why is this? Well, let's look at the linearized BCF gap equation. This is still textbook physics. So this is basically an eigenvalue equation in which this, if you think to discretize the KZ between the KX, K prime X along the arc, this is a matrix multiplication of your gap, which is now a vector evaluated at various K prime points. So basically, you are looking for an eigenvector of this matrix, but minus something attractive is a positive matrix, and in this case, the Perron-Frobenius theorem tells you that you have a unique leading eigenvalue and that you have an even solution. So this would be the corresponding eigenvalue condition. Here, minus V intra is a positive quantity. This will not work for interarc pairing. In general, the parity of interarc gap, let's call it pi, which can be positive or negative. And the eigenvalue condition becomes this one. So you can see that the product of the eigenvalue, the largest eigenvalue, and in absolute value, and the parity must be positive. So one has to rely, so the Perron-Frobenius eigenvalue does not satisfy this condition. So one looks at the following one. So one way of seeing which one is the dominant is to consider only vertical transition. And then your gap equation becomes an algebraic equation which only has odd solutions. Or you can numerically check which one is the next leading eigenvalue. And it turns out that it's indeed the one with the odd solution. Okay, next player here, and this the last ingredient is the Coulomb interaction. So we compute within our simple model the Coulomb interaction between electrons in Fermi arc states. It has the form of a typical two-dimensional potential, but with a form factor which describes you basically the varying penetration of the arc, of the Fermi arc in the bulk. So it contains the integration along Z if you want. We also add to take into account the complicated electrostatic environment, a screening Thomas Fermi wave vector, which cuts off the divergence. This is a rough way and possibly oversimplified, but to take into account all the screening coming from the bulk, from the other Fermi arcs, the other electrons on the surface, and possibly from a substrate.
You have 5 minutes.
Yes, that's my last thing. So you can see the role is when the screening is inefficient, the intra-arc potential quickly becomes from attractive to repulsive on average, while the inter-arc potential, since it involves large momentum transfer, is mostly unaffected by the divergence at small q of the Coulomb interaction. This reflects also in the critical temperatures, and so these are some results for varying bare electron-phonon interaction. The continuous line are the intra-arc critical temperature, and the dashed line are the inter-arc critical temperature. You can see that the last are mostly unaffected, but when moving the screening wave vector to 0, the intra-arc critical temperature quickly drops to 0. So to summarize, we have studied the interactions on Fermi arcs in this very simplified model. In the end, the three-dimensional nature of both the phononic bath and the Fermi arcs plays an essential role. We have proposed indeed a mechanism for the development of intrinsic arc superconductivity and the formation of the nodes. The ingredients are disconnected surface Fermi surface, a phononic glue, and the presence of weakly screened Coulomb interaction. Thank you for your attention.
Send the speaker. Okay, please, questions? Okay, okay, please.
Probably it's a very naive question, but that slide with the Coulomb interaction terms and potential, how is it related to the Kohn-Luttinger mechanism? How is it related to the Kohn-Luttinger mechanism?
No, I don't think one can see a Kohn-Luttinger mechanism here.
Not related. So
yes, not from here. This is a low momentum expansion. You would need a bit more. Yes, so I don't think I can get.
Thank you.
Sorry.
Any more questions? Okay, if not, let's. Oh, okay.
So comparing this intra-arcs and inter-arcs transitions, pairing, right? So in inter-arcs, could you, so you can consider these transitions between, let's say, plus and plus minus? And this gives you what?
In principle, it's the leading eigenvalue that dominates. But we did not study in detail the transition between these two.
I mean, could you just explain why it is one is odd, another is even?
Okay. Yes. So basically, these are eigenvalue equations. At the linearized BCF gap equation, you can think them as eigenvalues equation. So think to this as a sum over K prime X, which is the momentum along the arc.
But it is taken into account. So you consider this node in the center of this arc, right?
Yes. Here there is
and sign change.
So Sasha, so maybe you can say, if I may give your answer again. So the intra-arc has to be even because of the form, the mathematical form of this equation. The inter-arc can be even or odd.
Yeah.
And now you do either, you can, the numerics, and you find the odd one to be the lowest one, or even in some approximation on the scattering, if you say that the scattering occurs at only certain points, then you also find that's the odd one.
Yes.
So in principle, it could be both, but it turns out to be the one with the node.
I see two questions online, so please, Eduard Gorber.
Yes, thank you very much for very nice talk. I have a simple question. It is known that Fermi arcs could support Weil orbits for sufficiently thin specimen. Have you looked at? Did you look at dependence of experimentally on observed superconductivity for sufficiently thin specimen?
Okay, I'm not sure I've understood the whole question because I cannot hear very well. But so you were mentioning the Weil orbits, I think, in thin. Basically,
right.
the coherent.
Right. Coherent orbits on both top and bottom layers, right? And going through the bulk. Yeah.
Yes. So the natural question is to say, like, could phonon-mediated interaction scatter electrons from one side to the other?
My question is, have you looked what happened if specimens are sufficiently thin? Then we have strong intra-surface interaction. So Fermi arcs could hybridize.
Yes. Okay, there it's a whole. I think it's a bit of a different problem, no? Because you have the direct hybridization of the two surfaces, either through this conveyor belt, so this chiral null level in the bulk, or if it's very thin, directly between the fermionic states. The honest answer is I don't know what happens in the very thin slab limit. It's definitely something that we can study, because I mean, with this kind of model, it's within reach, and it's probably interesting to see exactly where and if superconductivity breaks down, even taking into account the hybridization between surfaces.
Yeah, thank you very much. Yeah.
Thank you very much.
Okay, please, Pavlo Sukhachov.
Yes, thank you for a very interesting talk. I have a simple question. So, have you considered the role of disorder on this type of superconductivity? It looks like one component should be strongly suppressed and the other is not, because you do have coupling between different lines.
Yeah, true. It's a legitimate question. The effect of the disorder should be probably the same at the level of the Fermi arcs. So you know that there is some degree of protection, so the Fermi arcs will stay there. But then the details will probably might change. Yeah, so in this model there is no disorder, as you can see, and I still don't have a clear understanding of its role.
Okay, thank you.
Okay. Well, I have questions I will probably ask already outside. So let's send the speaker again. And we meet in half an hour at 4:30.
Maybe we start. This is the last session of the workshop, and the first speaker is Andrij Shvaika from Lviv. Please.
Okay, thank you, Mr. Chairman. I am here from Lviv, from the Yukhnovsky Institute for Condensed Matter Physics, and I hope that you enjoy staying here in my own city. So my talk will be devoted to the development of the theory for the time-resolved spectroscopy. So there is an outline of my talk. So first I give you some ideas what Raman spectroscopy is, what is the time-resolved pump spectroscopy. Then I shall give you some introduction into the theory of such effects. It is the field which is now only developed. Next, I shall provide some dynamical mean field theory solutions for the time-resolved photoelectron spectra and for the time-resolved Raman spectra in the very simple Falco-Kimball model, but this model allows to find some exact results, and at the end there will be some conclusions. So I think that there are no need to explain how important are different optical and scattering experiments in the investigation of the condensed matter, because by tuning of the energy of photons, sorry, where is my mouse? I do not see my mouse. I see. So by tuning of the energy of photons, for example, you can examine different kind of excitations in the condensed matter, starting from the phonons, magnons, different charge transfer excitations, and many others. So this is the scale of the different energies and wavelengths. And what we are interested in are the effects connected with the inelastic light scattering. This is effect also known as the Raman scattering. And by different geometries and by different energy scales, you can you can measure either lattice phonons as different magnon excitations, charge exchange excitations, but also there is a such background connected with electronic continuum, and this background will be the focus of my talk. Why it is important? Because it was the first where it was just in the experiments of the Raman scattering on the electron excitations when there was first observed the superconducting gap in the high TCs, and also it was first shown that it is of the D-type symmetry. There are many limitations for such kind of experiments, and some of the, first of all, this is the intensity of our photon beams. So, and the last decades, there were established many different facilities. First of all, this synchrotron light sources, but also there are lasers on the free electrons, which allows to obtain to generate powerful beams of the photons and control these beams in a different way. And here you have a map which shows at which countries, how many there are facilities. And I know that many universities in the United States, in the Europe, in Japan, they just constructed their own lasers on the free electrons, and these experiments are increasing in the amount. Also, last decades, there were a big progress in the development of the techniques for manipulating and controlling of these photonic beams, which allows to obtain short pulses of photons of different energies. And such achievements were subject of the Nobel Prizes for the 2018 for the ultra-short optical pulses, and also in the 2023, there was the Nobel Prize was awarded for the obtaining of the pulses of the attosecond time scale. Why it is important? Because by using such short pulses, you can investigate dynamics of the different time scales, starting from the molecular vibrations up to the chemical reactions, and now this attosecond time scale allows to measure directly and electronic excitations in the different materials. But so there were a lot of different experiments, and here I provide, sorry, there should be movie, but it doesn't work. Yeah, so the main, as a rule, such experiments are conducted in the so-called time pump probe setup. So that when first your sample was excited by some high energy pulse, and then the second pulse provide a probe which allows to measure different properties. This picture shows you the photoelectron emission spectrum, but also other kinds of probes can be used. And here I also provide you some results. It is very old results, but they are very representative of how the energy spectrum is changed in a Brillouin zone with before and after the pump. What is also interesting with these experiments is that by conducting different kind of experiments, you can investigate thermalization of the different subsystems and different charges in different types of excitations in the condensed matter. And here I provide the results from the 2017, when these were results for the graphite, and they use time-resolved photoelectron spectroscopy, ARPAS, and also time-resolved Raman scattering on the phonons to investigate this graphite. And what they find, so they investigate the changes and evolution of the spectrum, but also they estimate effective temperatures of the electron subsystem, of the phonon subsystem. The temperature for the electron subsystem was calculated from the slope of the spectral density at the Fermi level, and effective temperature for the phonons was obtained from the ratio of the Stokes anti-Stokes line in the Raman spectrum. And here you see how that just as the pump, the light system electrons gain energy very fast and its temperature increases very fast, but at the heavy phonon systems gains energy much slower, but after the pump, these temperatures start to come closer and closer. They exchange, and the subsystems exchange energy one with another, and we achieve a new thermalized state, but it is a different state at the different temperature. So these are experimental side of these investigations, but the theory is much more behind of this research, because such theory should be non-equilibrium just from the beginning, and it is the main problem in developing of such theory. And here, now I shall give you some ideas how such theory can be constructed. And first, what we started, we consider the system. It is the Hamiltonian of this system. We have some time-dependent perturbation, and for the times before some time t0, our system is in equilibrium, and we want to describe evolution of this system with the time. So we must solve the time-dependent Schrödinger equation, and the formal solution of this Schrödinger equation is just the wave function psi at some moment time can be obtained from the initial wave function for our equilibrium system by applying a so-called evolution operator. Okay, is the formal expression for this evolution operator. Also, when we want to conduct some perturbation theory for our equilibrium state, so in this case, we must pass to the interaction representation, and here are the evolution operators in the interaction representation. Now, we can calculate some mean value of operator at some time moment t, and this is just a generalization of the Heisenberg representation, but for the case of non-equilibrium systems. So we have operator A and two evolution operators on both sides. In the interaction representation, we have now this operator in the interaction representation, but also we provide, use a perturbation theory for our equilibrium state, and we have this additional evolution operator for the imaginary times or inverse temperature scale. So this ordering of this evolution operators creates the so-called Schwinger-Keldysh contour, which just this branch of this contour corresponds to the first operator. Then we have our measurement at some time moment t. Then we have back evolution, and this segment corresponds to the perturbation theory for the equilibrium state. So we can define Green's function on this contour, and by choosing this time arguments on different branches of this contour, we can calculate different Green's function. This is time ordered, anti-time ordered, so-called greater function, lesser function, and this one is the Matsubara Green's function. So this provides a formalism which for the calculation of different kinds of responses, and such Schwinger-Keldysh contour allows to apply all known techniques of the charge of the time orderings, of the diagrammatic techniques for such non-equilibrium cases. Next, how we include interaction with the field. Because interaction with the photons, it is the interaction with the electromagnetic field. So we use a column gauge, and when interaction with the field is described by such as shift of the momentum by the vector potential, we apply a pump pulse with the Gaussian envelope of such kind. And this is for the many-body Hamiltonian. In the case when we consider lattice models, like Hubbard model, then instead of such substitution, we use so-called Peierls substitution for the Hopin integral. So we have Hopin term, and in this Hopin term, we must use such Peierls factor, which gives additional phase when our charged particle moves from one lattice side to another lattice side. And for the uniform electric fields, so when we neglect of the magnetic effects of and only consider the effect of the electrical field, this gives for the, such energy shift for the band energy in our system. So pump. In such approach, the pump is treated as a classical field. Now, using this background, how we can describe the Raman scattering. So we must calculate the photon flux of some momentum QF, energy omega F, and polarization EF. So we must calculate mean value of the photonic number operator in our final state. This final state is just an evolution. Sorry, I use here different notations. U is an evolution operator of our initial many-body state, this one, and one photonic state. So it is a creation of the photon with energy omega I, momentum Qi, and polarization I over the vacuum state. So next, we consider both pump and probe, and consider probe much smaller than a pump, and expand our evolution operator in the probe pulse. And probe pulse we consider on a quantum footing, so it is expressed in terms of the photonic operators. And what we are interested in for the Raman scattering are these quadratic terms. This one. So the first order term gives us the current operator. The second order term is the square of the current operators, and also such a square term. This is the so-called stress operator for the electronic Fermi liquid.
5 minutes.
Sorry?
5 minutes.
Sorry. I have half an hour. Okay, so by combining these terms, we can obtain different contributions. So we have so-called non-resonant Raman scattering. Where we have the stress operators. Also, we have resonant contributions with current operators, and we have mixed operators, mixed contributions in the Raman scattering. Next, we are looking only in the non-resonant contributions, and for the non-resonant contribution, we have only this expression. It is a correlation function constructed by these gamma operators, stress operators, which are it is a convolution of these tensors with polarization operators for the incoming and scattered photons. And we also here introduce the envelope function for our probe pulses. Next, now I go to the consideration of the our model. So we consider a lattice model in the so-called dynamical mean field theory, when we replace the lattice model for the fermions on the lattice by a single side problem with some effective dynamical mean field. And what is and in this case, our band energy has such form. For the stress tensor, we have such expression, and this is up to some constant kinetic energy operator. And for the B1G, it is for the A1G symmetry. For the B1G symmetry, we have additional such factor. And based on this, we can find that in the dynamical mean field theory, first of all, the self-energy for electronic problem is a local one, and can be found from some effective single-side problem. And for the non-resonant scattering, Raman scattering, we have for the B1G symmetry only the single loop contribution, and for the A1G symmetry, we must consider all contributions. We consider a Fallikov-Kimball model, which is a simple model where we have hopping of the so-called d electrons over the lattice, which locally interacts with the localized electrons, so-called F electrons. And this model possesses, even such simple model possesses a rich phase diagram with including mode transitions and charge orderings. And what is fine about this Fallikov-Kimball model is that when we consider this algorithm of the dynamical mean field theory, where we solve where we have connection of the lattice problem with the single impurity problem, that we know exact solution, analytical solution for the single impurity problem, which allows to solve to find solutions for all Green's functions. Then, based on these Green's functions, we can calculate a photoemission spectrum. We can also calculate density of states, and the ratio of this spectral function to the density of states can give us the non-equilibrium distribution function, which we will use to measure an effective temperature for the one particle excitation. Also, we can calculate this single loop for the B1G Raman scattering. And also what we find is that for the Gaussian probe pulses, we have modified this ratio of the Stokes anti-Stokes lines by this one. And this relation will be used to measure the temperature of the two particle excitations. For the A1G symmetry, we have the full symmetry. We must consider all contributions, but in order to avoid solution of the Bethe-Salpeter equation, we use the fact that this gamma operator is now the average kinetic energy. So we apply the functional derivative approach. So we add some additional field in our Hamiltonian, and then such functional derivative will provide us the correlation function which we need for our Raman scattering. So for the A1G symmetry, numerically, it will be such expression. So we calculate mean value of the kinetic energy in the presence of this field, then without this field, and such ratio will give us our Raman response. So now I provide some results. So here are the photoelectron spectrum for this Fallikov-Kimball model in the metal phase, in the critical insulator, and in the mode insulator. In the insets are the density, one particle densities, which in the equilibrium should be Fermi distribution function, but here we have we see how it is. This Fermi distribution is modified with the pump, And also we observe that for such case of critical insulator, we observe an inverse slope here on the distribution function, which is the signal of the so-called negative temperatures in our system. So it is inverse occupation. And in this panels, I show you the results for the Raman scattering in the B1, for the B1 symmetry. And in the insets, I provide effective temperatures obtained from the photoelectron spectrum. It is these red and green lines, which correspond to the one particle excitations, and the black lines correspond to the effective temperatures for the two electron excitations, which correspond which were obtained from this ratio for the Stokes and T-Stokes lines in the Raman scattering. And for the A1G symmetry, response is much smaller because we have this additional screening of our excitations due to the full symmetry of this setup. And what we find is that our Raman response completely gone at the top when we have the maximum of the pump, but later it restores, but now we have a large contribution from the central peak, so which correspond to some elastic scattering. And so from this point of view, A1G symmetry is less interesting than the B1G symmetry. So, and here are my conclusions that we were able to elaborate some formalism for the time-resolved spectroscopy. For the strongly correlated electron systems, we use dynamical midfield theory, which helps us to simplify expression for the Raman scattering and to provide some numerical calculations. We find solutions for the Fallikov-Kimball model and show how the thermalizations of different kinds of excitations is developed, is evolved for such systems. And so this work was performed in collaboration with my former student, former PhD student, Oleg Matveyev, which is now a postdoc at Georgetown University, with Jim Friedrichs from the Georgetown University and Tom Devereaux from the Stanford. And thanks Armed Forces Ukraine for saving our lives, and thank you for your attention.
Thank you very much, Andrei. Any questions?
Thank you for the nice talk. Maybe it's a bit of a naive question, but you mentioned at the beginning about different timescales of different processes happening on femtosecond scales or attoseconds, like the Nobel Prize that was given in 2023. Can you say how far can the theory that you developed be extended? Like, because attoseconds obviously different processes, but for femtoseconds, or like what is the time scale?
So in our case, the time scale is width of our conducting energy band. For such system, it is around 1/10, 100 of the electron volt. So it is this time scale from it is 1 point. But also you see, there are just numerical limitations how far we can get, because all this system of the dynamical mean field theory, these are just, you must solve in the system of integral equations, all this -1 powers, these are just inverse kernels of this integral equations. So this is the most consuming part of our calculation. It is 1 point. Another point is that for the Fallikov-Kimball model, we have an elliptical expression for this Green's function. But for the other models, we must use some kind of solver how to solve this single impurity problem. And this is also the time-consuming problem. And also, just to achieve precision for the calculation, you must discretize this Keldysh contour up to the suitable discretization. And again, it depends on the frequency of your pump. What is the energy of your pump? It depends on the width of your pump, on the width of the half width of your probe pulse. So there are different aspects which you must consider. And so such kind of calculation, you spend a lot of time just to choose appropriate parameters for this, for such kind of calculation.
Okay, thank you.
Yeah, maybe I wanted to ask similar, but I wanted to ask more generally about uncertainty principle in the sense that you say it is the time you choose because you are interested in the width of the band. It is from point of view uncertainty principle, or
no. When I say that time energy, the energy scale is this T star, it is the half width of our energy band.
Okay, just because my feeling that your peaks are too narrow than inversely proportional to the time of this peak of this. So
no, these peaks are just. No, it is of the same order. So the width of the energy bands is of the order 1 or square of 2 of square of 2. So it is of the same order.
Yeah, just the question. So it is consistent with. So what is optimal? So optimal, I understand that it is if you are interested in such a width of the energy, you could choose the width of in time, of the pulse.
So you see, it is another problem about this uncertainty principle, because again, by choosing, by narrowing your probe, you are more precise in the time scale, but you are less precise in
this is what I'm
scale.
Right.
So I know about this problem. It is also the problem of how to choose the optimal probe pulse, and we have a separate article just considering this uncertainty principle for such kind of experiments. So it is a known problem. You always get something better, but you also lost something.
Okay.
I did for a while time-dependent photo emission, and we looked at the distribution of the Fermi edge, and then we tried to learn something, but it was so complicated because if you have a decay of excited electrons, then you produce particle hole excitation, and so it's a multi-excitation process. And is it really possible to learn something about the ground state?
I'm not sure about that you can get this from this simple model, because I could see the very simple model, but you see, what is this pump probe experiment? You have already your spectrum in the equilibrium, and you look how it evolves with the pump. So, and the pump just excites your system and involves your high energy states. And it depends on the energy scales. Can you reach this state or you cannot? So, but you see, I'm theoretizing this.
Okay.
Your theory is developed for a well-ordered crystalline system, okay? But what you can say about the possibility extending of such theory for a disordered system, taking into account local environment because it is well known that local environment in crystal and, for example, and glasses is very similar, but in a disordered system is more distorted.
So it can be applied, such approach can be applied also to the disordered system, because what is good about the dynamical mean field theory, that it is it is a theory which is a local theory. So you can consider different single impurities problems for different signs of your disordered system, and then you can average over your system. So there are many works in these directions with just using dynamical mean field theory for such solutions. So
Okay,
dynamical mean field theory is well suited to consider disordered system. So,
okay, thank you so much.
Thank you too.
Very interesting discussion. Okay, the next speaker is Yuliia Gusieva from Dresden. Go ahead.
So thank you for the nice introduction and thank you for the invitation for this workshop. And I'm happy to present you here some of my results. And today my talk will be about the composition tuned magnetic anisotropy in quasi-two-dimensional van der Waals magnet. So here is outline of my talk, and first I will briefly discuss about the class of 2D materials, the structure and key physical properties. Then I will briefly in short introduce the method we use, which is the crystal growth technique and characterization. And in the main part of my talk, I will focus on the magnetic properties of manganese, nickel, phosphorus, sulfur. So let's start from the motivation. The class of 2D materials are interesting for us because in one hand, we can study on them fundamental physical properties. They show the 2D physics even in 3D materials. Some of them can host an exotic quantum state. They show a wide variety of electronic properties from the insulator to superconductor. And in another hand, these unique physical properties together with the 2D structure nature allowed us a possibility for the application in heterostructure devices, for the spintronic or storage devices. But investigation of intrinsic magnetism was missing in the field of 2D materials. This was because, as we know, because the Mermin-Wagner theorem, one or two-dimensional isotropic Heisenberg system cannot have a magnetic ordering at finite temperature. But in a chromium-germanium telluride, in a few layers was found a stable ferromagnetic ordering. And this was possible because this material has a strong magnetic anisotropy. And magnetic anisotropy is important to stabilize magnetism in 2D system. And later on, it was also found a stable antiferromagnetic ordering in a monolayer of iron phosphor sulfur and in a bilayer of nickel phosphor sulfur. So the promising class to study 2D magnetism is the transition metal phosphorus trichalcogenides class. Now is the obvious question, what is M and which chalcogenides we have? So M is the main group of transition element cation, is a phosphorus, and as a chalcogenides we could have either sulfur or selenium. And we can have a composition such as iron phosphoselenide and so on. All of these compounds share a similar crystal structure. They have a layer structure where we have, when we consider a layer, we have such octahedra, chalcogenide or octahedra environment, where inside this octahedra can be occupied by the transition metal or by the phosphor of 2-dimer, and then they are distributed in our layer, and this gives rise a honeycomb layer structure. Then these layers stack on top of each other, and the stacking periodicity depends on the monoclinic angle beta, and between a layer we have a van der Waals gap. And this structure has common physical properties. Due to this is a van der Waals material, they are ductile, and because of a van der Waals gap, we can easily exfoliate our crystal by a Scotch tape until to the few layer or monolayer, and these properties allowed us to create a heterostructure or study physics in a monolayer. Regarding the magnetic properties, here you can see a different phosphor-sulfur compound. All of these compounds order antiferromagnetically below the transition temperature, but they have a different type of magnetic anisotropy, which depend from the transition metal which we have here. And remember, the magnetic anisotropy is important ingredient to stabilize magnetism in the 2D materials. And also, this material show a 2D correlation even in a bulk system. So, and now let's focus on the two compounds, which is the manganese phosphosulfur and nickel phosphosulfur. So all of magnetism in this compound should come from the manganese case and from the nickel case. Now when we put in our crystal structure these two transition metal, we will have a two different magnetic structure. I skip all of the non-magnetic element, and here is only manganese atom and nickel atom. And when we compare both of them, first you can see that in manganese case, spin point out of plane and see in the easy axis, and magnetic order could be described by the Heisenberg antiferromagnetic order model. In the nickel case, you can see that spin lay in a plane and A is the easy axis, and magnetic order can be described by XY antiferromagnetic model. Also, manganese is a Neal type antiferromagnet, which means that each manganese order antiferromagnetically with their three nearest neighbor, and in the nickel case, they form a ferromagnetic zigzag chain which order antiferromagnetically with each other. And regarding the magnetic anisotropy and strength of magnetic anisotropy, manganese has a weaker anisotropy compared to the nickel. And different anisotropy and magnetic structure promise tunability in the intermediate regime. And my research question was what happened when manganese is replaced by nickel in a manganese-nickel phosphosulfur. But because I want to study the magnetic anisotropy, I need a single crystal, because only on a single crystal I can study magnetic anisotropy, and this single crystal should have a high quality, because from the quality of a crystal depends our physical properties. And to grow a series of manganese nickel phosphosulfur with X0, 0.3, 0.5, 0.7, and 1, I use a chemical vapor transport technique. With this technique, I use 1 gram of stoichiometry mixture of my elements and 20 milligram of iodine as a transport agent. I put it in a quartz ampule, then I apply a temperature gradient, and in this hot end, the starting material evaporate and react with the transport agent and form a gaseous spaces. Then over the temperature gradient, it's transport to the cold end where it's crystalline and form a crystal. And in a few weeks, I was able to grow such single crystal with a few millimeter size. But then I have to sure characterize them, and for that I use a scanning electron microscopy, and you can see here some example when we compare backscattering electron image, which give us information about the chemical contrast. Here is no chemical contrast, and when we compare it with the EC image, which give us information about the topography of our crystal, you see that this is just step on the crystal, but not contrast. And also, additionally, to know the information about the elemental stoichiometry, I measure the EDX, and EDX agrees with the expected 1:1:3 elemental ratio. Then the next step, I have to determine the crystallographic phase, and for that I measure powder X-ray diffraction and all of the compound crystalline in a monoclinic space group C2M, and there are no additional impurity phase. And all of the Bragg position shift toward to the higher angle, which is in an agreement that nickel has a smaller atomic radius compared to the manganese. And I calculate the interlayer distance, and it also shows the monotonous decrease with the increase of nickel contents and follows the Verga's law, which means that we have a solid solution behavior and nickel successfully incorporate to the manganese phosphorus sulfur lattice. Then I try to model our crystal structure using the radial refinement and all of the break position and calculated break position and intensity in agreement with our experimental data. And the best result I observed to the model when I have a statistical distribution of manganese and nickel on metal sides. So now I have a single crystal which was characterized, and I can measure on them the magnetic properties. Here you can see a temperature dependent of magnetic susceptibility for both parent compound, which was measured at field of 1 Tesla on single crystal when I apply field parallel to the AB plane and parallel to the C direction. And in the manganese case, when we follow with the curve, first we see the upturn, then susceptibility reaches the maximum, and the shape of this maximum is broad, which is related to the spin correlation in these materials. And then below the transition temperature, it order antiferromagnetically, and you can see that we have a magnetic anisotropy, and C is the easy axis. In the nickel case, we also have a broad maximum, which is related to the spin correlation, then it order antiferromagnetically. And in this case, the AB plane is the easy plane and C is the hard axis. Now let's have a look how it changed in the intermediate regime. I separate it into the two graphs when I apply field parallel to the AB plane and when I apply field parallel to the C direction. And first of all, at 300 K, you see that magnetic susceptibility decrease with the increasing of nickel contents, which is in agreement that manganese has a high spin compared to the nickel. Then curve increase, reaches their maximum, and then it order antiferromagnetically. And antiferromagnetism persists as a ground state in the whole substitution region. And then here I separately plot nil temperature and maximum temperature, and it shows a non-monotonous evolution. They first decrease up to 0.5 and then increase up again. And by the ratio of maximum temperature and nil temperature, we can get information about the short-range correlation, and it's more than 1, which means that short-range correlation persists on the whole substitution series. And also for us, it was a surprise that we have this decrease of Tn, and we try to understand this, and possible explanation is what we know, that we have a stochastic distribution, manganese and nickel on the metal sides, which means we don't know if we have here nickel, and the three nearest neighbors could be manganese, could be nickel, could be manganese and nickel. So that means that we have some inhomogeneous magnetic environment, and this could lead to the suppression of Tn. Also, what we know, we have two different magnetic structures. Manganese has a spin 5 which point out of plane. Nickel has spin 1, which lay in a plane. And these two magnetic structure fight with each other, fluctuate, and trying to stabilize. And this all can explain this suppression of nil temperature. And now, what about the magnetic anisotropy? Here I measure a field dependent of magnetization as at the temperature 1.8 K. So here you can see a field dependent of magnetization, which was measured at temperature 1.8 K when I apply field parallel to the AB plane and parallel to the C direction. And in the nickel case, we can see that AB plane is the easy plane. Then for the 30% of manganese, it's still AB plane as a easy plane. Then for the 50-50 case, the curve almostly overlap, and it is a question if it's isotropic. But then for the manganese 70% of substitution, we see that now the C direction is the easy axis, and we have a spin flop at 1.8 Tesla. And for the manganese, C is the easy axis, and we observe a spin flop at 3.7 Tesla, which is in agreement with the literature. And the main conclusion from this slide that we have a switching magnetic anisotropy from outer plane to inner plane as a function of composition.
Maybe we can look in the editing mode, not in the presentation mode.
Yes, and then the summary. We have the first crystal growth of single crystal for the intermediate composition. We established the reproducible growth protocol for the intermediate compound, lattice parameter forwards the Verga's law. And all of the as-grown single crystals show the antiferromagnetic ground state. Unexpectedly, Tn shows a non-monotonously shift to the lower temperature as a function of a magnetic substitution, and enhances spin fluctuation due to the competing ground state and stochastic distribution of manganese and nickel atom explains this lower Tm, and the magnetic anisotropy switches from out of plane to in plane as a function of a composition. And I would like to send my doctor father of Professor Buchner, my current group leader, Anya Walter, and my previous group leader, Dr. Sai Asfaram, and all of you for your attention.
Thank you so much. Questions?
So these black crystals, they are conductors, conducting?
And they are semiconductors. They have a gap around 1.5 eV.
So this is, you have some dependence on the gap as function of this doping, right?
It's relatively new crystal. I firstly.
So it is just impressive that it is transparent and then they are black.
I know for the nickel that it's 1.8 eV. Then we have a calculation, but there are no experimental data.
Okay, so it's new. Okay.
Yeah, it's new.
Thank you for the very, very clear talk. So for the 50-50 case, you don't have side order of the magnetic ions, so you have side disorder. Is that a chemical necessity, or is there a possibility to get a ordered state out of there? And what if not? Why could one change manganese for, I don't know, some other iron or some other element where you get side order?
I think in this case, when I substitute a manganese and nickel, by the nature, it will be not possible because we have manganese and nickel valence state 2+, they are similar from the atomic radius and so on. But I have an experience when I substitute copper and chromium, which they have a different valence state. One is 1+, one is 3+, and in this case, it shows the order like zigzag chain. Then we can manipulate. When we have these two similar atoms, it's difficult to say where they should sit because they are like feel like they are equal with each other. Yeah.
I have a question. And I have a button. You commented on anisotropy, but can you also comment, or is there a comment on the magnitude that you recorded? Because I think one of the samples is a much lower magnetic moment.
Yeah. I show that two parent compound has a strength of anisotropy, you mean?
No, just magnetization magnitude on the
Yes.
axis scale.
But it's in agreement with that manganese has magnetic. Okay. I still cannot switch to the next this You mean, yeah? Or when I show
Nickel is a lot lower, right? Smaller z-axis scale.
Yes, yes, has a smaller z-axis, but this due to the crystal structure, because nickel has a bigger lattice and bigger the layers, bigger the gap, and the exchange interaction is weak. And that's why we have a lower the magnetic moment. In manganese case, layer more close with each other, and they have a higher magnetic moment and more effective exchange interaction. I think it's come from the crystal structure. Okay.
Yeah, just wanted to say it's very strange, yes, that the sample which looks like very two-dimensional, quasi two-dimensional, with such a nice planes, has no anisotropy, so it should be just really interesting coincidence.
Actually, we measure the ESR, and ESR shows some kind of anisotropy, they measure a gap, but gap is multiply anisotropy by the exchange. It should be also has some anisotropy. From the statistical magnetic measurement, it's look like isotropic.
Okay, thank you very much.
Thank you.
Okay, great. The next speaker is online, and it's Eduard Garbar.
Hello, do you hear me well?
Yes, perfect. Thank you.
Okay, so I'm going to talk about impurity states and thermodynamic properties of pseudo-spin 1 fermions. This my talk is based on our joint work with Pavlo Sukhachov, which talk today's morning, and I would like to thank the organizer for the invitation and for opportunity to present the result of our work. Of course, I would like to say a few words about motivation. Why this particular topic was studied, and what is the motivation? The motivation is provided by the presence of flat bands. This is a rather active topics. So what is the main reason for interest of condensed matter community in flat band systems? It's absolutely clear that as soon as the kinetic energy of quasi-particle is quenched completely, or like in flat band system, or at least quite soft, then interaction dominates. So we could realize very interesting, unusual states, phases of condensed matter system. Of course, twisted bilayer graphene is a quite well-known example of the realization of strongly correlated phases, superconductivity, charge density wave, and others. So all this boils down to the presence of weakly dispersing bands. So then a natural question in this connection: what is a system where flat bands could be realized? And a seminal paper which answered this question is a paper in Science. This is 2016 by Bradlin, Kano, Wong, Verniori, Felser, Kava, and Bernavik, by analyzing crystal crystal symmetry, they concluded that multi-band crossing could be realized only in 4 cases. In addition to crossing at discrete points, like in graphene, or while indirect semimetals, more higher order crossings are possible with 3, 4, 6, or 8 bands. Here I give actually the system I will talk today. This is pseudo-spin 1 fermions. So we see that basically geometrically this is energy spectrum. Basically at low energy it's graphene plus flat band shown here by green plane. Low energy isotropic effective potential for such multi-band crossings actually quite simple. So it is given by the product of the Fermi velocity, momentum, and pseudo spin. So we have energy bands given by this equation. Actually, it's quite easy to understand why we have such a formula. For example, we, without loss of generality, could assume that momentum is directed in that direction, and then what we need is just to use that projection, the quantum number of Jz. This is actually magnetic quantum number, so it's minus j plus 1 up to j. Then it's absolutely clear that for integer j, we could have we have odd number of crossing, and m can be equal 0. So in this case, a flat band could be present. If we have half integer j, like for example in graphene, then we have even number of crossing and no flat bands is possible. So this is kind of theoretical general picture, and real world realization is provided by cobalt silicate and rhodium silicate. And in these materials, pseudo spin fermions are realized at the gamma point. Okay, so then because the title of my talk is about impurity states in pseudo-spin fermions, I need to say a few words about bound state formation. So to have an heuristic insight in the bound state formation in system with soft energy momentum dispersion, it is useful to look at the eigenvalue, eigenenergy equation in momentum space. So here we have the wave function, and on the right hand side we have this integral, and in the denominator we have kinetic energy plus minus energy. So bound states correspond to negative values of energy. So what we see, if for example we look at the case when coupling constant tends to 0, then what happens? For example, suppose we consider conventional case, quadratic dispersion, where A actually equals 1 over 2m, so the standard Schrödinger equation in momentum space then we have. And in this case, it's clear, for example, as J tends to 0 for and energy, bound state energy tends to zero, then we will not have any solution for general potential. Only when this integral will exceed some value. Why it happens? Because in the infrared we have integration over three-dimensional momentum space, and in denominator, if we set delta to zero, we have only square, so it's absolutely convergent, so everything is fine. In two dimensions, of course, we have logarithmic divergence. Then we have well-known result that however shallow potential well possesses a bound state for the Schrödinger equation in two dimensions. But if we look, if we return back to 3D, we see that as power n increases, then we could have, for example, it's equals 3 or higher, then we could have infrared divergence. This means that actually no threshold for bound state formation should be for sufficiently soft energy momentum, and in particular in the case of flat band where n tends to zero to infinity, then we approximately have quenched kinetic energy at low momentum. As I already said, quenched kinetic energy in flat bands makes possible to realize superconductivity, strongly correlated phases. Okay, so then let me proceed to our study. We studied bound states in dice lattice. This is two-dimensional tight binding model. Here, this is a lattice. It was introduced in physics by Sutherland in 1986. As usual, so we have basically, you see, this is like conventional lattice in graphene with additional atoms in the centers of hexagons, right? Then, as usual in tight bonding models, we have standard equation of motion with Hopin parameters, and in this model by Sutherland, all distances are actually the same. So what about the energy spectrum? It's easy to find out the energy spectrum. It is given. So here I show this energy spectrum. So you can see that actually it's really basically spectrum of graphene given by green color with additional flat plane shown here in red, and like in graphene where we look at quasi-particles near K and K prime points, where chemical potential is situated, and in this case we have quite simple geometrical picture, just a cone with intersected by plane. Okay, so linearizing in vicinity of cone vertices, we end up with this effective low energy Hamiltonian. So it's linear in momentum. Its energy dispersion is okay. Oh, sorry, I forgot here. This is two dispersive bands plus minus Fermi velocity times momentum. They are Dirac cons, and as I already said, flat band. So then natural question could dice model, fermions in dice model could be gapped. And in the paper done by Gusenin, Terekhov, and me 5 years ago, where we studied gap generation in dice model, we found that it is possible. So the most general gap parameter actually is given by this term. So we have 2 possible gaps on the diagonal, M, M2, and -2. Here I plotted what happened in the case when M2 is 0.3 M. So we can see that it is possible. And in what follows, I consider the simplest case when M2 equals 0. Then we have, actually, this is completely flat band separated from 2 dispersive band by gap M. Okay, so to study bound states in this gapped pseudospin 1 system, we consider the simplest possible potential, namely central potential of potential well type. So maybe, okay. So we have potential minus V0 for R less than R0, and then potential is actually 0. So we have a circular potential well. In view of rotation symmetry, wave function could be represented in such a form. So because the Hamilton actually is given by 3 by 3 matrices, so wave function is actually 3 component, and then equation of motion reduces to the system of 3 first order ordinary differential equation for this thought function A, C, and B. Actually, the system of equation is mathematically quite interesting, because we have a system of 3 equations. Naively, we would expect that if we reduce the system to a single equation for one component, it should be third order differential equation. But in fact, it's easy to see if we use first equation to express A components through C, and the last third equation express B through C, then substitute in the second equation E. We went up if we it's convenient to instead of C to look for function F, so C equal R times F, and for F we have this equation. It looks quite complicated, but if we consider small potential and bound state in vicinity of flat band where energy is 0, actually, for example, this term reduces just to -1 and so on. So it simplifies. And what is unusual for this equation? So as I said, this is a second order equation, so this is good news. But here I present the corresponding similar equation for one component of graphene. And what we immediately see here, I show in red term F prime, V prime over E minus V. And in graphene, we have a different structure. So we see that in graphene, this is actually spin-orbit interaction. And in graphene, as soon as energy and potential quite small, we have quite familiar to us from atomic physics, spin-orbit interaction suppressed by the electron mass in the case of atomic physics. Here, this is it is in graphene. It is again suppressed by gap if graphene is gapped. But in the case of pseudospin 1 fermions, we do have a gap here, but still for gapped pseudospin fermions, we have this term. Actually, what we why I say so many words about this spin orbit interaction, because we immediately see from such spin orbit interaction that this interaction is singular at turning point where energy equals potential. So at turning points where E equals V over RT, we have a singularity. So this suggests that wave function should have some singularity or some unusual feature at turning point. And okay, indeed, what we found. So here I show wave function, actually the square of models of the wave function as function of dimensional m times r, and value m times r0. Here we choose 5, so this is the h of our potential well, and j is value of angular momentum. And we quite clearly see that wave function are strongly localized actually at turning point, and localization increases with angular momentum. Actually, additional a similar result actually was done by Wong, Pottelberg, Zhao, and Peters 4 years ago, without drawing attention to mathematical reason for such a strong localization. And additional surprise for us was that energy levels in vicinity of flat bands, they actually decreases at large value of angular momentum. This is quite unusual, because naively we would expect that a centrifugal potential should actually increase the energy, but we see a different behavior. And in the vicinity of upper band, so dependence on the value of angular method, it is conventional. Okay.
Eduard, you have a couple minutes left. Is that okay?
Yeah, okay. So then we calculated thermodynamical potential, computed entropy density and heat capacity. And so we see that entropy actually monotonically increases with temperature and saturates at as temperature increases. And heat capacity has a peak, and then after passing the peak, it actually decreases and tending to zero. Such a behavior is actually quite familiar in spin system. For example, let me remind you, entropy and heat capacity in one de-icing model. So it's quite similar. So the reason, of course, that in our case, because energy of states with large angular momentum actually has low energy rather than higher, then when we increase temperature, there is no states to fill, and so heat capacity decreases. Of course, if temperature increases further when we enter the upper band, then it's start increasing again. So let me provide you conclusions. So main conclusion of our study is the spin-orbit interaction in vicinity of flat band is singular at Turing point for gapped pseudo-spin 1 fermions. Second, our observation that wave function of bound state are strongly localized at Turing point, and localization increases with angular momentum. And as a result, temperature dependence of entropy, density, and heat capacity per unit volume is similar to spin system with energy spectrum bounded from above. Thank you very much for your attention.
Thank you very much. Questions? Well, I would like to ask if there are crystals that have a dice structure. It's a very interesting structure.
Unfortunately, no. So actually, there are artificial photonic systems which kind of simulate dice lattice, but unfortunately, how to say, solid body realization is unknown. So the best what we have is 3D system, cobalt silicate and rhodium silicate. This is in this system they experimentally pseudo-spin 1 three-dimensional fermions were observed.
Okay, thank you very much. Let's thank the speaker again.
Thank you.
Okay, we saved the best for last. The hottest topic will be Oleg Feya from Kyiv, and it is about machine learning.
So good evening. It's really a pleasure to be here all these 3 days. I have only like 15 minutes here. It was really a pity for me that my talk was the last when I saw it, when I saw the schedule, because it's like you feel this tension that you should do something, you should make a talk till the very last, till the very end. But somehow I turned it in an interesting story, and I hope you also will enjoy it. So my talk is crystal structure prediction using evolutionary algorithms at machine-learned interatomic potentials. I will start with a slide which I use in my course in Kyiv Academic University. This is the very first slide of my course, and I'm usually talk about computational materials design. So what is it? We have structure. From structure, we can calculate properties. You have a lot of tools to calculate these properties, and we saw in the 3 days a lot of analytical methods. We saw computational methods. You can use WASP, Quantum Express, a lot of programs like FPLO from Dresden, and also you have experiment to evaluate it. My research interest is to create a structure from composition. So when you don't know when you don't know what you should get, or you know what you should get, but maybe you will get something interesting with this result. So it's like going from composition to structure. There are a lot of methods to do it, like Calypso, XTAL-OBST, RSS. So I'm familiar with all these methods. And when I started to make this work which I now presented, it was like 2022. It was end of the year. It was like blackouts in Ukraine, and I had a talk from Bogdan Semenyuk, who is now my PhD student, and he told that he used to be an experimental, but because of this blackouts, it's impossible to make any experiments. And he told that he also liked to make some programs to programming, and if I can give him some interesting task. So I told that, yeah, I have interesting task. So we have these programs, but there is a thing which I don't like in this program. So you should use DFT to calculate the structures. So you need a lot of researchers to do it. We had not these researchers. And also I wanted to have the code in which I can do everything I want, because these codes, they're usually like closed, like black boxes. And we took ASE, it's Atomic Simulation Environment Python library. In this library, we can find these genetic algorithms which are rather normal for mathematics. So how are they used to create new structures? We have so-called potential energy surface. So every point in the surface is some structure, some atom coordinates, some interactions between these atoms, some lattice parameters, and if you want to predict some structure which can exist in the nature, so you should find the global minimum of this potential energy surface, and so you should find this minimum. For example, on this picture, yeah, you have this landscape, energetic landscape, and you should find this minimum. And genetic algorithms, they allow you to do it not by searching every point, because we have infinite number of points, but like of searching some regions of this potential energy surface. For example, you can search this place, then by using some operators, variational operators, you can move, for example, to here. Then you can, for example, change lattice parameters of the structure and move to here, and you will search this landscape. And also each structure is the energy of each structure should be evaluated somehow. We can use DFT. It's solid, but it's really long, and the structures usually really creepy. So you will spend a lot of researchers, like 99% of your researchers, you will spend on relaxing the really creepy structures, and the structures then they will go to the trash to find like only this one structure or like dozen of good structures. So we started to use this ASE library with these algorithms, and then we added some relaxator, but not DFT relaxator. So our goal was to predict crystal structure from chemical composition using genetic algorithms to search this energy landscape. And we do this work with Bogdan Semenyuk, who is my PhD student. This is his photo in Saxony, Schweiz, in Saxony. So it was like 2021 when he was in Dresden on short stay. And first version of this code was like revised by Alexander Isayev, our collaborator from Carnegie Mellon University, and I think that Sergey Frolov knows him rather well. So it's a great pleasure to work with Sasha. And so our first version was to use GAUP. So it's a program which uses this interatomic Coulomb interactions, but it is really fast. But the problem is that it's only Coulombic interactions. Yeah, it's like it can give like 90% of the whole energy of the structure, but this 10% they matters, like even 0.1% sometimes matters. Then we moved to, and also GAUP has some problems. It's really hard to install it. It's really hard to start the parameters, to start the calculation sometimes. Then we moved to this so-called MLIPs, like machine learned potentials, and we tried to work with AIMNet 2. So this is the network which was created by Isaev and his team, but we had failed with it. So we spent some time by trying to include it into our program, but we had really not good results. And then we understood what was the case. So AIMNet was trained on moleculars. So it was not trained on like 3D solid bulk materials. And we moved to another potential maze, which was created by a team from MIT, and we made this H algorithm. So the name is by Bogdan. Firstly, he called it like H was for ASA, G for GAUP, E like espresso, quantum espresso, because we made this quantum espresso calculations after we got structures from GAUP. But then we moved to maze, and we liked this name H, so he asked ChatGPT, and it proposed atomistic genetic exploration, which is okay for me. So we have ASE library as a base. We add genetic algorithm to search this landscape. We add maze potentials on the precision of R2 scan MetaGJ, which makes the calculation like in like 0.5 seconds or something like this. And we made this like H workflow. How we compare structures? We compared them using fingerprint function. It takes some atom, then it searches the environment around this atom, so it searches the neighbors atoms and goes like with the spheres, and we can create such plot which is like DNA code of the material. So here you see in some quartz system, in some silica system, CO atoms. So it's like orange for CO. So it's like blue is alpha quartz. You can see here some small blue things. CO and the orange is created by our algorithm structure, and we see almost that they match almost perfectly. So it means that our structure is very close to reference structure. So, and this is how it looks like when the structure is far. So we tried to get BISCO, which has 30 atoms in unit cell. It's rather hard case. And you see that reference and our candidate, some crappy candidate from our calculation, they are really not matches. Yes, so this is how we, this is like 42% of match, which is not enough for good result. And this is how we relax structures. So we applied these BFGS schemes like Borides, Fletcher, Goldfarb, Shannon, quasi-Newton algorithms, which is very common. Then we also add algorithm like molecular dynamic, like fire. And here is some comparison of these methods in how we calculate this energy or how we calculate forces, and then we choose like the best algorithm for each case. So now I have only 4 minutes. I had 2 test systems. Maybe I will skip them because I think this is the most interesting. So in Monday, I asked Jeroen what structure he wanted to calculate, and he told that he wanted to create rhodium bismuth 2, like platinum bismuth 2, but we change platinum on rhodium. And I knew nothing about the system, so I asked Bogdan to start this calculation till the middle of the day, last day in Tuesday. We get some results. I have showed them Jeroen, and he allowed me to include them into the presentation. So this is the search. This is like 10 populations. Each dot is a structure. The lower dot is the best. So we have like one metastable state, another metastable state, third metastable state, like in these lines. Then we have made like our rating like 10 after 10 populations, like Forbes likes like 30 under 30 or something like this. We made this best. We made these best structures, and we got that the best structure is like cubic structure, PA minus 3. And Jeroen also told that the structure is cubic. But then we searched the other structures in this huge, really huge table. It's like thousands of structures in this table. And we have found like, for example, this 14 space group structure P21C after number of PA minus 3. So we have a lot of metastable structures for this system, and I like gathered it I spent like an hour to gather these things. So this is reference. This is I took from a materials project database like alpha rhodium bismuth 2. We got almost the same thing. I think it's really the same, like 9 milli-electron volts per atom. Then we got like this monoclinic thing. Then we got another structure, C2M, which is layered. So I now platinum bismuth 2, and I thought my previous thought was that it will be like this, and we really got this structure. And maybe we can then work on it more. Our King 2005 cubic system only on the fourth place. So after recalculation, so this is recalculated structures in the same basis because I wanted to compare them with reference structure. And we also got some another structures. I saw that maybe 64, 58 symmetries. So, okay, we also have 58, but I didn't have time for it to get. So this is how I compared like reference structure and generated structure by fingerprints. We see that so they don't match ideally because it has they have not ideally equal lattice parameters, but we see that only small shift and we will get one from another. And this is this 12 and this is structure with this C2M space group, and I found also like in 5-minute search the article with the same structure which was so I think that we matched. So we that this result is matched well. This matched well. So somehow we got a bunch of good metastable structures. And I also asked Ira Kovalchuk about the system, and she synthesized in the night this the structure. Okay, she synthesized it during her master student stay in Dresden in 2018 or 19. Yeah, but then she switched to platinum bismuth 2, but she found these results for me, these really old results, that somewhere in EFW you have this material, and you even have this diagrams, powder diagrams, and maybe we can I'm not experimental, so maybe it's also will be useful, these things. So that's all. Thanks for your attention. Дякую за увагу. And thanks for this great workshop.
Okay, tour de force for Ukrainian science to complete a research question in a couple of days. Maybe you can continue like some other questions, maybe Majorana, for example.
Unfortunately, Majorana is beyond my expertise.
Yeah, that's very impressive. Okay, you found out things that I knew. That's great because they are right, I think. But the main question, so the question is still open. Platinum bismuth 2 forms in this crystal structure 157 inversion broken. So is there any inversion broken layered structure of rhodium bismuth 2 that is somehow close in energy to this, or is that still an open question?
To platinum bismuth 2 symmetry, yeah?
Yeah, or similar to it, at least inversion broken, yeah.
I think maybe this can be. So I only searched like very small part of this table. So I should take a look of it, and it's only after 10 populations. So 10 populations, not like usually we make like 30 populations to get.
We have a few days more, so that's great.
Hmm?
Yeah, thank you for the great talk. My question is, could you please comment on how does both complexity and the reliability of this algorithm depend on the number of atomic species in the chemical formula?
So if we add some atomic species, if we tried it for like triple compounds, it works great. But then we tried it for BISCO. With BISCO, it was really hard because it's like 5 compounds and 30 atoms. We got rather close structures to the reference structure, but it was still like 0.6 electron volts higher in energy, but it was like 0.6 electron volts per unit cell. So it's like per atoms you should divide by 30. But we didn't get it, and now we like gathering statistics for publication, and that's one of our cases which we are working on to get BISCO. So I think when we will get BISCO, we can publish this.
Thank you.
And upload on GitHub for everyone's use.
So do you make some assumptions about translational symmetry? Size of the unit cell?
You mean translation symmetry in some specific case?
Well, for example, in this one, do you assume some size of the unit cell or maximal size of the unit cell?
Yeah, so you see this potential surface, yeah, it can be infinite because distances between atoms, they can be an infinite number of these distances. So we make some constraints, like the distance between atoms, so not bigger than this and not lower than this, because like 0.1 angstrom between atoms is like colonical barrier, yeah, Coulomb barrier. So it's impossible. It's unphysical thing. And then we also make some constraints, make limitations on the cell. So I don't want to see like super huge unit cell with really rare atoms in this unit cell. Yeah, this is constraints, and also we green dots is randomly generated structures. By randomly, I mean some of them are really random, like we just use these constraints on distance between atoms and on unit cell. But some of them are randomly taken space groups, and we just take space group, then we field in the space group randomly atoms, and see what will happen. Sometimes when, for example, if for example, I know that platinum bismuth 2 is 157 space group. I can specify it, and it will create some number of this symmetry. So it will make the search faster if you will know this information. Sometimes it's a good idea to include so-called seed. So seed is some structure. So we know that the structure, for example, exists, or the structure is good, and then algorithm tries to then algorithm took it into this as one of these dots and used in further calculations.
Okay, well.
Yeah, so quite interesting also for me as a synthetic chemist. So did I understand correctly, right? So when we have these ternary phase diagrams, did we heard it in the talk this morning, I believe, from Eteri, right? You can find different or new phases basically that nobody ever
perhaps yes, yeah.
So in principle, did I understand you correctly? I can give an input from, let's say I look at this iron, lithium, arsenide. I can give these three elements as an input, and then basically I can calculate through the entire space groups, and it will give me compositions that
some some structures. You see, what we also want to add to the program is convex hull creation. Maybe this is what you need. You mean this triangle, yes? This triangle. So it's convex hull diagram. So I mean when we place all low energy structures on this diagram, and then we see which of them are stable, which of them are not stable. So this search, I knew that rhodium bismuth 2 is like stable stoichiometry. So the question was what polymorphs we can get from this thing. Then I think we will move, like we will take rhodium 2 bismuth 2, rhodium 3 bismuth 2, and so on, just to create like this two elements diagram. For ternary diagram is the same thing. So we can play with the numbers and like make a search for each composition and get like this triangle.
Well, that sounds very promising. Thank you very much.
But for convex hull we had to work some time because it is not yet implemented. Yeah. So we just need to use use by hand, like to change the stoichiometry by hand and make calculation for every stoichiometry, but it's not automatically changes.
If you both promise a quick question and answer, I can allow it with my button.
Thank you, great talk. My question, how is mass interatomic potentials are obtained, and can you filter it for specific composition in your program? Use not all, but some, several of them.
So you mean how we filter like really bad structures, or if I want structure with some parameter, how I can filter it?
From where you have rhodium bismuth interatomic potential?
I have it from so this mass MLIP. So it was studied on this pre-studied on a lot of structures, and as I know, it's like materials project database and some other databases. Yeah, and it knows how to deal with these atoms. We also tried. So this is what I skipped. We tried to get CDV, charge density wave structures, because it's one of our topics, but we unfortunately got only this high temperature phase with 164 space group, so it matches perfectly, but we didn't get charge density wave. So we even tried to make our own potential by learning it on CDV database, which is not very high, but we asked some professor to give us his database. But then we failed again, because this interatomic potential, it's like one one atom interactions. So, but for CDV we need at least 2 atoms interactions, because it's many body interactions. And so the thing, the data on which the potential is learning, it's like limiting factor. So if there is some new physics should arrive, we will not get it. So it's like limitations of this machine learning methods.
Okay. Let's thank the speaker. And then thank all the speakers of this session. And there's probably some other item on the agenda, but since I'm sitting here, thank all the speakers of the workshop, the organizers, the hosts. It's been wonderful to be here. Thank you so much.
Okay, looking here on the program, I think we do not have any more coffee breaks. So we just will finish our session. So this is farewell to say something. While I'm thinking what to do, I would pass the word to Jeroen, maybe to say scientific part to finalize it somehow. If someone want to say something, please, Jeroen.
So yeah, so I think to do a scientific summary is beyond anybody's capacity. It was great actually to hear about such a broad topics from quantum computation to synthetic chemistry to machine learning. And we even found some connections between those different topics. I think this year we were broader in the subjects, which was intentional, to be able to include more and more diverse colleagues. The important thing is to do our science, to communicate our science, to find ways to work together. And I hope that this few days helped in that manner. I hope we can keep working together, strengthening the ties that we have, and hopefully also create new ones. I want to thank a few people. I want to thank first of all the colleagues from COW for organizing everything so nicely. Where's Olha? Well, she's not here. Thank you very much, Olha. You did a great job. Also together with Sylvia in Dresden. I want to thank my co-organizers. Asle is here, Ben Büchner is somewhere in Dresden, Christoph Wolfeld is there, Maya Fagnori is somewhere on the globe or in an airplane, and Sasha here. Thank you very much. And as is usual, we should keep the things, thank the ones that keep us safe, not only in Ukraine, but actually in Europe, which are the armed forces of Ukraine. Thank you.
Yes, thank you, Jeroen. I also, of course, wanted to thank to every one of you to stand to the end and to stand this workshop. It is quite dense. It was quite dense. It maybe was less dense than in Kyiv, but it's still quite dense. We will think how to proceed in future. And actually, the ideas were next year we planned it to in Kharkiv. If the war is finished, if not, then probably in Chernovtsi. So, but we speak that we change it. But going back to this workshop, of course, Jeroen already mentioned Sylvia, and the program actually moved just smooth because the people behind it, and Sylvia made all this programs and so on and site, and it was very nice. All the organizations here was made by Olga, and I want also to thank local organizers from university. It was very kind from them to do everything. We had also from Kiev a number of PhD students which they were ready to do, but they do almost nothing because our hosts organized everything. The special thanks to Oleg and of course to Christy. They did a lot, helped a lot. So thank you very much. Some organizational things about talks I already uploaded to our YouTube channel the first 2 days. We will improve it and put some in program to some links, but just have a look. If you have some suggestions to remove either talk or some parts, we can always do it. So if you, for example, do not like it, about today's evening, communicating with people, I had impression that it is much better not to go somewhere all together, because in Lviv it is very nice, especially that you go by some small groups around the city and you see some places. So if you need some suggestions and helps, we still have a possibility to do it. I think at least most of us maybe will move now to hotel and then continue to explore the city from there. So finally, I thank you all again, and we finish with this.
Maybe some finish photo on the stairs. On the stairs.